atoms. So please go ahead. Yeah.
Okay.
Yeah, sorry, I didn't introduce myself. So, myself, I'm Sagar. I'm a senior researcher. I'm working with Professor Saptarshi Chaudhary. So I was a PhD student here till 2023. I worked in quantum gas mixture experiment of sodium and potassium. So during my PhD, we have built that. And now then I was a postdoc from 2023 to 26 in European Laboratory for Nonlinear Spectroscopy in Florence. And I worked with Paolo Di Natale and Gabriele Sant'Ambrosio. Then there I built, that was like first of its kind in Italy's direct laser cooling and trapping of polar molecules. We worked with calcium fluoride polar molecules. Then I joined here from February. So now I'm kind of taking a leadership role with my professor to build India's first neutral atom quantum processor with rubidium atom. So now up to you. Okay, please go ahead.
Thank you. I think this works for me here. Yes, I'm Athanasios Laliotis. I work in the LPL in the north of Paris, if you remember sort of the map that Fabienne showed. The university that I work with is, actually I forgot to thank the organizers, obviously, for this, sorry. For organizing this conference and for getting us here. Sorry, I shouldn't have said conference. This was not the good word. Okay, this workshop. It's a bit too early, forgive me. So I work at the University Sorbonne Paris Nord. And just brief introduction of my sort of CV, my background. I studied in Greece and in the United States. I did my thesis at Imperial College London in a subject that's kind of unrelated. It was in integrated optics. Then I did also a postdoc at Imperial College London working with Ed Hines on atom chips. And then since 2008, I'm an associate professor at the LPL, where I work basically with hot atom vapors, and I use them to probe the near field of surfaces and basically Casimir-Polder interactions or any other kind of interaction that can happen in the near field. And this is more or less what I'll be talking today. This will be an overview of kind of this subject, focusing a little bit more on Rydberg atoms. Okay, I think that's pretty much it. So just an outline of my talk, just to have an idea what I'll be talking about. I'll talk a little bit about hot atoms, how, I mean, I guess you know what it is, but how can we actually use them in order to probe the near field, because this is not so evident. Vapor cells are macroscopic cells at the end of the day. I'll introduce Casimir-Polder physics. I'll take a little bit my time. I guess most of you are not familiar with it, even though it's basically just dipole interactions at the end of the day. I'll talk about our experiments that we do with excited atoms. I'll focus a little bit on the temperature dependence, which is kind of something we did a few years back in my lab. We measured the temperature dependence of interactions. And I'll talk a bit about Rydberg surface interactions of the Casimir-Polder type. And Rydbergs, as we say, have a lot of exaggerated properties, so they can be used to probe other types of fields. And I'll say how we use them to probe the near field, the sort of electrostatic fields in the near field. And if I get time, I'll tell you about how we can do maybe something more with metamaterials. Okay, hot atoms. For people that work with cold atoms, they're just there to lock your cells, your lasers, I guess. But you can also do other things with them. For example, people do metrology. They make portable atomic clocks in these very nice, beautiful, microfabricated cells. They are portable, not the best stability, but they're portable. Of course, we all heard that you can use them to do sensing, magnetometry, electrometry, and so on. But you can also do some fundamental physics with them. For example, people study quantum fluids of light with atomic vapors, collective effects. It's a bit tough, but you can do it. Spin noise. And our thing, the thing that we study, is Casimir-Polder interactions, which take a place at the nanoscale, let's say. So the question is, how do we actually probe them with hot atomic vapors? Because, well, vapor cells are macroscopic, and we need information on the near field. So the way we actually do it is by probing reflection, doing reflection spectroscopy. That's one way, instead of transmission spectroscopy. And transmission spectroscopy here is sort of, in this case, when you look at transmission spectroscopy, you would imagine that you'd get something like that you would be adding the coherent contribution of all these atomic layers in your signal. So essentially, when you get the signal in the transmission, the longer the cell, the bigger the absorption. This is kind of how it works. But reflection doesn't work like that, because when you start adding the contribution of each layer to the backward direction, you actually have a phase factor here. And this phase factor actually averages your signal out. You can increase the size of the cell, but the reflectivity will not change, the resonant reflectivity. And essentially, your signal will come from a thin layer that comes, it's in the vapor, that's in the sort of interface between the window and the vapor. And it's basically there because the atomic motion changes due to contact collisions with the surface. So the polarization of the medium changes, and this is where the signal comes from. So reflection, selective reflection as we call it, is sensitive at a probing depth that's lambda over 2 pi, let's say, typically, which is about 100 nanometers. And it's also a subdoppler spectroscopy because it's mostly sensitive to atoms that are slow. Atoms that are slow move basically in this layer, whereas atoms that are fast fly out of it, and their contribution gets averaged away. So this is nice, but there are not only contact interactions that change the atomic motions, but there are also some more long-range interactions. I mean, if I'm to use a sort of a language that is also there in the cold atom community, that are of the dipole type, and these are the Casimir-Polder interactions, and our signals here are sensitive to this type of interaction. So you don't have to do much, basically just measure the reflection instead of the transmission.
Can I ask?
Of course, yeah.
Would you say that the fact that it's sensitive to small probing depth
Mm-hmm.
is similar than what we do with optical coherence tomography in the eye? You know, when they do the imaging of the eye, they go only at those thin depths.
I'm not
You're not
sure of that. I mean, we could maybe talk about it. Yeah. So, yes, where was I? That's one way of doing it. The other way of doing it is by nanocell spectroscopy. So in this case, what you would do is you don't have a macroscopic cell. You actually fabricate a cell whose thickness is nanometric. We fabricate some cells whose thickness ranges between, let's say, 50 and 1,000 nanometers. We fill them with vapor. And then here, transmission and reflection follow the same rules, but because the thickness is so small, both of them are sensitive to Casimir-Polder interactions. And here, the probing depth does not depend on wavelength. This is a good part. The good part, you can actually change the probing depth, and typically we can say it's lambda over 2. So again here, we are sensitive to Casimir-Polder interactions, which I will sort of try to describe a little bit more in the following slides. So let's start with the simplest description. I kind of like it because I can understand it much better. So this is an electrostatic description. So the atom is a fluctuating dipole, and when it's close to the surface, it's actually interacting with its own image. And if this is an electrostatic regime, these fluctuations are instantaneously correlated with the image. So a minus here, a plus here, a plus here, a minus there. You have two dipoles, and these two dipoles basically attract. And there's an attractive electrostatic potential. 1 over Z3 is the distance dependence. D square, the fluctuations of the dipole moment. And this parameter here that I call image coefficient, which basically means that your surface is not a perfect conductor. It's epsilon 1 minus 1 divided by epsilon plus 1. So this interaction is anisotropic, and what it does, it perturbs the free atom Hamiltonian. And when you do this perturbation theory, you find that you need to sum over all the allowed dipole couplings in order to get the shifts, which is what we will be measuring. and you find a coefficient here that we sometimes call van der Waals coefficient. Some people nowadays call it Casimir-Polder coefficient to avoid any sort of confusion over Z3. And C3 actually depends on the dielectric properties, but also on your given atomic state. It's not the same for a ground state and an excited state. Okay, that's a simple approach. Another approach that's probably a little bit more complicated was introduced by Casimir and Polder back in 1948. They described the problem as an atom interacting with a fluctuating vacuum. It's kind of like a Lamb shift, but the quantum vacuum here is modified by the reflective boundary. So you pick up a distance-dependent term, and this distance-dependent term is the Casimir-Polder interaction. Now, in their description, if you go very close to the surface, which means that the distance is much smaller than the relative, sort of than the wavelengths of the relative dipole couplings, then you recover the electrostatic law. But if you go a little bit further away, you find a different scaling law. And this was famously measured by Ed Hines back at Yale. And since then, many other groups have actually studied it at many sort of distance ranges and so on and so forth. Okay. This, of course, is valid for ground state atoms. If you actually want to look at an excited state atom, you also have to account for emissions like spontaneous emission. And this adds another term that is kind of like a retroaction term. And this was actually taken nicely into account by Willy and Sipe in the 80s. This is a paper I would recommend. And then if you look at the near field interaction, here you get the same dependence. But if you go to the far field, there's a different dependence. Is sort of, it has an oscillatory term, and it decays much faster. It's kind of like a classical dipole interaction. So this description here is a QED description, and it also accounts for some effects that electrostatics doesn't account for. And this would be dispersion. The dielectric constant depends on frequency, and electrostatics doesn't account for this. And also thermal fluctuations. Thermal effects are not taken account unless you do the full QED calculation. So I'd like to talk a little bit about this effect, temperature effect, that we measured some time ago in my lab. So thermal Casimir-Polder interactions. Let me just introduce again, like in the simplest way I can, how this sort of would work. Normally, thermal emission, when we think about it, we think about black body radiation. So black body radiation, you have some density of states. You multiply them with the number of excitation, the Bose-Einstein factor here for the photons, and the energy per excitation, and you'll get some broadband spectrum. Now, if you look at the thermal emission of a real dielectric, actually, real dielectrics also have what we call evanescent modes, polariton modes. And these actually, they turn out to be the density of states, the local density of states depends on distance. Actually, the closer you go to the surface, the more evanescent modes you have. And it's actually 1 over Z3 dependency. And they also depend on the imaginary part of this coefficient, epsilon 1 minus 1, epsilon minus 1, epsilon plus 1, which actually turns out to be a sharp sort of function, bell-shaped function around the frequency that is the polariton frequency. So essentially, if you go far away, you get something broad. But if you go very close, thermal emission starts becoming very monochromatic thanks to these polariton resonances. So if you put an atom very close to a sort of monochromatic evanescent radiation, here is the atom. The atom is kind of a two-level system here, A and B. This is an evanescent sort of field, the hot surface created by the hot surface at the polariton frequency. And if this sort of field is red detuned compared to your atomic frequency, then the atom will be attracted. And if it's blue detuned, it will be repelled. And this term, which is kind of like a dipole interaction, if you want, it actually plays right into your Casimir-Polder physics. Like it's a term that you kind of add to your usual sort of other non-temperature dependent stuff. So this one is a sort of dispersive curve, the shift, but you also have a lifetime dependence because, of course, like the atoms can also absorb. So you can actually do the calculations and you can find to convince yourself that C3 actually does depend on temperature. And the main factor to keep in mind here is this sort of factor, this real part of epsilon minus 1, epsilon plus 1, that is kind of a dispersive function. And the Bose-Einstein factor here that basically says the more you increase the temperature, the more photons you get in these things. And you have a C3 dependent coefficient. And you also have a Z3 dependent lifetime, okay? That depends on the imaginary part. But I won't talk about lifetimes here. Okay. This is a nice effect, and we'd like to measure it to do some experiment. Well, when you do an experiment, you need a real surface. And the surface that we use is sapphire. It's a nice surface. It's very durable. It doesn't interact with cesium, so we like it. Also, it has a nice kind of isolated polariton frequency at about 12.2 microns. So if I take this surface as a reference and I plot the C3 coefficient as a function of some atomic frequency, like what I would find, I see the polariton resonance is here, and I would find that if I'm actually to the left and I increase the temperature quite a bit, I get a C3 that now becomes negative, so the interaction can become repulsive. And if I'm on this side of the resonance, I can increase, I can have some huge attractions, and the interaction can become, well, hugely attractive. Now, the problem, of course, is that these are kind of infrared frequencies, and the ground state atoms do not really have resonances at these frequencies, but excited state atoms do. So we're not at the Rydberg level yet. Here, for example, if we look at the 7p½ sort of atom, it turns out that the strong dipole coupling is in this transition, 7p6d, which is actually very resonant to the polariton frequency, and this is the position in this graph that I showed you. So if I do this experiment, I probe the interaction of this level with the sapphire surface, I heat up, I expect to increase the C3 coefficient. And that's what I'll try to do. This is my experiment. First, I talk to my Armenian collaborators that actually make some high temperature sapphire cells. This is the one here. So this can go up to 1,000 even more K, 1,200 K, let's say. And I'll build up a selector reflection experiment to probe the interaction here. And my transition, the one that I would like to do, the spectroscopy here that I'm interested in, is 6s7p. And this will actually probe the interaction of the 7p level. Okay. So I can do this experiment in my lab, but before I do this, I actually need to find the dielectric constant of sapphire. I mean, this would be good to know, because here actually I put some more or less things, and these more or less things can be important when I'm here. So I go in, and what I do is well, not me, my collaborators in Orléans, to the south of Paris, we give them a window. And what they do is they measure the emissivity or the reflectivity is kind of the same for a big range of frequencies, between 10 and say 40 terahertz here. And then they measure the emissivity at various temperatures, because the dielectric constant can be a function of temperature. We assume an analytical function that is basically a sum of Lorentzian resonances for the dielectric constant. This is kind of basic stuff, I guess. And then we take this spectrum and we fit it, and we find the width, the amplitude, and the sort of frequency of each of these resonances. And this gives us the dielectric constant, and then we can do our calculations to find epsilon minus 1, epsilon plus 1, and find the polariton frequencies. Good. And then I can do the experiment. So I'll show here some spectra. I'm not sure how interesting it might be to you, but it gives you an idea of how well our models fit the sort of data in this sort of case. 6S, 7P, one hyperfine component. We actually increase the temperature of the window. We can also play with the temperature of the vapor, meaning the pressure of the vapor, which actually changes a little bit the line width of the transition because you introduce collisions. And we fit to find the C3 and the gamma. And actually, you see that the models work very well. And we can extract them with sort of kind of quite good confidence, let's say, levels, the C3 coefficient. And you can see that it increases with temperature, as I would expect. And I can show you also what the final graph would be. So C3 actually kind of explodes here. This is the C3 in kilohertz micron cube. I point that out. And then this is temperature. So I start pretty high, and then I sort of go up a lot. This would be my data. And this would be the predictions I would get when I use the sort of dedicated measurements that I sort of did for the dielectric constant that include the temperature dependence. So there's a mismatch between the two. And I guess there are two ways to explain it. One way would be that, well, there are some systematic effects that I didn't account for in my sort of experiment. But the other way would be that if I want to get information on polariton frequencies, which is really a near field effect, my far field predictions that I used that I extracted from this type of measurements are no longer very accurate. So actually, the most accurate experiment that can give us the polariton characteristics is my experiment that uses the atom as a sort of Casimir-Polder quantum probe next to the surface that can sense polariton and frequencies and dielectric properties in general. So this is also one way to look at it. And this is actually was published a few years ago, but also other temperature-dependent sort of stuff you can find in this publication much, much earlier on. How am I doing with time, sir?
20 more minutes, 20 minutes.
Okay.
Why is it deviating more at very high temperatures?
Sorry?
There is no deviation at a higher temperature.
So actually, if you look at it, these are the predictions actually from our data. This line here would be just some extrapolation if I use the temperature dependent, the room temperature measurements, just using QED sort of. And this would kind of fit very well, but not so well when you actually heat up a lot the sort of your system. So you can probably see a sort of temperature-dependent dielectric constant in this part of this of the curve. But then again, what we actually predict seems to be not so much reliable. And we think that what we predict with these measurements is not reliable, and not what we predict with these measurements. But okay, this has to be tested a bit further. But you know, I think the hypothesis that atoms can be used to get information about this near field resonances is a very valid hypothesis. Does that answer the question? Okay. So this is pretty much what I wanted to say about temperature. And I'll just move on to atoms that are now a little bit more excited. Because, well, I said maybe we get to do some Rydberg stuff. Okay, this experiment started some time ago. And Rydberg atoms, of course, I don't have to convince you. They're very interesting because of these, again, exaggerated properties, which means that a lot of the properties have strong dependencies on the sort of principal quantum number, the effective quantum number. And of course, we heard it before, the radius changes as n square. And when the radius changes as n square, the fluctuations of the dipole moment would change as n to the power 4. So if I look at the C3 coefficient of these guys, they would actually vary very quickly with n. So I can use it to measure giant sort of Casimir-Polder interactions, and this is pretty much what I want to do. I'll be focusing on this type of measurements. But another thing that might be interesting to sort of think about, like we haven't measured it yet, but it might be an interesting thing to do in the future, is if you actually look at this, so actually as the atom sort of starts becoming bigger and bigger, the sort of size starts comparing with the typical atom surface distances, and your sort of dipole approximations are not valid anymore. You have to do your multiple sort of development. And the first sort of term that you might be sensible to is quadruple interactions that are minus C5 over Z5. This is a kind of novel dependence that we could measure with Rydberg atoms, sort of in some sense in the extreme near field, because this is like somehow very close to the surface. Okay, I'll be focusing more on this term here. This is very difficult to measure. And this is my experiment. Yeah. This is a good question. Actually, no. When you actually try to do the quantum averaging, it turns out that the terms average to 0, because essentially what you would want is, you'd want to go up and down, up with a dipole and down with a quadrupole, and you cannot have it. Like you cannot have a cross term, like in this, in the averaging. The detail is in the averaging. So in order to get a non-zero averaging, you have to find a dipole coupling that is also a quadrupole coupling, and this doesn't exist. But you can have a dipole octupole terms. This is not an absolute rule. I'm not sure. I'm not clear. Okay. I guess it's a little bit on this. Well, okay. Maybe we'll discuss after. Yeah. Like it comes back to the slide I showed in the beginning, where you have IMJ, JMI. So if you have quadrupole, you have IMJ, JQ. Okay, we'll talk later. Okay, but you cannot have, these terms are 0, we calculate them, dipole quadrupole, but dipole octupole are non-zero, they can exist, and we calculated them as well, just for fun. Okay, so the experiment here is this one. So we have a cell. The cell, like I said, varies from 50 to 1,000 nanometers. And the experiment we do, we measure transmission and reflection. And this is a pump probe experiment. Here we first pump the atoms to the 6p level, and then we probe with a green laser all these levels that you can see here. The C3 coefficients, I show them here for you. Just remember again that here we're talking about hot atoms. They're actually really very hot. We heat it up a little bit to increase the signal. So we have collisions, and we actually try to characterize these collisional properties in big cells before we actually go and do the experiment in the thin cells. So this is the experiment, and I'm going to show you some data now on this sort of 6p 16s line. This would be the transmission, and this would be the reflection. So you have here the sort of transmission that basically means that like some light is absorbed. This would be the sort of volume, the transition in the volume, like for a very big cell, this would indicate the transition. And what you can see as the sort of thickness decreases of the cell, you'd see that the curves shift further and further to the red, which is really very nice. It's a visible sort of proof that there are interactions going on there of the Casimir-Polder type, shifting things to the red. Okay, but you'd want to be a little bit more quantitative. So what you do is you try to fit them. So you fit them using your model that takes into account everything, Casimir-Polder interactions, movements, and so on and so forth. And what you get is this type of curves. Now, like I said, we fit for a C3 coefficient, but we also fit for the width and a sort of shift that can be explained due to collisions. So the C3 that fits best kind of works with the sort of theoretical predictions, but the fits are not perfect. The transmission works very well, but in some cases the reflection is not really perfect. And this is really not a good sign. We're not used to it. We would like to see what happens. But that's not the end of the story. The other part that doesn't look so good, and it's evidence that there's some other interactions here, is that these parameters are not constant. Actually, they can vary a lot with thickness. And this is what we get. We get a broadening that depends on the thickness, okay? And it increases with a sort of scaling that's kind of comparable to Casimir-Polder interactions. And also, like the shift, there's an additional shift that you actually have to account for. And this cannot be explained with collisions. So,
You can go back to the previous slide, just for 435 nanometers. How out of this you get the width that you plot in the next slide? And
yes,
that fits me in this case of spectrum.
you're talking about the reflection spectrum?
Yeah, thank you. It was the transmission?
So the transmission, yeah, gives you a sort of an effective line width.
But the next slide was reflection?
No,
Sorry.
the next slide was like we fix the parameters for both spectra here.
Sorry, can you show the next slide? Because
Yeah.
I made my experiment fits.
So
this is
Gamma
gamma
is,
delta, but it's taken from the transmission.
it's taken from transmission and reflection when it fits, because well, here
okay.
you can.
That was my question. How
no,
can you
okay.
get parameters out
No,
of
no, no.
this?
Like here you cannot get. Here it's
Okay.
basically the transmission. Yeah.
So then you use only transmission.
Yes.
Okay,
Yes.
thank you.
But well, when it fits, it fits good for both. But reflection doesn't fit all the time. It's like, okay. So you get these things, and we think that these things happen because of electrostatic interactions that happen close to the surface. Casimir-Polder is not the only interaction. There are other effects that could be described as systematic if what you're interested in is Casimir-Polder physics. So just to convince you a little bit that this is probably due to electrostatic fields, I'll just plotted the curves for two different states that actually have polarizabilities, static polarizabilities of opposing signs. You can see the 16S kind of shifts nicely to the red, as you would expect it, but the 15D stays to the blue and sort of goes maybe sometimes a bit further to the blue, which is an evidence that you have something else that is not a Casimir-Polder type of physics. And it's probably stark DC, interactions. So how would this work? Like the tricky part here, I would say, is that you need to find some sort of distribution that kind of works and gives you distance-dependent stuff, because this would be the shift here, and it depends on the sort of intensity of the field squared. The polarizabilities scale a lot with quantum numbers, so this is probably not a big surprise. But if you have, for example, a uniformly charged plane, this will give you a constant field, and this is not very interesting. It wouldn't show in our experiments. It will just be a little shift. But we think that in reality what you have is randomness, and these random deposited charges actually only look uniform if you're far away. If you go very close to the surface, as we go, and at distances that are typically sort of the separation between these random charges, then you pick up a randomness, you see the randomness, you pick up a distance dependence, and you pick up fluctuations, and these fluctuations can give you broadenings, essentially. So we feel that this randomness can explain things relatively well, what we're seeing. And we did some theoretical models in order to actually see how this would work. So first we sort of calculated what happens when you deposit randomly charges separated by an average distance. And actually the intensity of the field scales surprisingly simply 1 over Z2. And the standard deviation would actually have a more complicated dependence, and scales actually let's say on average, faster than the average sort of intensity. And you can also do the same assuming dipoles. And the reason we use dipoles is because cesium atoms, when they stick to the surface, they sort of act like permanent sort of dipoles. And if they are scattered here, then you get another very simple sort of dependence. So this intensity would scale as 1 over z to the 4. And the standard deviation will now scale a little bit higher with like a higher sort of scaling laws. And so you would expect the sort of broadening to scale at something with scaling laws that are faster, let's say. So obviously in real life, probably you might have things in between the two. So maybe what you would expect is some sort of power laws that would be between 2 and 4, let's say, and something higher for the sort of broadening that you would expect, like a distance-dependent broadening. So as a first step, what we did, actually, we actually have been beyond the first step, but what I would present here now is we actually try to take a sort of an ad hoc sort of description of these interactions and actually fit in order to find a scaling law that fits best. And this is what we find. So now we introduce an electrostatic shift that would depend on these sort of factors that we actually fit for, 1 over z to the 2.8, 1 over z to the 3.5 for the broadening. And then these parameters, which be the collisional shift, the collisional broadening, and the C3 coefficient, will all be sort of fixed. And we don't vary things other than the exponents here. And what you get is that things actually work surprisingly well. So the fits work much better for the transmission. They work spectacularly well for the reflection. We can understand the signals. These factors are constant. All of them are sort of interpreted with the same parameters and so on and so forth. So we feel that we actually we're very close to explaining things, and actually, like I said, we've been a little bit further and we've done fits that actually can provide information on what's the charge, what's the dipole, how far are they separated, and so on. How am I doing?
5 more.
5, okay. I'll finish ahead of time. Okay, so this is pretty much what I wanted to say for electrostatic fields. So we are sort of working on that at the moment. My PhD student, Esther Buteri, is working on it. But let me give you a glimpse of what we want to do in the future. So we said, okay, maybe we can use atoms to sense resonances. Maybe we can use them to sense electrostatic fields with Rydberg atoms. What about using them to characterize the near field of more complicated structures, like metamaterials? So, and what I think it's very interesting to study is metamaterials that work in the terahertz range. This couples very well with Rydberg atoms, obviously. And these are essentially look like microfabricated LC circuits that resonate at terahertz frequencies. And people that work at these frequency ranges, they use them to fabricate devices. Because they're not easy to get these devices at this sort of frequency range. So when you excite them, you get some sort of near field sort of exaltations of the terahertz fields. And people usually, in order to characterize them, because you need to find a sort of reliable way to characterize them, is by what we call scanning near field optical microscope. It's kind of a simple thing if you think about it. What you do is you take an oscillating tip and you scan it around your device, which you excite by a terahertz external source. And of course, this field, this tip would scatter the terahertz, the local terahertz field into the far field, and you use a terahertz detector in order to measure it. And this works relatively well, but it's kind of a slow technique because you have to scan things all over your device. And of course, it creates artifacts because this tip is a macroscopic object, so it shadows, fields, and so on and so forth. So what we propose to do now is to go into something that looks a bit like a quantum version of this sort of thing. So what we do is we want to use vapors, Rydberg vapors. We submerge the terahertz resonators in the Rydberg, with the atomic vapor. We excite the resonators with the terahertz beam, and now we also excite the atoms with our Rydberg beams. Okay, and then the atoms locally, they can absorb terahertz photons because, of course, we heard that they're good detectors of terahertz frequencies, and they can emit optical photons at frequencies that are distinct from our laser wavelength frequencies. And this basically will convert terahertz to visible, scattered away, that we can actually measure efficiently with our detectors, with our cameras, let's say, that we position there. So this is something that we want to do in the future, sort of that kind of combines measuring fields, terahertz fields, and measuring resonances, because this is a sort of resonant device here. Okay, so I'm pretty much done. Just like to thank my group before I do so. So this is our Paris group. So Esther Buteri, who is here and here in these photos, is actually the PhD student that worked on the Rydberg atoms and has produced all these measurements that I showed. She's actually writing her thesis now. That's why she's not here. But Hippolyte, that is with me, like he also has posters, and I also will present a poster on these things. Biplaub is an ex-PhD student in my group, also working with Rydberg atoms. And Paolo Pedri is actually a theoretician that has done these calculations, especially with the fields and so on, and spectra. So it's kind of been very useful for this sort of project. And finally, I would like to thank people in the Rostock group. I have a lot of collaborations. We have a lot of collaborations internationally, especially with Rostock people like Stefan Schill that do theory for us, and also other people in Brazil, Uruguay, Singapore, Japan, and who knows, maybe in the future, maybe India as well. So with this, I'd like to thank you for your attention.
Thank you very much. Thank you. So questions?
Hi, I have one question. Is it possible to study this in a like 1D waveguide problem? I take a waveguide, truncate it, put a reflective boundary condition, and keep the emitter coupled to this waveguide away from this. You can't hear
I cannot hear you very well.
Oh, I was saying that is it possible to study this in a 1D waveguide problem?
Mhm.
Okay, I take a waveguide, cut the waveguide, and put a reflective boundary condition.
Yeah.
Keep the emitter away from that boundary so that it is like away from that
You mean
hardware.
like make a cavity or something?
Not a cavity. The waveguide will be still a semi-infinite waveguide, so it's not a cavity in that sense.
Okay.
But I'll keep the emitter just a bit away from this reflective boundary,
Okay.
so that it's still interacting with this hard wall boundary condition. So I was thinking about simpler, lower dimension and a simpler setup like this. Would it be equivalent?
I'm not exactly sure of the geometry that you're thinking about. Like,
Okay.
what would you want to measure? You would want to measure the Casimir-Polder interaction?
Yeah.
So you could do it with waveguides. I mean, so I'm not really sure what you are
Thinking of the
what you're
geometry.
thinking of the
Oh.
geometry, but like, I'll just give you an answer that is probably not your question, but people do see Casimir-Polder interactions when they're close to waveguides, like fibers, tapered fibers, for example. Like they can be sensitive to Casimir-Polder interactions, and also not just fibers, also waveguides as well.
Okay.
So you can do experiments with atomic vapors that sort of submerge waveguides. And I guess you can play with your waveguide structure to sort of have what you want. But I think interpreting spectra is something that might be a little bit trickier than you might think. I mean, so this is why sometimes I point out that it fits well. It's not so trivial for it to fit well.
Okay.
So yeah, I hope that kind of answered you.
Okay, thanks. Yeah.
Any more questions?
Okay, thank you for your talk. I wanted to know, you showed us your fit for the collisional broadening and the shift, and so I understand that these are the values that you extract from your fit. But do we understand physically the origin of the collisional broadening and why is it so big? It's 2 gigahertz. I'm not used to this.
Yeah. Okay, so this collisional shift. So actually, this is we measured it. So Rydberg atoms, they interact very strongly, like they sort of with. I think this is basically with ground state atoms. But the pressures are really high. Like this is about, let's say, 1 torr, half a torr. And, like usually you have, for example, I think it's 10 to the minus 6 at room temperature. So this is like, like really, really cranking up the density of the atoms.
Okay.
So the temperature of the side arm is at 250 degrees.
Okay.
So this is why the interactions get to be like
And
really.
this is why you get very
Yeah,
large, very wide resonance.
yeah,
And
yeah.
for the shift, do we understand it all, or like
This shift. Well, you say that this is big for me. Like this is peanuts here because like.
Okay.
Yeah, the shift is the same way. Like when we actually do the experiments in the volume, like we take a big cell and we try to measure collisional effects, they give these orders of magnitude
Okay.
pretty much. Yeah.
Because when I was interested at some point in the physics of cells with buffer gas, these
Okay.
would be typical numbers, but so I was wondering if there are anything.
Yeah, so like if you have like cesium-cesium collisions are much more effective in broadening the lines that buffer gas would be. Like buffer gas essentially considered velocity changing collisions, whereas these ones they can be much more efficient into broadening and changing the populations and things like that.
Okay.
So, yeah.
And for your value of C3, can you imagine going higher in N so that you can get a higher value and make your experiment a bit easier for you? But is it technically feasible? And
Yes, you can imagine, to do so. Like it's probably a good idea to do so. Like the thing that is a little bit tricky is that the higher you go, the smaller the signal you actually get. So, like like these sort of scalings, sometimes they don't work in your favor, and actually.
you mean for the same power of the laser?
Yeah, so these are
Okay.
linear spectroscopy. This is linear spectroscopy. So the power of the laser will not give
Okay.
you so much, will not really, you will not gain a lot from adding more power to your system.
Okay.
You would gain a bit, but not so much as you would imagine. So it gets more and more difficult to measure, and your signal-to-noise ratio will go down. And I don't know if I showed this enough, but these signals can be, 10 to the minus 5, and if you want to squeeze them even more, and so on. So this is something indeed that can be done. It probably should be done, but there are some difficulties involved, and signal is one of them. Like,
Okay.
I mean, yeah, like. People have probed higher states in thin cells, like Tillman-Pfau, for example.
Mm.
There's a paper. They've seen weird stuff.
Okay. Okay.
Yeah, so like I'm not sure. I don't know if our new models can explain that weird stuff, but we'll see. Yeah.
Okay.
Yeah.
Thank you. I don't want to monopolize. I have also
No,
many
it's
questions. So if
Yeah,
anyone wants to ask a question, go ahead.
Poster break. We are having poster break as well. So,
Okay.
Yeah. So can you have more questions during the poster break?
I
Okay, okay. One more question, yeah, please go ahead.
Yep. Thank you. I was wondering what happens if you put like a mixture in your cell. Would you just get two overlapping spectra, and can you then discriminate contributions from two different species or not?
A mixture of species. Sorry, why would you do that?
No, just out of interest.
I
what
would
happen?
say that, yeah, you'd get a signal for both of them. Maybe you get some inter-species collisions, so you probably be broadening some transitions a little bit more. I have to think of what would be the gain. Well, I guess maybe you can gain by actually having a cell that you can probe more transitions. Yeah, actually, yeah. Maybe not such a bad idea, actually.
Okay, if so, then please thank the speaker one more time.
Thank you.
Thank you. So now we'll be having Professor Manu Kumara Manjappa from Indian Institute of Science and Science. It's like 10 minutes drive from here. After we'll be having a poster break. Then right after, Almon will talk. Then after that, Professor Abhishek talk will be there after the poster session.
Is it okay?
You, Almon.
Yeah, that's good, I think. That's good. Okay. Yeah, I think let me just check once. Yes, good. Thank you. Thank you very much. Thanks. Okay. So, yeah, good morning to everyone. And yeah, my name is Manu Kumar Manjappa, and I'm an assistant professor at IAC, just the other side of the road. So, particularly, yeah, to say that I was here as a project student, and I think, yeah, coming back here after I think 15 years, and then giving here a talk, yeah, it's a kind of, yeah, nice to know. And this auditorium is really the same as 15 years back. So it's really nice to have these things going. And so yeah, firstly I would like to thank Professor Sanjukta basically for his inviting for this nice workshop, Indo-French workshop, which is also really termed as chai, right? Yeah, it's nice interaction and sessions and all. So I think mine is basically expertise in terahertz. I think it was a nice kind of conclusion at the last talk to kind of tell about what is terahertz. Particularly, it's a new frequency domain in the electromagnetic spectrum, which I think many will be not aware about. But I think so. My today's talk is particularly in terms of looking at the condensed matter systems in the terms of terahertz spectroscopy. Like we perform transient terahertz spectroscopy as well as some of this, pump probe engineering of this, quantum systems. Particularly here in this talk, I'm talking about 3D Dirac semi-metal, which is cadmium arsenide. So before going into the talk, I just want to give a brief outline, quickly that about what is the research activities that's happening in my lab, which we call it as terahertz quantum and nanotechnology lab. Particularly, the one domain that is today's talk is focused on is looking at picosecond physics in materials, where we kind of excite with optical as well as terahertz pulses, and then to look at the dynamics in the electron phonon or electrodynamics that happens, where nanomaterial spectroscopy and pump probe measurements, and also focused on some kind of ultrafast spintronics measurements as well, to look at the demagnetization or spin processes, diffusion processes, and in this type of magnonic systems. And in the second pillar that we are working is particularly related to the terahertz cavity QED, where I think maybe we have a lot of things to talk about in terms of the interaction of this the quantized electromagnetic field in terahertz cavities with solid state materials. Particularly, we focus on some of these antiferromagnets as well as some ferroelectrics and paraelectric systems and superconductors and some of these particular things. They mainly to explore again the Casimir type of interactions with solid state materials in this particular system under the strong and ultra strong polaritonics. Okay, and the third domain is basically a terahertz metamaterials. I think the last talk actually briefly said about what is terahertz metamaterial, where you can make microstructures which can resonate in the terahertz frequencies, and what is we are interested is also like in terms of sensing using these metamaterials and performing some kind of structured light engineering, and also for 6G communication. That is one of the interesting thing coming for the technology aspect of it, and reconfigurable metamaterials. So this is some of the outline of the research, and if you are anyone interested in collaboration, or I'm very happy to discuss in these particular aspects of it. So moving on to my talk today, that I'm going to briefly tell about what is terahertz and what is terahertz spectroscopy is all about, and particularly some of the results that we recently got in terms of spectroscopy of cadmium arsenide, which is basically a 3D Dirac semimetal, which is quite analogous in terms of 3D analogous to the graphene, which is well studied, and where we observe semimetal to semiconductor phase transition in this terahertz spectral regime, and also that is associated with the population inversion in this particular material. And also we observed some spectroscopic observation of terahertz gain, which is one of the first observation in this particular material so far, and so I'm going to discuss some of these results here. Okay, to kind of briefly introduce what is a terahertz particularly, is that you all like well aware about the electromagnetic spectrum, where in all internet we actually see microwave, IR and visible, where terahertz becomes invisible. But there are a lot of interesting aspects in this particular spectrum, which in the sense that it's also a picosecond pulse, like the temporal resolution will go to picosecond compared to nanoseconds in the gigahertz, or like some of these things. So for some ultra fast devices in terms of electronics are kind of are being looked at as an device. So to look at these properties of terahertz, where the frequency is typically defined in like 0.1 terahertz, which is 100 gigahertz to 10 terahertz. That is the range of frequencies deal with, and the lambda, which is sub wavelength in sub millimeter type of wavelength. And as I said, the time is picosecond, and energy are much smaller than the thermal energy as well within the thermal energy, particularly 0.4 milli electron volt to 40 milli electron volt, and this is the KBT, which is basically spans this entire thermal property of this. So looking at it, so what is interesting with this terahertz is that, so this behaves like it exploits some properties from the photonics aspect, like some of the photonic characteristics of the light is well utilized here, and also ultra fast, as I said, and picosecond time scales, and non-invasive spectroscopy is one of the important thing, and also semiconductor sources like QCLs and all are well exploited in terms of terahertz applications. And looking at the electronic band of this side, like microwave, where the transport properties, the measurements of the the dielectric constants and all this stuff, the electronic transport properties can be performed using terahertz pulses, and again it's transparent to most of the semiconducting materials, similar to the longer wavelength, and it can offer larger bandwidth and all. So this is one some of these interesting aspects, that it has some vibrational or rotational frequencies of molecules to kind of perform some biomolecular sensing, and this is basically focuses in the intraband or intersubband transitions of an semiconductor. Okay, so these are some of the interesting aspects. So what our thing is that we are trying to exploit terahertz fingerprint in quantum and topological materials. Particularly, I'm trying to list out some interesting aspects across the domain. So for example, for topological materials, which are like what I'm going to discuss today is about 3D materials and Dirac semimetals and all. So there is an exciting aspect of Landau physics to study with magnetic field, and there is a root scattering, and Dirac plasmons actually appear in these particular frequencies, and bulk band gap of these topological insulators lying in this spectral regime. So compared to superconductors, there is a superconducting band gap, are the binding energy, which is in this particular energies, and also Josephson plasma and phonons and all are very interesting collective excitations that can be looked in this particular spectrum. Similarly, for magnetic materials, as interesting aspect of high frequency fermions and antiferromagnetism, and as I said, that ultra-fast spintronics, which is basically one of the domain of terahertz frequencies, and strongly correlated materials, which helps in terms of looking at charge density waves, phonons, all lie in this particular energy scale. So that makes it quite interesting to study the terahertz, the spectroscopy in terms of both steady state as well as the transient response of the materials. Okay, so going into the briefly how the spectroscopy is done. So basically, this is a schematic of the terahertz time domain spectroscopy. What we perform is basically, we don't actually kind of directly detect the photon, but we detect the temporal pulses that is emitted from the terahertz sources. So for that, we have a femtosecond pulse, which is basically an ultra-fast laser, which is 800 nanometer for this particular system, what we are using, on 1 kilohertz rep rate. So that's been sent, and the beam is split and sent as one of the probe beam for the detection of terahertz, and one is sent for the emission, which is basically drives any kind of terahertz emitters, particularly a nonlinear crystal, which has a very good N2, or like second order nonlinearity, so can emit multiple frequencies, and terahertz, like lower frequencies, one of the radiation that comes out, and we use some set of parabolic mirrors to collect these broadband frequencies that are emitted in this, and then we have the sample here too. And so, and at the other side of it, we use something called electro-optic sampling technique, which uses a Pockels effect. It's basically an AC Pockels effect, where you have a terahertz pulse as a voltage, which is basically acts upon the crystal, which changes the birefringence and induces a birefringence in this crystal. That changes the linear polarization that passes through the probe, which is optical, which is linearly polarized. So looking at the change in the polarization of this optical probe, we can map the electric field of the pulse that has been incident on this thing. So that's basically a non-destructive type of measurements, where you can directly measure the electric field of the pulse, and if you do the Fourier transform, this is how electric field, pulse looks like, which is this is the volts and units, and then this is the time delay, which kind of achieved by changing the path between the probe and pump. So that helps us to scan this entire terahertz pulse, okay? And if you perform, once you perform FFT, then you get a nice bandwidth that is in the terahertz spectrum, and also a phase which is associated with this spectrum. So with this, you can measure the transmission is this, and then you can extract refractive index of this entire material, which is frequency dependent conductivity, can be extracted using this particular measurements. And so in another point is that when you, in the same setup, if you introduce another path to a pump, so you can also perform optical pump terahertz probe measurements, so which helps in terms of exciting the sample, or like any kind of material, to higher energies, and then to look at the dynamics, like the cooling dynamics or the recombination dynamics that happens in materials using terahertz as a probe. So this one of the example is that, so for example, if you are exciting with an energy of the light which is higher than the band gap, so you all know that you create electron hole pace with electrons, actually are electrons in the conduction band, so but they take some time with the interaction to come down. So this is the dynamics that is being mapped using as a terahertz amplitude, like transmission amplitude, as it changes with respect to the dynamics of it. So this pump probe delay is basically controlled by this. So you can see that a nice dynamics where you have a complete excitation where electrons are in the excited state, and then they relax back to the ground state, have like valence band, right? So this gives us something like photo-induced conductivity, which is also called terahertz photoconductivity. So where you can look at the change in this transmission of the terahertz can help us to kind of look at what is the photo-induced conductivity in the material as a function of frequency. So this is what we will do in our experiment, to kind of briefly tell you. So this is what in our lab currently in IISc, we have an ultra-fast laser, and we have like optics all arranged to get this terahertz pulses here, and this is the pulse that we have in our lab. And I think tomorrow there is a visit. I will be happy to show the lab, and we can discuss more about it. So to coming to the work that is being done in our recently is that the material that we are working with is cadmium arsenide, which is basically a 3D Dirac, or like 3D Weyl semi-metal, where it has a tetragonal structure, and it's the electronic properties, because of this Dirac type of, or like massless Fermi electrons in this entire three-dimensional part, makes it interesting as a 3D analog of graphene, where so the properties such as like it exhibits very high, ultra high mobility of 10 power 6 or 7, which is similar to graphene, and high stability because of the crystal, which is basically three-dimensional and large area fabrication, and it also exhibited negative magnetic resistance for spintronic application, and also in terms of terahertz plasmons, terahertz nonlinearity has been looked at in this particular material. And in this work, particularly, I'm just going to review, like, there's for the first time in they observed a quantum Hall effect in 3D, particularly cadmium arsenide. It was the first observation in the 3D material in using cadmium arsenide crystal. And this is the Nature Material paper in 2015 where they reported ultra high mobility of order of 10 power 7 in this single crystal cadmium arsenide. And there is a point contact superconductivity also is shown with respect to the tungsten tip, showing the superconductivity at its behavior at the interface type of effects. And again, negative magnetic resistance that I pointed out is that gives a negative magnetic resistance MR in this particular domain of it. So a lot of interesting aspect as a crystal. So what in our study we used is a thin film. Basically, the cadmium arsenide material was grown using molecular beam epitaxy, MBE grown. And this is high quality, and it's basically a polycrystalline. There are some domains which orient in a different way. You can see it in the TEM measurements. And this is the configuration of the material. We have 50 nanometer of cadmium arsenide, and there is a buffer layer of cadmium telluride in between, and there is a sapphire substrate. And so the idea is that we actually want to study the terahertz dynamics in this particular material, and to look at is there any kind of non-equilibrium terahertz the population inversion or gain in this particular system, right? So how much time I have?
You have
10 minutes. Okay, good. So now I think this is well-known phenomena in condensed matter that how the behavior of insulator and metal behaves with temperature, right? So basically, the resistance of the insulator kind of goes down as the temperature increases, and where the metal resistance increases because of the scattering mechanisms, and this is a number density related, right? So similarly, this to look at in the cadmium arsenide in a single crystal, which is pure single crystal. So this exhibits purely like a metallic property, which is a semi-metal behavior. So that's well observed. But when you make a thin film of this, because of the defects and on the polycrystalline aspect of it, so this entire material behaves like almost like a semiconductor, with resistivity going down with increasing temperature. So this has been well reported, and also there is a band gap which opens, very small band gap as you go to the thinner film because of the confinement which changes. So this is what basically a semi-metal, and there is a semiconducting behavior with respect to the crystal and thin film. So what we now, the same material, we had this from the same collaborator, which they published this work. So we did, again, this is a conductivity plot, what we plotting here, but these are resistivity. So in the same things, we observe that conductivity, the same behavior when you do the DC transport measurements, like you have IXS and the for 2 probe measurements here, particularly in this case. So but when we perform the terahertz measurements in the same things, we can extract, as I said, that we can extract conductivity using the terahertz pulse, right? So when we looked at the conductivity of this terahertz at what particular frequency of 0.25 terahertz, what we observed is that the conductivity behaves similar at some temperature, but as you cool down lower than some certain temperature, then it starts to increase again. So this is just that we are probing the conductivity of it at higher frequencies. So this was actually a kind of interesting aspect, because usually in a DC measurement we don't see it, but in terahertz we actually look at this type of behavior where you have a semiconductor, but it turns to be a metallic at lower temperature. And so this is what we looked at. But now I think I'll show you the data in further. So what happens here is that because we are trying to probe the interband and interband interactions in this, because as I said, the terahertz is high frequency, there is an intraband, the electrons, the response we are looking, and also the interband response at higher temperature. So that basically shows that at some temperature it actually behaves like a semi-metal with the intraband aspects in the picture, and as it increases, then interband excitations with the band gap of, because the measured band gap from this measurement we calculated around 3.5 milli electron volt, which is in temperature is around 40 Kelvin, and also in the frequencies of similar terahertz. That I showed you that the 1 terahertz is basically 4 milli electron volt. So here the terahertz is in that regime that you can explore both intra and as well as interband type of interactions here with temperature. So this is what we further did was different frequencies we plotted this conductivity, and as you see that as it goes to higher frequencies, there is intraband because of the band gap, the frequency is higher than the band gap. So then you kind of start to see a semiconducting behavior that happens in this particular system. So this is quite consistent in the case that this is what the conductivity spectrum. So what we plotted is that at this frequency, it shows a semiconductor to semi-metal, but as you go to higher frequencies here, because there is an interband transitions picks up, so you kind of come to a close to a semiconducting behavior as the conductivity actually increases as the temperature increases. So here, and this is all steady state where we have only terahertz as a probe to look at how the conductivity is behaving. And in this work, continuing that, we did transient measurements. What basically in this particular material happens is that when you excite an electron from conduction, valence band to conduction band, you have all the processes like thermal interactions or like cooling processes, particularly in this Dirac semi-metals. So you have, if there is electrons are excited, and if there is a Coulomb screening in this particular, because they actually are interacting with each other, if the Coulomb screening is smaller than in the system, then there is basically Auger processes dominate, in the sense that it becomes quite longer, and electron hole recombination is actually of the order of the same Auger recombination. It means that when the electrons tries to cool down, they come down without any kind of time lag. But this is where we usually see the terahertz absorption. When you do that, when you put terahertz will absorb in this, because you have some excitation, there is the arc carriers, they absorb the terahertz, that's what it happens. And this is because of the weak Coulombic interaction in the things and enhanced Auger processes here. But if you do some engineering in this phase space of this EK systems, where particularly if you have a material such a way that you can enhance this Coulombic screening, particularly in the 3D Dirac materials, because of the three-dimensional part, so they have much more density of states here, in the case varying with respect to this. So there is a kind of Coulombic screening that happens in this. It's a Pauli blocking that happens near to the band edge of it. So in this case, at particular temperature, we can suppress Auger recombination so that the electron hole, photon, like what you call interactions are, timescales are much smaller than the hole recombination. It means that they come down quickly to this state, and then they stay here for a while, and then they decay back. So this is what the things that gives terahertz gain or population inversion. There is a population inversion for some time, and then you can observe terahertz emission that happens between this band gap, because it's of the order of the similar 4 milli eV, which is the terahertz frequencies. So this is what happens in cadmium arsenide. And this is the transient ultrafast pump probe data that we have. So this data shows the terahertz, pump probe data with respect to temperature. You see that at some temperatures below that, nearly like 50 lower than, there is some noise level as well. You see that the conductivity, basically the terahertz photoinduced conductivity becomes negative. That's well observed in graphene and all, because of because actually you can engineer the scattering here. Like there is a more scattering, it means that it becomes like a metallic behavior, and then it shows negative photoconductivity in graphene. And here also we observe at some particular time scales. And this data shows that at particular temperature we have, and then change the fluence. At higher one, you can tune it. So there is both change that you can go from, this is basically a semi-metallic behavior, more scattering is there, and this is semiconducting behavior, less scattering, so that basically you can switch transient between this at picosecond time scales, okay? So this is what we used to, by exponential fitting with the time constant for the electron phonon interaction and electron hole interaction to derive. And this is where there's a direct measurement of terahertz transient. Like basically when you measure at this point, the terahertz pulse, it shows conductivity quite positive here in this part. But at this point, the conductivity, the photo-induced conductivity becomes negative. You see that it's below that. This is where the thing. So there is basically terahertz is kind of amplified. It means that there is a more terahertz coming because there is an increase in the conductivity of it. So, and we actually fitted this entire pump probe data using this one, and extracted the time relaxation for electron phonon and electron hole recombination. And this is what it shows. The ratio of electron phonon to electron hole interact, the dynamics that I discussed about. Here, if this ratio is less than 1, it means that the time is basically the Auger process are much faster. Okay, in this case, you have this condition of gain condition, but when it is basically electron hole becomes almost comparable and higher, there is the loss here in the sense that this is actually a no gain condition. So this we measured, and with temperature there is at this particular regime and with the noise level, so we have a very good gain at lower temperature, and this also is here. And then as you increase the pump fluence or temperature, the gain condition is kind of, lost. So this is what here is that the separation of Auger process is basically is the one of the things that engineers this population inversion. And here this data shows the similar terahertz conductivity. Like what we did was at room temperature, we excited the sample and then measured the terahertz conductivity, non-equilibrium terahertz conductivity, and then it shows that this is the red one is basically the imaginary part of conductivity and the black line is real part. You see that it's almost above in the it's positive conductivity, but at lower temperature when you go 30 Kelvin with the same pump fluence, if you are driving this, so you see that the conductivity, that this is actually a spectroscopic observation. It's a direct measurement of terahertz conductivity when you excite electrons to higher, I'm done this. So higher state. So then you see that at some frequency regime, which is higher than I think 0.6 here, so you see that the terahertz is basically negative conductivity. It means that you observe a gain in the sense here, and what we used to interpret this, we use because this, whatever the positive is basically a Drude behavior, which basically well explained using the intraband Drude-Smith models. Basically, it's no resonance and it's a frequency dependent one, and also we combined this with the interband process, which uses the absorption like basically a Lorentz type of model, and using that. So where this A is basically a gain coefficient, it means that the amplitude is higher. It means that higher the gain, the thing. So we kind of extracted this A, gain amplitude, and plotted here in these things. You can see that at 295 Kelvin, which is red points, there is no gain. You change the fluence, but here at 30 Kelvin, you can actually kind of look at the gain is basically you can tune the gain because there is basically a negative conductivity which is here, and this plot shows that there is a zero crossing of this conductivity plot, which depends on the temperature. So for example, lower temperature means it's actually at very low frequency here. As it goes to higher temperature, then the zero crossing moves to the higher frequency. It means that the interband, because of the higher frequency of the terahertz, which it actually kind of dominates this process. So you have a gain which disappears because you are directly exciting for using terahertz. So this is the results, and to conclude this, so we actually observed there is a semiconductor to semi-metal transition, both steady state as well as in the transient domain of it, and that is associated with this population inversion and non-equilibrium terahertz gain in this 3D Dirac semi-metal, and these are very important in terms of developing compact terahertz optoelectronics, which are actually kind of very, very rare because of this, the semiconductor behavior of terahertz is quite weak, so that finding the gain medium is quite challenging. So here, this is one of the examples that cadmium arsenate can be used as a gain medium in the terahertz at this particular frequency. So with this, I would like to acknowledge Professor Ranjan Singh, where we did some low temperature measurements in his lab there in NTU, and I was a PhD there, and now we conducted with the student, Shoban, who helped with the measurements, and Fashion Shu from Fudan for the sample he provided, and the fundings from IAC seed grant as well as STARS and SCRB, which, and this is my group. We have, and Abhishek is the one who actually involved in this work, and he performed some of this, measurements and analysis of these results. And with this, I'd like to thank you for your kind attention. Yeah,
Thank you very much. Questions?
Yes.
Meganga, Mike.
Yep. Thank you for your talk.
Thank
I have a question about your sample fabrication. So you showed you have like sapphire, cadmium telluride, and then cadmium arsenide. So what's the role of sapphire and cadmium telluride?
Basically, this is epitaxial growth. It needs the index matching from sapphire to cadmium arsenide. So the cadmium telluride actually gives us that like refractive index gradient, so that you grow a good epitaxial things. That's where there's a very thin layer of 20 nanometer of like 10 nanometer of cadmium telluride, and then it's for the epitaxial growth of it.
And then when you excite your...
You are excite, oh, you mean like?
When you excite, you only excite your cadmium arsenide?
Exactly. So the cadmium telluride is purely insulating. It doesn't really have, but cadmium arsenide is semi-metal. So that's whatever. We also looked at the data of the cadmium telluride. There is no pump probe signature. So it's all purely coming from the cadmium arsenide. I think I might have that probably.
Thanks, Manu, for the nice talk. I have just one question regarding the Auger process, and you mentioned in your experiment. So, what is the typical timescales of this process in your kind of systems?
Usually in semiconductors and all, because these are like multi-quasi-particle interaction at the thing. So usually in picosecond time scales.
Oh,
Yes.
Okay.
But here in this process, particularly in graphene and all, this is much more. This Artcurry culling is much faster. But the thing is that the recombination is also quite fast. So it's about the electron hole recombination to the Auger process, which is happening.
Are there cascaded process or anything?
Yeah, it's kind of cascaded process. Yeah, because one thing is that in graphene, particularly the phonons, which are there, this bit higher energy, so they don't really kind of contribute to this type of things. But in cadmium arsenide, the phonon is near to the terahertz frequency, so it means that it enhances the faster recombination of this Auger process, which is much faster in few hundred femtosecond. So that's the way it kind of gives you. Then you have the Coulomb screening, so that here the actual electron hole recombination in cadmium arsenide is of hundreds of picosecond. Nearly picosecond, but the Auger is much faster, so that you can observe this type of
Thanks.
Yeah.
If I read correctly, it looked like the DC conductivity was like order of magnitude smaller than the terahertz. So is there a simple reason?
Yes, I think because one thing is that here, that was also. So basically, what we are measuring in DC is look at that the of the what do you call EXX one particular, but in terahertz we are actually kind of measuring the entire bulk conductivity of it. So basically, it's a transmission measurements, which basically tells it about the entire aspect. Entire electrons which are basically contributing to the conductivity of it. Because here, if you look at, that's what I think. Actually, we noticed that. So in this particular one, here, right? In this case, right? This is 10 power 3 and 10 power 4. That's what you're saying. Because basically here is the IXS which are contributing to this particular one. But in this one, it's a bulk conductivity. What I mean is that the electrons which are actually kind of contributing to the other direction as well, and also this is basically is a transmission measurement of the entire bulk material. That's what. And particularly maybe it's also related to the topological signature of it, because usually the conductivity increases for higher frequencies. It becomes like a linear with respect to the things, because as you are actually kind of at higher frequencies, you are trying to also thermalize in the sense that the frequency is exciting, so that the conductivity is also increasing in that particular domain of it. That's what I believe. Maybe we can look at.
Can I ask? And using this method, can you also measure like Hall conductivity? Can you also measure Hall conductivity, for example, using this?
Basically, the Hall conductivity here, because usually this is AC conductivity, which is particularly the high frequency. We can measure with magnetic field as well, but the thing is that the magnetic field that is required is quite high in the sense, because to kind of influence this, there is a Landau type of interaction that's trying to ask.
No, I mean sigma xy instead of sigma xx.
Sigma xy. It's quite difficult, basically, because you are having a light which is polarized in one of the things, and we are only detecting that particular aspect of it. So you are saying that apply in one direction, the measure xy type of So it's basically we have to look at, but the data would be different in the sense that this is a higher frequency effects, and there are a lot different, the noise, thermal noise and all will coming up. So that's where the things would be in terms of,
Yeah, one more question,
I was wondering, in cadmium arsenide, do you have like directional effects? So if you change the polarization of your pump, does it matter, or you just always have the bulk response?
I think this has, we have done it with circular polarization. That changes basically. There is orbital effect, which is, but with X and Y, there is no anisotrope. Like it's particularly isotropic.
So you mean linear to left and right,
yes,
or also left and right?
Yes.
Also
that
left and right is also different.
As a different thing, because there is because this also is spintonic. It can also emit terahertz, as people have actually looked at. And this has a signature with circular polarization, where you actually can excite the orbital moment of this, and then to kind of have orbital spins which can contribute in terms of this. So there are some recent experiments showing that, yeah, you can change with different LCP and RCP states as well. Yeah.
No more question. Please thank the speaker one more time.
Thank you. Thanks.
So now we'll be having the poster session, and let's have it in 20 minutes. After that, we'll be having talk from Almon. After the talk from Abhishek Third.
Okay. How's everything? You came, or maybe I did.
I was looking for you.
Oh, I was back.
Lunch or
So how's everything now? Yeah, we can just talk about.
Things are going on.
Yeah. It's like entire week, right? Almost completely. No. Yes. Thank you.
Okay, let's start the session. So now we are having Alban. He'll be talking on cold atoms and nanophotonic waveguides. Yeah. So Alban, please go ahead.
Okay, so good morning, everyone. I also want to thank a lot the organizers, both local and on the French side. It's a pleasure to be here for the first time for me in India. Can you hear me well? Everybody from the back? Okay. I'm an associate professor at Sorbonne Université, and I work at LKB in Paris in the group led by Julien Laurent and myself. And I will be telling you about cold atom and nanophotonic waveguides. And I also want to thank a lot the previous speakers, especially Alexei and Fabien, who really will make my life easy and quick in explaining some of the concepts that everything is based on. So as requested, I pulled up my About Me slide. After studying in France, I spent quite a while in Germany, in Stuttgart, and I worked in the group led by Tilman Fau and Robert Löw. And I was looking at dynamics of excitation of Rydberg atoms in vapor cells for a while. Then I moved to MIT as a postdoc in the group of Vladan Vuletic, and I studied and realized laser cooling to quantum degeneracy. So first BEC with direct laser cooling. And since 2019, I joined Julien Laurent in the quantum networks team at LKB, and I've been doing quantum optics. I'll be talking about atoms and nanophotonic waveguides, but we also do quantum optics more generally speaking, with and without atoms. So geographically, this is Paris, and LKB you might not know. I like to pull this up as well because people think of maybe one site, but we're actually in 3 different locations in Paris. I think the Eiffel Tower is around here. Notre Dame is around here, so we're not too far away. So there's 3 different places. One is at Collège de France, where there's BECs with Jean Dalibard and Rydberg atoms, the Michel Brune and so on, and Clément Serrin and so on, the former group of Serge Haroche. And can also add, I guess, Alexei over there with very close ties to LKB. Second location is INS with a bunch of different groups. I won't go through all of it, but we will hear about cavity QED from Romain, who works together with Jakob Reichel. And finally, Jussieu, the formerly UPMC campus, where we have actually quite a lot of stuff going on from metrology, theory, optomechanics, and quite a big quantum optics activity. And so this is where I'm based together with Julien Leroy. So what do we do there? This quantum networks team, we're focusing on how do we get towards such a future quantum information technology, quantum information network, where you would have quantum nodes where you can store and process quantum states, and channels where this quantum information can be distributed. So there's two types of things you need here. First one, in the links you need light, and the second, in nodes you need to manipulate this light, and our medium of choice is atoms. So all of that is with the goal of going towards complex entangled networks where you can do a bunch of different interesting things. We have three different directions of research. First one, purely photonic. We call it the hybrid photonics lab. We work now towards complex quantum state engineering, photonic quantum state engineering. Among other things, towards heterogeneous networks, and by heterogeneous I mean with different encodings, continuous and discrete variables, for example. Second research direction is based on the long-standing activity in the group of a free space quantum memory based on electromagnetically induced transparency. And so in particular, we have a very efficient quantum memory platform. So this is the new version of it with a very long magneto-optical trap where we can store photonic quantum states for quite a while with very high efficiency. We've extended that activity into developing photon pair sources that are compatible with telecom networks and storing in this quantum memory. And all of this is, among other things, towards quantum repeaters, so how to distribute entanglement in a deployed network. And last but not least, what I'll be talking about today, which is waveguide and atoms, where we have two experiments, interfacing cold atoms and guided light in nanophotonic waveguides. And broadly speaking, this is with the goal of going towards deterministic operations. So this is what I'll be talking about today. So the goal there is really to move towards a bunch of atoms coupled to a pipeline for light. And to go towards an all-fibered light matter interface with atoms. And the idea there is really to combine nanophotonic, nanoscale waveguides and cold atom arrays, which are, in a way, fields that have been somehow disconnected because they deal with kind of different things. So this will be the focus, actually, of my two tutorials on these two platforms. The first one today will be a general introduction into waveguide QED with nanophotonic waveguides and cold atoms in particular, and some of the things people have done, and especially we've done in the in recent years. And the second will be on how to go a bit further with more complex waveguides, and in particular slow mode waveguides to try to increase the coupling. And this is a theme that you will see is quite common with what Alexei has been telling you. Okay, so the outline for today is waveguide QED, generally speaking, and nanofiber. So my poor man's sketch of what we have, what the idea is behind this is, so poor man compared to what Alexei did, is we want to go towards deterministic operations on optical photons. So we want to take an input state, photonic input state. We want to make it become something else and controlled by another photonic state. So this is kind of a gate, if you want, and we want it to be controlled by another photon, so we need a medium for that, and our medium of choice, as I said, is atoms. If we want to do this in any reasonable way and useful way, what we need is strong interaction, strong atom-photon coupling at this stage, so that we can get to something efficient and on demand, such that anything can be made scalable and can be implemented and useful further moving on towards these quantum information networks. So strong requirement is atom-photon coupling, and again, you will recall similar themes to what Alexei told you. It's not trivial to do, or at least it's hard to do if you just focus a beam on an atom. You get relatively limited interaction probability of this photon focused on the atom, and it's hard to scale because of diffraction of this beam you focus down. So this cavity QED, a very successful platform. You will hear about it from Romain. You also heard about it from Alexei, with many different platforms, from bulk cavities, nanofabricated ring cavities, nanophotonic crystal cavities as well, which are closely related to what I'll be telling you about. They're super powerful. You can do amazing stuff there. What is typically hard in these platforms, as Alexei told you, is to extract a photon that has been emitted into the cavity. So you can do clever tricks, like Alexei is doing, by combining it with a different ingredient, in particular Rydberg atoms. Also not super trivial. So this is super powerful, yet we're trying to go a slightly different way. Our approach is to have atoms coupled to one-dimensional propagating waveguides. And so the link here for now is really to the focus beam, where we have a confined beam along a long distance where we can have a bunch of atoms coupled to it. And so there the figure of merit is to compare the rate of decay of the atom into the waveguide and to compare it to the natural line rate, for example. And it's given by a couple of different factors. One is lambda squared. This comes from the scattering cross-section of the atom. The other one is A, which is the geometrical confinement factor of the field around this waveguide. And then there's the group index, of which I will not touch on today, but I will touch on more tomorrow. So waveguide QED, so I'll be describing it in terms of atoms coupled to nanophotonic waveguides in the evanescent field. But there's actually quite a zoology of different platforms in this direction, of emitters coupled to a waveguide. So there's ensemble of atoms coupled to nanofibers. I will be telling you quite a bit about it today. You can go further, and people have started to go further with engineered waveguides, in particular this alligator waveguides coupled to a few cold atoms, with the pioneering work of Jeff Kimball, with quite a few very important preliminary results in the direction of going towards strong coupling of single atoms to the propagating waveguide. But also some limitations in these efforts, with only a few atoms and not so much a stable trapping, really where the field is strong. So I'll tell you more about these type of efforts tomorrow. You can also do it differently. You can take such an engineer waveguide and put a different kind of emitter, for example, a quantum dot. And I'll highlight here quite specifically the work of the group of Peter Lodal in Copenhagen, where they have quantum dots coupled to these structured waveguides. So essentially this line here is a waveguide. And they can get really strong extraction efficiency of single photons, really high extraction efficiencies, and actually all the way up to photon-photon interactions with a single emitter. You can go in a really different regime, use superconducting qubits, and make sure that they are coupled to a transmission line, so an RF transmission line. There, you get actually really low emission rates of the superconducting qubits in free space. So basically, everything is going to be emitted into the waveguide, but it's also microwave photons, so you're not going to have them travel over long distances. But you can also do kind of fun things. You can be in a situation where you have an engineered atom, so a superconducting qubit, interacting twice with the same line. So this is a kind of a fun configuration, which is called giant atoms. You can also do some more exotic things and reversing the roles. There's a group in New York, I forgot the name of the PI, sorry for that, where you really reverse the roles. The waveguide now is, the waveguide is made of light, and the atoms are the emitters, so the atoms are propagating into these essentially dipole trap, and you're propagating matter waves instead of light waves. So I also want to highlight 3 very interesting reviews in this field of research, one of which by Li Biandu. So here I've actually showed you waveguide QED platforms where there's an actual physical waveguide, but you don't need an actual physical waveguide to do waveguide QED physics. You can essentially take what Alexei was telling you about Rydberg atoms and Rydberg blockade without the cavity, and because of the EIT physics that is in the background, you have strong coupling to a single mode, and you can really do waveguide QED physics with one-dimensional propagation without a physical waveguide in this system. And this is something that is pushed forward by Sebastian Hoferbert in Bonn, for example. Okay, so as I said, we are focusing on these type of platforms where there's atoms coupled to nanophotonic waveguides, and these atoms are coupled via the evanescent field. So how does it come about? Imagine a waveguide on really narrow optical fiber, I'll get back to that in a moment, which is sub-lambda in size. And imagine that this is glass. So there's an index contrast with vacuum, so you can guide a mode in it. But this mode at a wavelength lambda, if the waveguide is of size sub-lambda, will extend quite far out into vacuum, and a lot of energy will be in the evanescent field. So in our case, think of something like 50% of energy in the evanescent field. So what we want to do is to have the atoms interact with this evanescent field and interact with it in 2 slightly different but strongly related ways. First, on resonance for the photonic operations you have in mind, and maybe even state preparation. And second, for optical dipole trapping. So we also want to have optical dipole traps which are propagating here, which are operating from the evanescent field. And so this ensures that we can have common mode operation of these two effects, the trapping and then the photonic quantum operation you're trying to do. So how does it look in the lab if we try to couple atoms to nanofibers? So nanofibers are essentially optical fibers, which you can see here on the electronic microscope, which we will stretch under a hydrogen flame. I'll show you a little bit more if I have time at the end. All the way down from 125 microns to 400 nanometers. So 400 nanometers is much smaller than lambda. We're in the situation I described to you just before. And this is what you can see in our lab. We have, so this is the inside of a vacuum chamber, and this part here, which is glowing red, is the nano size part of this nanofiber. And it's glowing a little bit because we are shining a bit of light through it, and so there's light in the evanescent field, so every little defect will scatter a little bit. Still, they have really high transmission, more than 99% when we fabricate them. So we get this guided mode, but this picture here I'm showing to you is a little bit simplistic, or way too simplistic if you want to do things kind of more precisely. It's a guided mode to sub-lambda size, and so you get near-field features that you don't get when you usually focus a beam in the paraxial approximation. And in particular, what happens is that because of Maxwell-Gauss equation, so let's say you have this nanofiber here where you send linear polarization vertical, so it will be guided along here. But there's the evanescent field which is decaying outside. Usually, from Maxwell-Gauss equation, which is valid everywhere, you get this longitudinal polarization term which vanishes. But here, because we have strong variation over a size of roughly lambda, then we get a strong gradient of one of the polarization components, let's say Ex, X being vertical. And so necessarily from this, we have a longitudinal polarization component. So what you see here is that this longitudinal polarization component is going to be depending on the sign of the gradient of the transverse field, and it's also going to be depending on the propagation direction k. On top of that, you get a factor I here, and this means that actually the field above and below this nanofiber is quite strongly circularly polarized with a direction that depends on which side whether you're above or below. And if you propagate in the other way, because of this k factor, you actually invert this polarization. So what this means is that if you have an atom which is going to emit a circularly polarized light, a circularly polarized photon is going to be emitting this photon along one direction and one direction almost perfectly. So this is what's called chiral coupling, and it's quite important in what we do. It can be quite important, and it's also can be also useful in a theoretical context to have this because it simplifies how you think of the problem. So essentially, what this means is if you have a chain of atoms coupled here, what happens is only sequentially in one direction. So it simplifies how you can treat it theoretically. Second thing, which is a consequence of this, is that you get actually this only above and below the nanofiber, so along the axis of the linear polarization. And so what this means is that you get an azimuthal asymmetry of the mode. So this is a cut of the nanofiber. You get peaks of intensity above and below due to, in particular, this longitudinal polarization. And you break the cylindrical symmetry of the nanofiber just because of polarization. So how do we work with it with atoms? So this nanofiber is actually immersed in a magneto-optical trap. Yeah. Oops, my bad.
Yeah, in this picture, I can take this vertical axis like any x and y, right? Propagation is along z.
Propagation is along z. This vertical axis is given by the polarization you're injecting into the fiber.
Polarization I'm injecting into the fiber.
So it's if you inject linear polarization, it's actually a quasi-linear mode. Quasi-linear because actually what's the light that you have above and below is actually becoming circular, not in the direction you would expect because of this longitudinal component arising.
Yeah, I'm quite not understanding why above is plus sigma plus and below sigma minus. I mean, apparently there is no asymmetry in this.
There's an asymmetry between top and bottom?
Yeah.
Okay. That one is because the gradient has a different sign. The gradient of transverse electric field has a different sign. You're decaying here. The electric field is decaying above and below, but the gradient has a different sign.
Okay.
Right? Along this x-axis. And so this is what results into a different rotation direction of polarization.
Okay. Thanks.
Yeah. Can I ask another question?
Yeah, go ahead.
So you're mentioning this azimuthal asymmetry. Is there any way that you can experimentally play with that when you already have the fiber within the setup?
Yeah. So we do actually optimize the polarization, and we also use this specifically so we're looking at the light that is scattered, and the light that is scattered also carries these properties, and so we're able to, by minimizing the polarization on one axis or maximizing polarization contrast, to make sure that along the nanofiber we have linear polarization aligned the way we want. So in particular, we usually go in vertical direction in our experiment.
Thank you.
Electric field distribution change, or how does it change with your, let's say, radius of your waveguide?
how the electric field distribution changes as a function of radius of the nanofiber.
Yeah, so if you make it thinner or thicker,
Yeah.
but you still keep it sub-wavelength.
Yeah, I swept it on the carpet. So essentially, the smaller you make this core is really just a one single material at this stage. The thinner you make it, the more the field extends into the evanescent field. That's one thing. The more single mode you make it, and we operate in a single mode regime where there's really only this mode here. And we choose the radius of our nanofiber such that we maximize the amount of energy into the evanescent field while minimizing the extent it takes in the evanescent field. So we have the maximum intensity out here. So if we make it much thinner, it's still single mode, it still propagates, at least for a perfectly straight nanofiber, but the mode will extend more and more out in the evanescent field. So this decay constant will become much larger, and then the coupling is weaker. Okay?
Affect like simulated Brillouin scattering affect your experiments? As the fiber losses, the power losses that happen?
Yeah, so the power losses are really low. We get 99% transmission. On resonance, we're sending single photons, so I don't expect anything nonlinear to happen. For the trapping light, I'm not sure, and I'm not sure we would care either because it's far off resonance anyways. Okay, so how do we put single atoms around that? So we immerse this nanofiber into a magneto-optical trap, and we have to make a dipole trap with the evanescent field, like I was telling you. And so the recipe was put forward quite a while ago. First implemented in Berlin, and used in many groups. And this list is actually incomplete. It's to use a two-color evanescent field dipole trap to create chains of atoms above and below the nanofiber. So how do we get to that? First of all, we need radial trapping, so to trap the atoms in the radial direction. And here we use a combination of wavelengths. We use a red detuned light that will attract the atoms toward the surface, combined with a blue detuned light that will repel them from the surface. And because they have different wavelengths, they have different evanescent decay constants. And so when you combine it, you get a stable trapping potential at a few hundred nanometers from the surface. You actually need to combine it with Casimir-Polder forces, so thanks also Athanasios for introducing that. Here, this is really negligible at 100 nanometers, 200 nanometers away. So we can trap atoms radially. We trap them azimuthally in two chains of atoms above and below from the asymmetry of the field I was telling you just before. And then we make it a chain by having counterpropagation of in particular, for us, the red detuned beam. We also counterpropagate the blue detuned beam for a bit of a technical reason, and also because of the circular polarized light. That's in order to cancel vector shifts of light. So we have a couple of configurations for us in the lab. The first one is 685 for the blue and 935 for the red. This gives us a magic trap where the transition frequency of the atom is not shifted compared to the resonance. And we've also used 852 nanometers for cesium atoms. We use cesium atoms. And I will get back to that in the following.
I have one question.
Yeah.
About the bending of this fiber, effect of the trapping of light. Can you bend the fiber?
It's straight.
Yeah, I see.
Yeah, there's a little bit of bending here, but in practice, it's straight. That probably was an older picture on the experiment. In practice, we stretch it, and it's fully straight.
No, because you mentioned about this giant emitter kind of.
Ah, okay. That's an idea. I'm not sure I'm going to try that first. maybe we would use nanofabricated waveguides for that. Yeah.
How uniform is the drawn fiber? I mean, is there a gradient of
No, it's actually pretty good. I can show you a picture towards the end. We can make it really uniform over 10 to 15 millimeters. It's quite a bit of work to make that nicely uniform, but we can do it. Yeah.
How much power can you send without burning the fiber?
So milliwatts, no problem. Depending on wavelength, up to 10 milliwatts, up to a bit more. So the bluer the wavelength, the more critical it is. So we can see huge differences between these two wavelengths, for example, in how much power you can send. And it's not quite clear to me why. Okay, just to flash a few recent or not so recent results on these platforms, and this is really not a complete list, including some of the things we've done. We've done an EIT quantum memory, which I won't tell you too much about. You've heard the term EIT quantum memory from Alex Hay a bit. I will mention it a little bit towards the end, but I'm happy to talk about it further on if you want. We've looked at how to make collective single excitations in this system, and I will tell you a bit just after. And there's also a lot of work, for example, in Berlin on things like super and subradiance. So one nice result for us was a few years ago when we were able to create a single excitation of this ensemble of atoms. So with the so-called DLCZ protocol, if you shine in light from this direction, from time to time you're going to have one of the atoms which will emit a photon inside the nanofiber. If we detect that, this projects the ensemble of atoms into a single excitation state, collective. You don't know which atom has emitted the photon. And you can recover that as a very good single photon emitted into the nanofiber. So this was a nice first realization of quantumness, let's say, in this type of system. What I want to tell you more about today is our efforts towards atomic Bragg mirror, and we've had a couple of results here. So there, the idea is we have this chain of atoms coupled, trapped around the nanofiber, and we make sure that the distance between two neighboring sites is very close to lambda over 2, where lambda is the resonant wavelength of the atom. So then what happens is that if you send in light, this En, each atom is going to be a little bit polarized by this light and emit a bit of light both in the backwards and the forward direction, depending on chirality, as I was mentioning. And because you have this nearly commensurate trap, almost lambda over 2, what happens is that you get constructive interference of all the light scattered backwards by all the atoms. So essentially, the light comes in, will be reflected a little bit by this atom, and it will also be reflected by this one after acquiring a phase that is coming from the propagation over multiples of lambda over 2. And what happens is that we can get really strong reflection from about 2,000 atoms. Here we can get almost 80% or 70% of reflection with 2,000 atoms in this system. So here really each atom is playing the role of a dielectric transition into in a dielectric stack that gives you a classical Bragg mirror. So what you can see here, two things is that depending on polarization, we get slightly different behavior. This is the chirality I was mentioning. And we can simulate it quite well using what's called matrix transfer formalism, where we look at the reflection coefficient of each atom, and then we also take into account the propagation phase acquired. And if you multiply the n matrices from n times doing this, then you end up with this, which matches really well. These reflection and transmission coefficients, they essentially arise from or they are closely related to the coherences in the optical Bloch equations. So, yes, yeah. This is really weak. I mean, it's classical light, but single photon level or lower. Yeah, good point. Very good, very important point. So It's actually in these type of platform, nanofibers, it's percent level. So it's a percent level. The beta factor, which is close to the Purcell factor, is roughly 1%. So that's why we need many atoms here. It's also why we're trying to move further with what I will tell you tomorrow. So what you might see is that this reflection happens a little bit off resonance, and this is because we are trying to counteract the fact that we cannot trap exactly at lambda over 2. So essentially what we're using there is the fact that from one atom to the next, light will be transmitted, reflected, and then transmitted again. And so we're using this transmission phase acquired when you're off resonant to counteract this delta lambda small mismatch from the Bragg condition. So that's what I was trying to tell you here. And there's a few other people who have done this Bragg reflection without a nanofiber, but with a lattice trapping cold atoms. So this was, for example, William Guérin when he was in Tübingen. He's trying to do it again now in Nice. Okay, I'm running out of time, but it's good. So these results we had in 2016, or quite a while ago. What we've done recently is we've tried to extend it to control this mirror dynamically with light. And the tool we use is EIT, electromagnetically induced transparency. You've heard about it quite a bit, so I don't have to tell you too much. Essentially, when you go from a 2-level system to a 3-level system with a control field, you can make the atoms transparent to the probe field here. So we propagate all of that, both of these inside the nanofiber, and we go from this situation in transmission in red and reflection in blue without control field to when we had the control field on. We can see, for example, in the red, we see the opening of a transparency window, and correspondingly, there's a dip in the reflection on the blue curve. So if we study this as a function of here the energy of the control beam pulse, we can go from one behavior, so reflective, to transmittive again. And so this is what we call a photon router. We can make a truth table which looks relatively good with fairly good contrast. And so this router actually has fairly low control power and decent extinction ratio, which is comparable to kind of integrated technologies going in that direction. Yeah. Oh, yeah, thanks. Okay. So this we published last year. And we also tried to go a bit further towards stronger nonlinearities. By nonlinearity, I mean going lower in the amount of power we need to switch the behavior of our system. And here, if you actually add a 4th level to the game, this is a trick that is already kind of well known in the community, you can now control from being transmittive to being reflective again. And you need about an order of magnitude fewer power or fewer photons in the switch beam than you would need in the control beam. And so we can measure this type of transition curves I was showing you. And we need as low as 30 photons to switch from transmittive to absorptive. We need a little bit more to recover the reflective state. We can also look at the spectrum. Yeah. Yeah, and it's a type of cross-Kerr nonlinearity because of this omega s. Yeah, because of the omega s is causing a cross-Kerr nonlinearity between.
Like a 3-level system with a like a coupling beam or control beam, you can have cross-Kerr nonlinearity, right?
Yes.
System. No, one of the original experiments on those.
Okay. So you can have Kerr, but can you have cross-Kerr?
The cross-Kerr means like you are controlling by another coupling beam. That's the cross. Like you have a probe and you have a control, and you are controlling by the control beam the nonlinearity of the probe beam.
So you can do Kerr nonlinearity with EIT, but cross-Kerr I'm not quite sure. We can discuss afterwards. So right, so here we can get down to about 30 photons, and this is kind of the limit we can push to with this nanofiber because of the 1% coupling I was mentioning just before. Okay, I'll switch this. And I want to highlight that this was actually the work of Jérémy Berroir in his PhD thesis, and Tridib Ray, which is, I believe, an alum from here. Okay, I'll now flash quite a few things briefly. So we've also looked at whether we can use these chains of atoms in Bragg condition to make, to go towards cavity QED. There was early work by Derek Chung and Valerio Scarani, for example, looking at a single atom in a atomic Bragg mirror cavity. And we've had some theory collaboration together with Dima Kuprianov in St. Petersburg, looking at what happens if we now put a collective excitation in between two Bragg mirrors. And there's a bunch of different regimes you can look at, in particular making this cavity quite long and starting to explore non-Markovian dynamics. So just a few words on recent developments. What happens is that sometimes the nanofiber can break, and here this bright spot here is just the light scattered out by the broken nanofiber. This happens in our case not because the fiber died, but because we ran out of cesium atoms, so we had to open it, and after 7 years, we ran out of cesium atoms, we had to open it, and the fiber didn't survive the whole operation. So we had to actually do it again 7 years later to fabricate these nanofibers. So this is what they look. This is how we. This is the narrow part we were trying to create, and it's really done by brushing a hydrogen flame across it and really doing it quite a few times to make sure that it's a reproducible process, and we can make this 400 nanometer nanofiber over here 15 millimeters. So it worked after quite a few months, and I want to highlight the work and the effort by David Lee and Ming-Shin Dong there. And you can really see here over 15 millimeter, it's faint, but you can quite see it, the scattering that is really constant over 15 millimeters. Okay, what's next? We actually wanted to go towards EIT quantum memory in fiber, and we got some preliminary results on par with what was in the literature in this platform. Here I'm showing you the slow light effect from EIT in this system. But we were kind of limited for a bunch of technical reasons, and we thought, can we, so we want to do EIT memory, we also want to add Bragg to that, and I can tell you a bit more if you want later on. We've also looked at whether we can improve our signal, or improve our coupling with atoms by some cavity enhancement, some ring cavity, following initial work by the group of Arno Rauschenbeutel, for example, and in Shanxi as well, where if you use an adjustable fiber beam splitter, you can make a ring cavity, and we were able to have some preliminary results on collective vacuum Rabi splitting, showing that we can have atoms coupled in there. So we'll see where this brings us. And these were the final results of David Lee's PhD. What is next otherwise? Well, moving to a different type of waveguide. On a separate experiment, we do keep the nanofiber. We want to move to keep working with these collective effects, but we also want to go towards stronger coupling with engineered nanophotonic waveguides coupling to one or more atoms, and this is what I will be telling you tomorrow. Pretty much on time. So coming to the end, I want to highlight the work I told you about so I mentioned Tridib and Jeremy, also Ming-Shin and David, who took over. Also Julien, who's leading these efforts with me, and the whole really good team. I'll mention the collaborators tomorrow because they were really relevant there. And I want to thank you for your attention.
Thank you very much. Questions? Any questions?
Thanks. So when you talked about the single excitation, collective excitation creation by measuring the photon emitted, does the photon emission rate or the loss rate from the cavity have to be much stronger than the atom-photon coupling for that to work? Or
does the photon emission rate?
Yeah. So whenever a photon gets emitted, I mean, so I suppose there's some coupling between the atoms and photons, which is like an exchange sort of interaction.
Not so much. So what happens is that you're exciting off resonantly, and from time to time the atoms will scatter randomly.
Okay.
And from time to time, they will also scatter inside the nanofiber. If we put a detector there and detect a single photon, we know we have a collective excitation inside the ensemble of atoms coupled evanescently to the nanofiber.
Okay, so whenever it's emitted in the nanofiber, you sort of sure to detect that.
We detect that, we herald essentially the creation of a collective excitation inside the ensemble of atoms, and that excitation can be read out with essentially the same pulse we use to excite.
Is it possible to continue this? If I detect one more photon, then I create two collective excitations instead of one? Is there something preventing it?
I guess you can. It's also a bit tricky because what you create is a two-mode squeeze state. So in order to make a single collective excitation, we need to make sure that we're in the low excitation regime, so we only detect the 0 and 1 excitation from the two-mode squeeze state. So you can go further. I believe the fidelities might go down as you go further.
I had just one follow-up, which is that you talked about creating this trapping potential using this combination of blue detuned and red detuned beams. Does that allow you to control the relative distance from the, and
Yes.
that sort of controls, so how much control do you have in terms of the coupling strength between the atom and light, for example? Using that, is it possible to?
So something like 100 of nanometer positioning is you can do, and it's an exponential decay. So we can go down to, I don't know, in this setting maybe 150 nanometers, but typically we stay at 200 to keep a good matching between the two optical powers, red and blue.
Thanks.
Okay.
Can I?
Sadiq, yeah.
Yeah. So a follow-up on that question. So let's assume that just do a Gedanken. You arrange atoms in kind of double lattice, okay, and you fly a photon in between, no fiber, nothing. You just arrange atoms and let the potentials do the talking. The thing is, how much does the fiber, okay, change the atom-photon interaction versus, and what are the scattering properties you would expect to see for such a system? Because while you are doing this excitation, collective excitation, there is more to, I mean, the entire system has kind of, the entire scattering process has changed dramatically.
Yeah. So so two things there that make it stay in a simple setting. The first one is the wavelength separation between atoms is not much shorter than λ/2. So we don't see dipole-dipole coupling between the atoms. The second is the coupling of the atom to the waveguide is on the percent level. And this really tells you that the scattering properties of the atom are not strongly modified.
Sir.
Okay.
Mike, we have many more questions.
Maybe you already covered it. So there are also these atom surface forces when the atom is very close, like Casimir-Polder, or with the curves. So do you have corrections due to those?
To use this?
Or
so it has been used. Very recently, Arno Rauschenbeutel has made a trap using only blue detuned light and Casimir-Polder attraction. It works for several atoms. The trap is usually a bit, the trap minimum is usually further away than what we can do with a two-color trap.
Okay.
There's one in the back.
Yeah. Can I ask? Okay, yeah. So I was asking that why is it called photon router?
Why is it called?
Photon router.
Photon router. Okay. We didn't want to call it a switch because it's not just looking at what comes out. So you can call it a two-port switch, going one way or the other, or router if you want. It's called in literature either a router or two-port switch.
No, that's like how do you like set the directionality, like whether it comes out on one way or other way?
So this is really turning on or off the Bragg reflection.
Okay.
So if the atoms do see the incoming light, so it's in the 2-level or 4-level scheme, essentially the atom will scatter light. You get this Bragg interference effect that reflects efficiently. And if you're in an EIT regime, the atoms are essentially transparent, and light is transmitted.
Okay. Okay.
So I'm just curious. So talking about your atomic Bragg mirror part, I'm just curious that in solid state platform, is something like this has been designed where you have like a sub wavelength waveguide and you have ions or atoms doped in that solid around that waveguide, and you see similar kind of features.
It has been on, or
No, I'm just curious, asking if you know or if it's possible or not.
I'm not aware of it.
Okay.
One thing we gain for free here with atoms is that they're all the same. So we can put many of them, they're all the same. So they all have their resonances at the same frequency.
Okay, one from back, back from back.
Yes, thank you. I think I may have missed this point. But how exactly do you maintain the separation of lambda by 2 between the atoms?
Okay. So so we create this evanescent dipole trap by a standing wave.
Okay.
And depending on the wavelength we choose, we can be in the Bragg condition, so very close to resonance at lambda. Lambda here for us is with cesium atoms is 852. So we go a few hundred terahertz away.
Okay, let's have one more question then during lunch session. Okay, done. So yeah, so then we can go ahead with the next talk. Okay, okay.
No,
okay,
in
please.
your that Coscar setup, is it also possible to measure KR by switching off your phi omega of S?
By switching off omega S, so do you mean to dynamically switch?
No, just switching off. Like if you have like, again, as you are saying, like you need 3 level first and then phi omega of S is creating the cos KR, right?
Yes.
Now let's take I switch off omega S and I measure the KR nonlinearity of this medium.
Okay. So just in this setting, you mean?
Yes. Because nonlinearity like a phase shift, right? You will measure some phase shift.
So we're not so much looking at phase here, just more at the coherence on this transition going down.
By the way, sorry, how you quantify cos KR?
Let's discuss afterwards.
We can go for next talk. Yeah. So he has, during the lunch time, please ask the question. Okay. So now we have Professor Abhishek Thar from ICTS, in International Center for Theoretical Studies. So this campus is located 20 kilometers away from here. So it's a very nice campus from crowded part of Bangalore. It's a bit outer skate of Bangalore. So, okay.
Yeah, so I would like to thank Sanjukta and all the other organizers for inviting me to this very nice meeting. Okay, so yeah, so I'm from this International Center for Theoretical Sciences, ICTS in short, and it's a center of TIFR, which is Tata Institute of Fundamental Research. The main center is in Bombay, and there are various branches, one of which is ICTS. So I just want to point out that, okay, so it's like he said, it's 20 kilometers from here, but it takes It takes about an hour, and it's a purely theoretical institute, so there are no labs, so I can't invite in people to see our labs. So I am really, it's nice that I can hear a lot of about experiments and in this meeting. So I want to point out that at ICTS, other than research, we also organize a lot of conferences all through the year. And anyone can propose a meeting there, and there's very good support and so on. So I would encourage you to look at our website, and you can find a lot of information. Okay, so this is work done with upon Dinda and Archak Purkasta, who are at IIT Hyderabad, and Tan and Hisao, who are at Yukawa Institute in Kyoto. Okay, and I thought this work would be kind of closest to the interests of this meeting. So I am actually a theoretical physicist. I work on equilibrium statistical physics, but I'm interested in open quantum systems and hydrodynamics and so on. And this is one of the recent things that it's sort of still incomplete work, and I really look forward to inputs from people here. Okay, so just to make, sorry. Okay, so yeah. Okay, so just to make clear what I'm going to talk about, I just want to mention this setup, which I think at least a lot of people know about. It's a very famous experiment, and in fact, Alexei in his first lecture briefly mentioned this. So this is an experiment where there's a cavity, and then you send a series of atoms across this cavity. Okay, so each of these atoms is prepared in some. You can think of it as a two-level system, and it's prepared in some it's like a fixed initial state, and then it interacts with the the cavity mode, and then after it comes out, it's you make a measurement of the state of the atom. Okay, and these measurements are done in some random measurement axis. And okay, so then you have a series of atoms, and you look at the outcome, and then from your measurements, you can you try to infer what is the state of the cavity. Okay, so basically, one of the what was most interesting about this experiment is that what you find is that after you send a lot of atoms, the cavity actually collapses to a fixed state. And if you start from a superposition of cavity states like this, then eventually in a given experimental run, it will collapse to some state with probability, which is exactly the Born rule. Okay, so it's like you kind of uncover the Born rule. Okay, so this experiment was done in 2007, and there's a very nice theoretical description by Michel Bauer and Denis Bernard in this 2011. Okay, so our setup is kind of very similar, so that's why I just wanted to start with this setup. Okay, so what we do is we have a cavity again, and there's a single photon mode, and then we send again atoms sequentially, but these are not. So we alternately send up spins and down spins. Okay, and these spins interact with the cavity over some time tau. And the up spins interact and the down spins interact for different periods of time. Okay, so and then they come out, and then they're detected. So you make a fixed measurement of whether it's up or down. Okay, so this is what I've said. You send atoms in states G and E sequentially, and measure their state every time. Okay, and for us, I mean the state, if the atom is in G, it interacts for some time tau G, and then you make a measurement in this basis. And if it's in state E, it interacts for some time tau E, and then you make a measurement. Okay, and then you repeat this process. Okay, So the interaction between the atom and the cavity is what is given by this Jaynes-Cummings type. So this is the atom energy, and this is the cavity energy. So there's a linear part, but you can also include some nonlinear part. And then there's this cavity atom interaction. Okay, so just note that this chi indicates the nonlinearity of the cavity. Okay, so now what we want to know is basically like after you keep sending these atoms, how does the state of the, so every time you make a measurement, the cavity, depending on the outcome of the measurement, the cavity will collapse into some state. So the cavity is doing some random walk in whatever space, and we want to know how it's evolving with time. This one is some function of A dagger, yeah, right, yeah. Okay, so now this system is basically you can describe it by what's known as a cross operator dynamics. Okay, so we send a sequence of, let's say, 2k atoms. So like you send a upspin and a downspin, that's like one step, okay. And so you send 2k atoms, and that takes some time tau, t, and after every measurement, the atom and cavity are in kind of a product state, right? And then the interaction causes the atom and the state and the cavity to get entangled into some through this unitary evolution. And okay, and then when you measure, there are two outcomes, and this causes the cavity to collapse to two possible states. And if you send two atoms, then you can have four possible outcomes, okay, which occur with different probabilities. Okay, so basically you have some Markov process which is described by something called cross operators. Okay, so I'll just describe the cross operator dynamics. So if so let's say the density matrix of the cavity at some time is rho t, then then it evolves through this unitary operator, and then the measurement can have four outcomes which are described by this operator case. Okay, and so every step of this model, of the dynamics can basically be written by using this cross operators. And so, so this is the evolution of the density matrix. Okay, so there are four possible outcomes, and there are four operators which I call K0, K1, K2, K3, and they satisfy this sum rule. Okay, so what do these four outcomes mean? So the K0 basically corresponds to, if you send up spin, it remains up. If you send it down spin, it remains up. So there's no photon detection or injection, and the photon number is unchanged basically. And K1, you detect a photon, and K2 corresponds to you inject a photon, and n goes from n to n plus 1. And K3 corresponds to, again, both you detect and inject a photon, so total net photon number is unchanged. Okay, so now you can talk of either the dynamics of the density matrix, but you can also talk of like a stochastic trajectory of the density matrix. And in this case, basically what you can say is that depending on the outcome of these four possible events, each of which happens with some probability, the post-measurement state is given by this. Okay, so you can define the stochastic trajectory also. Okay, so now, so first thing I want to point out is quite often what one studied is a limiting case where you consider the continuous time limit of this dynamics. Okay, so let me tell you what one expects from the continuous time dynamics. So this is given by what is known as Lindblad. So in this case, you imagine that these times of interactions, you let them become very small, and at the same time, the interaction between the qubit and the atom should become large in such a way that this ratio is kind of finite. In this limit, the equation for the density matrix is given by this Lindblad equation, and you can either have this photon loss or photon gain term. okay, which have different strengths, let's say. And okay, so now, I mean, in this, so you have a density matrix, and but it turns out that the diagonal elements of the density matrix have independent dynamics. So you can just write the dynamics for just the diagonal elements. And so if you look at the dynamics, so that just tells you what is the probability that there are n photons in the cavity. So that actually is basically follows a random walk. Okay. So from this, if you just write the equations for this diagonal elements, then it's a random walk on this positive line, and the probability of the photons increasing by n to n plus 1 is proportional to the rate of this process is given by this, while the process of loss of photon is given by this. Yeah.
The fact that it becomes the Lindblad equation comes from the fact that you had many Q's in the previous slide. If you had only one Q.
Sorry, what is Q?
In your previous slide, there.
Because
this is a closed, I mean, you have a unitary dynamics in there.
No, it's because you're also doing measurements, so it's not unitary, right?
Okay, so
yeah.
Doing
right, yeah. Okay, so okay, so now it's a random walk, and what you can show is that I mean, it's clear that if the rate of gaining is larger than this loss, then of course it's a biased random walk which will just go to infinity, right? So the photon number will just keep increasing. On the other hand, if this rate is larger than gamma e, then you'll reach a steady state, and you can find what the steady state is. Okay, so you'll have some distribution of photons in the cavity. Okay, so this is if you go to the continuous limit. Okay, but now supposing you look at the case where I mean, these are small and so on, but you don't really go to make them infinite. They're just small and finite. Okay, so in that case, we just have to do the discrete random walk, and so we have to do the exact cross dynamics. And if you so one can just work it out, and the precise dynamics is just this. Okay, so it's a discrete random walk with some rates. So let's say this is the 1D lattice, and from each photon number, I mean, so this it can increase with probability beta n, it can decrease with probability alpha n, and it can remain unchanged with probability 1 minus this. Okay, and so of course you don't have anything on this side. So this is the random walk. Okay, so now and these rates are known precisely depending on the coupling of the Hamiltonian and everything. Okay, and now let's say we are looking at parameters which correspond to in the Lindbladian limit to precisely this, where you have a steady state. Okay, and we ask, I mean, what is the steady state in this system? Okay, so now I mean, I don't know what people would guess, but the big surprise is that this system does not have a steady state. Okay, so if you do the exact discrete dynamics, this I mean, this model does not have a steady state. Okay, so so the transition rates are now more complicated and generally lead to dynamics that is qualitatively actually very different from that predicted by Lindblad. So in particular, there is no steady state even when the rates are chosen such that the Lindblad has a steady state. Okay, so now how do we understand this? I mean, the simplest way to look at this is, I mean, so there's a random walk with some rates. And then I can imagine that I can interpret it in terms of potential landscape. So there's a lattice and there's a potential Vn at every site, and this the ratio of these sites just depends on. I think it will just come back. I think it just comes back after some time. Yeah. Okay, so yeah, so this ratio just depends on the transition rates, corresponding transition rates. So this is basically kind of using the idea of local detailed balance to define a potential. Okay, so we know all these rates, and so this using this one can basically define a potential at every site, right? Starting from 0, you can just iterate it and you can get the potential. So all these rates are exactly known just for any set of parameters of the model. Okay, so now once you have a potential and you have a random walk on that potential, it can have a steady state only if, this kind of is convergent, right? Because that's the steady state measure. It's like the partition function. However, what we find is that the potential is typically unbounded from below, and thus there is no steady state. Okay, so I'm roughly speaking, you can see that it looks like a sum of kind of random numbers, so and which does not have to be bounded. Okay, so now like we measured various things. Okay, so these are the kind of observables we look at. So we start from some initial state, and then we okay. So first, what I show here is okay. So this case corresponds to the linear case where there is no nonlinearity. So chi is 0. So it's the potential is completely just a dagger A. And I plot the potential, so it has this feature. Okay, so what one sees is that it keeps going kind of oscillating with the bigger and bigger minimas and maximas, and so it's clear that if you have a random walk in such a potential, there cannot be a steady state, right? So we then looked at various things like how long does it take if you start from the origin. How long does it take for the photon number to get populated to some level? So that's the mean first passage time for the photon number to go from some value to some value. How much time is that?
You have 7 minutes.
Okay, great. Okay, that's perfect. That's more than I need. Okay. So okay. So here what we find is that if you are going from 0 to till this point, it's kind of fast. But after that, if you want to go beyond this point, then it takes a very long time. Okay, so because you have to overcome this barrier. So it's basically like a random walk evolving in this kind of deep potential wells. So the mean time to go escape from these potentials becomes extremely large. Okay, and then one other thing you can look at is just look at the mean photon number as a function of time. So if you start from again a very low number of photons, and then what we find is, so you can ask this at an average level but also at a trajectory level. So at a trajectory level, you see that it stays kind of small for it some time, and then there's a sudden increase, which basically means it crosses from this well to the next well, right? And then the photon number becomes very large. Okay. So the mean follows this curve, but at a trajectory level, you get these various plots. Okay, now if you put in switch on nonlinearity, then things are very different. That the potential landscape looks completely different. I mean, this is one example of like with some parameters you get a potential like this, and now the mean time it has kind of this feature. I mean, it has more structure than this linear case. It keeps getting stuck in this local minimas, and then it evolves again. Okay, so basically this just shows that you have a lot of local minimas, and similarly the mean photon number now has this kind of a structure. Okay, so I mean in the nonlinear case actually things can depend quite drastically on how you choose parameters and so on. I just show another example, like this is for the potential which for some other set of parameters, and you can again see the structure that there are this large number of local minimas where the system keeps getting trapped, and then there's some mean residence time, and it then goes to the next trap and so on. Okay, so this is the sense in which the dynamics is glassy. The other thing we measured is this mean photon number fluctuations, which you can do at different times. So it's a function, two-time quantity. Okay, I think, yeah.
Can we try to understand where this nonlinearity coming from in the cavity? This is inside the cavity, right?
That I would imagine that you can cook up cavities with nonlinearity, right? I mean.
No, I'm asking like in your model.
Yeah, in the model we just take it, right? I mean, it's just given.
Given, but
yeah.
It's like the experiment of that which you are showing, atoms moving through it.
The first experiment, there was no nonlinearity.
Okay,
I mean,
so
right,
you now
yeah, and that was just I mean, illustration. Yeah. This one I'm just imagining that it's possible. I think that it is indeed possible to create nonlinear.
And the other question you said, like it generates some kind of random number when you were explaining about that potential. So that random numbers are coming from what can I?
No, okay. So basically, okay. So I mean, so you are summing up these quantities, right? Log of this. Okay. Now, if you look at what are these rates, hopping rates, right? So they have these expressions. Okay. So they are like kind of complicated, right? And if you just plot them, I mean, okay. I mean, we have some arguments like for large n, you can do some asymptotics and all. But typically, if you just plot them, you can see that they are kind of random. Okay, these alphas can become like, okay, so alpha n is this mod square, but they can become extremely small or they can become extremely large and so on. So
does it depends on like this photons emission from the atoms? Because A and B is what, again I forgot, capital A, B.
A and B, okay, so it's, see, basically all this comes from computing this object. So there's this photon cavity interaction Hamiltonian. You start from some uncoupled state, then you evolve it, and then you find what's the probability of these 4 outcomes, right? So this you can just compute exactly. I mean, so this is just, it just comes from the computation.
A, B are defined by this quantity?
Yeah, yeah. From this, if you do this calculation, you'll just get the explicit expressions for A, B and all, which is what I
So the
write.
dynamics create these random numbers you are saying. The dynamics in the cavity.
Okay, in principle they are not random, right? They are completely deterministic. But I'm saying in practice, if you just plot them, you'll find that this they are effectively random.
The dynamics means I'm saying like random emission of the atoms inside the cavity creates these things.
Yeah, so the atom, I mean, goes from level n to n plus 1 or n to n minus 1. The probability of going this way or that way, that's okay. So there's a random, okay, so that's a random event, but this probability itself is a random number. I mean, it's chosen from, it's, in this case, it's not from a distribution, but I'm saying it's different on every, like for every, it depends on n. So it's, I mean, there's a model called random walk in random environments. It's similar to that. I mean, so it's a fixed environment, but then the probabilities are all random. Yeah, so I'm just saying if you just compute these ratios, and then this log of this ratio, right? This you'll find it's, I mean, it's randomly +1 or -1. Not +1, -1, sorry. Positive, negative is a sum of positive, negative numbers. So in that sense, it's a sum of random numbers. Okay, so yeah, so this is other quantity we look at, like it's the mean square deviation of the random walk in some sense. And here again you see features of classic physics where it like, I mean, it goes from, it stays in one minima, then it goes to another minima, and then goes to another minima and so on. And there's also some dependence on this this waiting time. Okay, so that's another feature of glass. Okay, so yeah, I think so. These are the main results. I mean, so I think I'll just summarize. So basically, we are looking at dynamics of a cavity that is probed by a series of two-level atoms in alternating states. And so we have results from the. What we find is that results from the true discrete cross dynamics are completely different from the corresponding continuous time Lindblad limit. And for the linear potential, the effective potential, I mean, seems to have. So I showed you this increasing, like the oscillating but increasing amplitude profile, and the profile actually goes as square root of n, and which we can argue. And for the nonlinear potentials, then the effective potential seems kind of like what is generated by random walk. And so this I already discussed, and so this is roughly like a sum of random numbers, and this is so if it was exactly sum of random numbers, then this is known as the Sinai walk, which is known to be a model with which has features like I mean glass. I mean, like it's it has extremely slow relaxation, and yeah, it shows many properties like glasses. Okay, so that's why we say that this is like glassy dynamics. Okay, so I mean, so I would really be interested if people have ideas on like if this is sort of there are some interesting experimental consequences of this. Thanks.
Okay, thanks a lot, sir. Any questions?
Just wanted to see for other glass kind of situation. So you were showing about this tau, the slow dynamics
Right,
of
yeah.
the order of 10 to the power. I saw in one graph 10 to the power 45.
Yeah. So right now those times are crazy, and we are playing around with parameters and trying to see if you can make them more reasonable. Yeah. Right now, of course,
Because in experiment, if I say that tau is typical relaxation time, which is let's say of the order of 100 nanosecond, then 10 to the power 7 and so on.
Yeah, no, that would be impossible. But it just depends on like how big this this minimas are. I mean, one can kind of play around with parameters to make them less
and in other kind of
more
systems, how do people detect this transition into glassy dynamics? Means they detect that slow dynamics.
Okay, like I know, for example, if you look at let's say molecular glasses, there you look at like tagged particle diffusion, right, which is very similar to this quantity.
Okay.
And you can see that it it has this kind of similar feature.
And those T over taus are similar or
No,
less?
there of course it's a completely different time scales. Are like it's first of all it's a many body system, and time scales, everything is very different. I mean, but of course in real glasses also sometimes time scales are so large that it's difficult to access in experiments. That's still true. Yeah.
Hi, you have two terms in the nonlinearity. One, I think minus, another was plus b.
Yeah.
So do I really need to keep the b part a cubic term or?
Okay, I mean, okay, this is something I don't know very well, but like what my collaborator tells me that is this, I mean, that is something which it seems like in some experimental setup can be realized very easily. And yeah, but you don't, one can put any nonlinearity, of course. We haven't explored like what the potential landscape would look like for different nonlinearities. I showed what, I mean, the ones which we did.
First, if I keep the first term, it's like curve nonlinearity.
Right, yeah.
Thanks, yeah.
Okay, you said there is a no steady state.
Yeah.
But when we do the post measurement, what will we get?
No, so if you keep, I mean, like you are measuring, of course, the atom, right? But you, I mean, you are asking after you you have measured a lot of atoms, has the cavity reached a steady state? I mean,
that condition is different. But you said that there is certain condition, there is no steady state.
Right, yeah, so cavity never reaches a steady state. I mean, if you keep doing it, I mean, it will, I mean, eventually it will move to a higher photon number. I mean, so the photon number keeps changing.
Okay, then suppose you are doing then a post measurement, then what will come? You showed one condition there. You measure the post measurement state.
Yeah.
You will get something, or
it will still be the
do
same.
The measurement, what will come?
No, I mean, if you are saying measure the cavity itself.
Suppose we want to measure the state post measurement.
Yeah, no. So when I say post measurement, I mean post measurement of the atom, not the cavity.
Okay. So
right.
What will come in the atom?
In the atom, of course, you will get up and down because there are only two states, right? So that, I mean, that's not a.
Cavity.
In the cavity, it will never reach a steady state. I mean, like if you keep doing it for longer, it will go to a different state.
Okay, so you said that it's basically like a biased random walk where the bias depends on the position n, right? So the from 0 up to some n threshold, it's going to the left, then it goes to the right, then it goes to the left, and so on in the Vx profile.
So in this case, it's a very clear biased random walk,
yeah.
Right? But the funny thing here is that these rates, I mean, even though you have chosen parameters such that in the Lindblad limit you would have a biased random walk which is biased in this direction, but in the discrete model the biases can be It depends on where you are.
So in your Vx profile, it
Yeah.
goes up from 0 to some threshold value of n before it goes down.
In the what profile?
The effective potential landscape, yeah.
Yeah.
So this one, or it goes down, I guess, first.
Ah,
Then-
okay, yeah.
So this threshold where it sort of goes up and then turning point and then goes down again.
Yeah.
Does that threshold go to infinity in the Lindblad limit? So
Yeah. So in the Lindblad limit, you would either go just in, I mean,
Just
you
become a
wouldn't.
single well sort of
Right,
thing?
yeah, you'd get a single well essentially. Right, yeah.
Hi. So coming back to the absence of steady states,
Yeah.
do you know if there are some conditions for a steady state to exist? Because for me, when I look at a Liouvelian in general, if it's an n by n matrix, I always get a steady state from that, and it ends up with a rank n-1 matrix. So
No,
maybe
so-
you know why is it like that? I don't.
I mean, Lindblad, of course. I mean, also it would depend on these rates, right? I mean, for example, trivially, if gamma e was greater than gamma g, you would never get a steady state, right? But I mean, that is for Lindblad. Okay, but now, I mean, the surprise out here is that, of course, here the rates, I mean, the biases are depend on where you are. Okay, and in this case, I mean, whatever parameters you choose, it doesn't have a steady state. Yeah, so that's the big surprise. I mean, it's completely different from Lindblad.
If no more question, please thank the author, speaker, and yeah. So now there will be a voting for the flash talk. Yes.
Okay, some energy there. So do we go for lunch now, or do we go for lunch and reconvene in an hour and do the poster then? So lunch now. Who wants? Okay, so poster. What?
We can have either the poster now and lunch after, or lunch now, but only 1 hour, and sharp 1:30 we are there, and we have the poster speedrun session. It's okay at Teams, so don't worry.
Thank you.
So who would like to have to go for lunch now and poster at 1:30? Who would like to have poster now and lunch afterwards?
Yeah, poster now.
So poster now.
Sorry for the hungry people. So, yeah, so we'll keep going, starting with Anthony, young people first. So the order will be Anthony, Nishant, Bhumija, Ashwarya, Shruti, and Asta. I'm not sure about the pronunciation. And then, if time permits, Romain, Nikos, Niranyan, and maybe Fabienne, but all these people have talks, or we'll see. I did notice, I went to see Romain's poster, and I must say, this is very helpful. If you don't want to follow the talk, or you fall asleep during the talk, I think you can catch up in front of the poster. So he actually did put some efforts into allowing for naps. So.
So hello everyone, I'm Anthony. My poster number is 23, it's over there. The last one over there. Okay, I got some publicity from Fabien yesterday. I guess I'll have more today. So the idea is that I'm working at ONERA, which is the French Aerospace Lab. It's a lab in Palaiseau, near Université, it's included in Université Paris-Saclay. And we've been developing quantum gravimeters for about 20 years now. They are deployable in field and either on plane or on a boat. But for the last 5 years, we've started a new activity, and the main interest is exploring the possibility of using read bag atoms for RF sensing, but with another approach that is done in, for example, Lumine. where we are cooling down our rubidium-87 atoms in a magneto-optical trap. And so we are able to do a two-photon transition from the ground state to readback state. And so here I represent schematically the magneto-optical trap and the lasers that we use that are counter-propagating. And when we look at the fluorescent signal of this magneto-optical trap that is always sending light, Sanjukta yesterday talked about, yesterday we were at the last talk, she talked about the trap loss spectroscopy, where the fact that once we excite the atoms into a readback state, the fluorescence, the amount of number of atoms in the trap get lost. Thank you. So I'm describing this graph here. So when we are at resonance with this state, with this transition, we lose the atoms in the trap, and so we observe a drop in the fluorescence, which is our signal that we can use. And once we apply a microwave field that is resonant between two readback states, we will strongly couple these two states, and we obtain a Noether-Tönnes doublet that you've also seen many times now. And by measuring the difference in frequency between these two resonance, we can go back to the amplitude using the value of the electric dipole that is associated between these two readback states and the fundamental constant. And so in my poster, I will discuss many parameters of this sensor, so the linearity. If I apply a microwave field, how well does the response of the sensor stay linear? The sensitivity, how well can I measure a microwave field? The dynamic range, what's the range of my measurement from the smallest to the largest value of electric field I can measure? The stability, so if I'm trying to measure something and through time, is it changing or not? We can also look at resolution and also at multi-parameter estimation. I'm not going into that actually, but we can discuss it. So we are able to not only measure the amplitude, but also the frequency. We can also measure polarization. There's many things going on in the field. And what we are also trying to do in the next few years is implement an optical tweezer array of atoms to explore the potential use of, for example, quantum metrology protocols to improve the sensitivity or obtain a very high resolution measurement. And so I can discuss with you many technical aspects, acousto-optic deflectors, spatial light modulators, atomic fluorescence on EMCCD camera. I can discuss frequency locking, laser amplitude lock. There are many things that I can discuss with you, so please come and visit my poster.
Thank you very much. Thank you very much to Anthony. So now we have Nishant, poster number 24. Okay. So we go straight to Ashwarya. Yeah. Who's one of the co-organizers of the speedrun poster session. So warm round of applause.
I have a video also to play and maybe do it from here. Hello everyone, good afternoon. Myself Aishwarya from Raman Research Institute. I'm working under Dr. Sanjukta Roy. So we are working in quantum sensing and quantum computing with the Rydberg atoms. So this is the name of a lab, Coral, Quantum Optics with Rydberg Atoms. So I'm from Himachal Pradesh because I saw a few of the posters, they were listing out their things, like from, this is where I belong. So, okay. Now comes to the topic. So as you know, the Rydberg atoms are those who have the like outermost electron excited to the higher principal quantum state, which provide them such beautiful properties which we can harness in different fields of like quantum computing, quantum sensing, and such like that. So so we have this term called EIT, which is like greatly explained in throughout the conference. So it's just a brief that under the for the Rydberg excitation, we have this 2-photon excitation method. We have 780 laser, which we call as probe, and 480 as a coupling. Under the influence of strong coupling, there is a transparency window which appear in the probe. Here you can see that. So now, then we have the energy. If we go in higher principal quantum number state, the energy gap between them becomes in the level of microwave. So here is some animation. So under the influence of the microwave field, the EIT peak splits in the ultratown, and we have the separation between these two peaks from where we can measure the electric field which is falling on the Rydberg vapor cell. So this is the formula from where you can measure. Now, this is the classical way how people measure the electrical field, but we have a choke point here, where the energy of the electric field is not enough to split out the EIT line width. For that, we have different method that we have used. If someone wants to know, can come to our poster. I mean, we can explain it briefly there. And also there is such experiment where we try to detect the direction of the electric field, the polarization angle. So by rotating the polarization of angle of 780 and 480, we try to map it out. So the results are in the poster. You can come visit. And other than that, we also work in cold Rydberg atoms. So this is our setup there. And we recently made the optical tweezer where, recently we have 7 atoms trapped, but it's a bit older picture where 140 atoms were trapped using a dipole trap. So we are using 850 nanometer laser for that, which is far detuned. Now, next. Okay, so in order to lock our laser 480 and 960, frequency double of 960 and 780, we are using this microwave cavity. Sorry, this stable laser cavity, which has the mirrors specially coated for our requirement. And this is the modes of the cavity. And in order to measure the thinness, we did this transmission reflected. We took the reflected signal and saw how much time it takes to completely fall off the signal. And from there, we can measure the thinness of the cavity. So it's around 14K. Okay, so this was the error signal which we found from the LG00 mode. And if we lock it there, we get around 20 kilohertz of line width. Okay, based on that, we did one experiment in the lab, and we tried to lock both of the lasers through the cavity, and we can see that the ATS split become very nicely, and the feature become very sharp by the locking it. If someone wants to know in more detail, like how we lock it, how this whole process goes on, they can come in our poster, which is at poster number 26. Thank you.
Thank you very much to Aishwarya. So please go and visit poster 26. These are posters on this side. So I know it requires some tunneling effect to go from the coffee to there, but I'm sure, taking a coffee cup, you can go there. Just poster presenters and interested people alike. So now we welcome Shruti, poster number 27.
Good afternoon. Okay. Good afternoon, all. So my poster basically is going to speak about how we are building an OPLL TCL mechanism to basically transfer stability of the optical frequency comb, which is currently housed in RRI, to continuous wave lasers and do experiments with it. So Raman Research Institute has a frequency comb which is not a fully automated comb, so which means that I was tasked with the responsibility of building a locking mechanism for it. So why do we need an OPLL? So essentially, it provides an absolute frequency sequence.
Sorry, what is OPLL for?
Optical phase lock loop. I'm so sorry. I should have basically expanded that. So a free-running comb can be useful for any kind of broadband measurements, but if we are basically interested in high power single frequency excitations, then we definitely need to lock the comb to a laser or vice versa in order to achieve this. So very low power and limited accessibility of each comb line is not practical if one is looking for specific transitions or coherent manipulation. On the other hand, if we are looking at what is a transfer cavity lock, that is a laser stabilization technique where a slave laser is locked to a master laser via a cavity. And the cavity basically acts as an intermediate where the transfer happens from the master to the slave laser. Now, the biggest advantage of a transfer cavity lock lies with its long-term stability and wide-range tunability, where you can do different lasers, and it's not limited by a spectroscopic lock. So the idea here is to combine both benefits of the optical phase lock loop and the gravity transfer lock into achieving a locking mechanism where the comb's stability can be transferred to any number of continuous wave lasers that can be used in the lab. So what are the advantages one has with the optical phase lock loop? One, it has a high bandwidth, and it transfers both phase and line width. But what are its limitations? One is it has a very small capture range. It requires a stable beat, because beat detection is the most important part for the optical phase lock loop. And we need the frequency of the beat to be as close as possible to any of, not the frequency of the beat, but the frequency of the laser to be closer to one of the comb lines. Otherwise, we're going to spend a lot of time trying to just search for this. On the other hand, the transfer cavity lock has a large capture range and slow drifts and are handled very well. And of course, there's long-term stability. But its limitations are that it has limited bandwidth in the order of kilohertz. And the efficiency in transferring the phase is much lower compared to the optical phase lock loop. So eliminating their minuses and keeping only the plus, we can see that if we integrate the transfer cavity lock into the optical phase lock loop, we can basically have the frequency close to capture range. It prevents losing the lock due to large drifts. And hunting for the beat signal is extremely narrowed down. We can achieve beat signal to be much faster. In terms of high bandwidth and long-term stability, both are going to be achieved with this particular hybrid. And it's especially useful if we have narrow line width transitions and extremely long experiments. So just to get a better picture, this is a block diagram where we have the optical domain. I'm more interested in the calcium ion forbidden transition, which is the 729, since also specifically the Menlo system comes with a inbuilt beat detection unit specific for the 729 nanometer laser. And if I would welcome any suggestions which can better this particular mechanism which we are trying, and please do visit my poster, which is poster number 27. Thank you.
Thank you a lot to Shruti. So 27 is really next to the Raman Museum, and maybe, I don't know if you said it, you're working under SADC, aren't you? So it's for people to organize their thinking. So now we welcome Asta, number 28. So don't forget to say where you work, when, with whom. Yeah.
Okay, my name is Astha. I have just finished my bachelor's and master's from Indian Institute of Science. I did my bachelor's and master's thesis with Professor C.M. Chandrasekhar, and currently I'm doing RA in the same lab. So this is my master's thesis work.
Sorry. Where is the lab? Which city?
IISc Bangalore. Yeah. Quantum Optics and Quantum Information Processing Lab under Professor C.M. Chandrasekhar. So this is my master's thesis work. So what we did was we constructed quantum circuit for boson sampling. So boson sampling is a model which gives us quantum advantage. However, there are certain problems in boson sampling experimentally, because you want interference at each beam splitter. So which is very hard to get experimentally. So what we did was we constructed quantum circuit for generalized boson sampling model. And once you have a quantum circuit, it is not restricted to photonic qubits. You can do boson sampling in any other cubic hardware as well. So, so this is the encoding scheme for 2-photon N-mode boson sampling. So you have a cascade of beam splitters, and you are sending 2 photons into it. The number of modes can be any, it is arbitrary. So this is the encoding scheme which we have used. So if you have n modes, we have encoded it into n qubits. So each mode corresponds to 1 qubit. And this is the scheme which we have used. So if there is 1 photon in that mode, then it is encoded as 1. If there are no photons, then it is encoded as 0. And the idea behind making the quantum circuit is any n-mode interferometer is a sequence of 2-mode beam splitters. So if you are able to make quantum circuit for 1 beam splitter, you can use the same circuit for all the beam splitter, and when you add all of them, you can get quantum circuit for the whole scheme. So we are using 1 reusable circuit block for each of the beam splitter, and this is the repeating unit. So this unit is for 1 beam splitter. If your beam splitter is acting on mode QY and QJ, then you apply this gates and you have 1 ancilla qubit for the whole circuit, which will act as control for the last 2 gates. So we have experimentally demonstrated this for n equal to 4 mode. So we did 2 photon, 4 mode sampling. So this is the optical scheme which we have used. And so you can see there are 4 modes, and you can send 2 photons into it, which will give you 10 possible states. I did not have space to display everything. So for more details, you can visit the poster. There we have everything. So we made a quantum circuit for this using this scheme. And so that circuit was very big. I could not add it here. And we did it for... we reduced the circuit for specific inputs. So this is the reduced circuit for the input 0, 1, 0, 1. And then we encoded it into path and polarization degree of freedom. So first, second, and fourth qubit was encoded into path degree, and the third qubit was encoded into polarization degree. And we did it using 1 photon only, even though the sampling is 2 photon 4 mode. And this is the output we got. So the red one indicates the expected, and the blue one indicates the measured output, which you can see resembles very close to the theoretical output we were expecting. Yeah, so this thing demonstrates that the scheme we have used works well experimentally as well. For more details, please visit poster number 28. Thank you.
Thank you very much, Asta. So now is the time for the junior member of the poster session. So them, I'm not afraid of rushing, okay? So the idea is also that maybe they introduce a bit their career path, just PhD, postdoc, etc., so that it's useful for the career session, or if you want to chat with them. So the idea is to just put them there, because they'll get plenty of exposure and then time to explain the science, so that the people at the back and the younger people are not afraid to go and chat to these people.
Yes, okay, so I take my chance to introduce myself. So I'm Romain, I'm coming from Laboratoire Kessler Brussels, and what I'm doing for scientific activities, actually during all my career, it's combining cold atoms with optical cavities. So I started to be interested in this kind of very interesting game and funny game during my PhD. So I did my PhD under the supervision of Serge Haroche at Laboratoire Kessler Brussels, and it was also a collaboration with a group of Jakob Reichel that was at that time in Munich. And the goal was to combine cold atoms that were trapped in an atom chip, so magnetically trapped, with an optical cavity, and it was a kind of exotic cavity, which was a microsphere cavity where the atom can be coupled with the evanescent waves of the cavity. And then as a postdoc, I moved to Stanford University in the group of Mark Kasevich, and here it was almost the same game. It was putting cold atom inside a microscopic cavity, and the goal was to produce a kind of spin squeeze state that could be useful for quantum metrology if you want to improve an atomic clock or an atomic sensors. And then I came back to Laboratoire Kessler Brussels as an associated professor, where I joined the atom chain group, working again with Jakob Reichel, and we are working for now almost 20 years. And now what I'm mainly doing is combining cold atom inside a fiber Fabry-Perot cavities. So these fiber cavities, it's like a standard Fabry-Perot cavities, but it's really microscopic because it's just between two fibers. And I think you have already seen this cavity because I came from Paris with Gokul. Now it's a new kind of new activities we have in the team. We try to develop more practical application of the cavity for real life, like a trace gas sensor or optical filters. But if you have a question, you can ask Gokul. He has a poster which is just behind the wall. So if you have a question about this part, talk with Gokul. But the main motivation why we have developed this cavity, it was, of course, more for quantum physics, and we are really interested in developing multi-atom entangled state using cavity QED techniques. And I'm just highlighting a few results. We have really pushed hard to get high fidelity quantum non-demolition measurement, and with this kind of measurement, we can produce some kind of specific entangled state, like W state or spin squeeze state. And now more recent activities, it's investigating what happens if we are having an ensemble of atoms but with different properties, so different coupling or different atomic frequency. And there is a kind of subtle effect like cavity protection. And the last topics I will present during my talks is a kind of hot topic in the community, which is combining these single atom arrays with strong coupling cavities. And you see the progress we are doing right now. Thanks.
Thank you very much. So this is poster number 9, and some talk in the program, but less interesting than go and interact directly in front of the poster, from my point of view. Okay, now Nikos.
Yes.
Who's poster number 1?
I don't have a poster. But
okay, you should be.
Yes, sorry. So, hi, I'm Nikos Fayard. I am maître de conférence at ENS Paris-Saclay, and I do my research at Lumine. And basically, I'm a theoretician that studies collective effect in complex media. I've done my PhD at the Langevin Institute in Paris. At that time, I was working on light scattering in classical complex mediums, so made of classical dipoles, not atoms. And I was interested in the speckle pattern that emerge from those systems. Then I changed the topic of my work. When I went to ICFO with Derek Cheng, I started the study of open quantum system with waveguide QED and many body localization into those systems. In a second postdoc at Laboratoire Charles Fabry, I worked with Christophe Sauban in the design of new waveguide for waveguide QED in collaboration with Alban and Julien. You will learn about that tomorrow maybe, for sure, because I will talk about that also. And also I worked with Jean-Jacques in collaboration with Igor Ferrier-Babu and Antoine Brouez on the control of collective states in 1D ordered atomic chain. And now that I'm at Lumine, I work on 3 different topics. The first one is the study of collective properties on top of engineered waveguide. In those systems, there is funny things that emerge because the Born and the Markovian approximation can break. In a second project, I work on the competition between superradiance and pure dephasing. This is something I do with Elisabeth Gliot, who is here. So she has a poster on that. She's a postdoc with me. And on a third project, so in this I collaborate with Fabien, Nadia. The PhD is Elwin, who is here. There's also Adwait, who will give a talk on that. And in this project, we study spin noise spectroscopy in the dense regime where the signal is affected by collective effects. So that's it for me.
So yeah, can you go back one slide actually? So thank you very much to Nikos, sorry. And yeah, because Nikos did a very, very good job at connecting people. He mentioned very people, so a lot of people there. But maybe Adrien is doing his PhD with Igor and Antoine, in the, the people you you mentioned. Okay, Niranyan, or so that's number 14 for my super efficient assistant in finding the random numbers. So I hope you got all the numbers to play the lottery, because it wasn't in the right order, but...
Hello, everybody. I came to this side to say that I did my PhD about here, in the room right below this point, where we made a lithium experiment, which does hybrid ion atom trapping. I also did a brief work with rubidium in optical cavities in the other part of this institute. Later, so I have two posters today because I used the opportunity to bring one for each of my posters. So this is the one that I'm currently working on in the Observatory of Paris. So I work in the group of Frank Pereira in the subgroup led by Leonid Sidorenko. So what we make is in the lab, we measure the value of acceleration due to gravity, which some of you might have been doing, which you have done in your high school, but to a precision which is at the level of parts per billion. Okay, so there are some interesting reasons why we need to do that, because once you start measuring the acceleration due to gravity more and more precisely, you eliminate the effects of things like latitude, longitude, rotation, and then effects of large reservoirs, hills, etc. And eventually, at a later point, you start measuring something which is sensitive to local effects due to what is there right under the gravimeter at some distance below it. Okay? So naturally, it is useful for geophysicists and for some guys who need to explore without completely drilling through the earth. Here is, so what we have done is we have done the indoor tests and done meteorological performance assessments on this portable system, which is what I have presented in this poster. This guy has done a survey in the city of Reims in France, where it is known that there was a medieval city, and this is right now a parking lot, but it is known that underneath that are the remains of an old medieval city sometime during maybe the 12th century, I guess. So what you're seeing is actually a gravity map which has been measured by doing 1 point at every 10 meters distance. The new instrument measures both gravity as well as the gradient of gravity. And you can see that the gradient map has more contrast than a gravity map in this particular case, because the elements that are trying to be probed are near field. Because, I mean, an archaeological remains is not many, many meters below, but it would be like 10 to 30 meters below. And by inverting this map, they have tried to, I mean, our partners, BRGM, and particularly the inversion was done to find the contours of where the walls of this particular archaeological city were, etc. The way they have done is, of course, gravimetry is not going to give you all the information. So what they have done is, in some places here, which were more accessible to do invasive testing, they had dug up to find the actual composition over some distance. And they know that mostly what this place is made up of is three materials, which is gravel, stone, and the medieval mortar. So they have fitted a distribution of these three materials to find the contours. Okay. You will see the instrument in better pictures and the final results in the poster. It's 14. And what we have done is, these are testing along with multiple gravimeters. This is called the gravimetry hall in LNE, which is a bit far from Paris. But so it stations a superconducting gravimeter, which is not portable, in one site. And then we rotate between all these very well known points where we know gravity for many years. We have been measuring that with different instruments. It's a simultaneous campaign with the old absolute quantum gravimeter of Exhale, the new version that has been developed, which has two cold atom sources which are falling, which is how we obviously measure gravity and the gradient, and classical instruments, which are actually just spring mass instruments. So to see how they compare, you can come to the poster. The other one is a poster on my talk. The talk is tomorrow, so I think if you want to have more details, you can also come and catch me at the poster. This work was done in Amsterdam Optic. in the group of Vincent Jos, and also we have the luxury of sometimes talking to Allah, because it's a project initiated during his time with his interest. Our theoretical collaborators are from LKB, and we also have another sort of mathematicians kind of interaction that we do, because the theory of Anderson localization is very close to landscape theory, which is application, which has some interest in pure mathematics. So briefly, I would say that if you...
Yeah, so because you have the talk tomorrow.
Yeah, that's right. So I think it's even better. Yeah, sure. Sure.
So
I think it's better you catch me in the talk.
Yeah. So this was very good to introduce the collaboration, and you have the talk. And the very last presentation is Fabian, and then we'll. No, you don't want to do it? Okay, so. Okay, so time for lunch. Thank you, and let's thank all the speakers for the speedrun sessions. Who is you? Who are Alban? Okay, Alban, you got nominated as the next chairperson. Congratulations.
And I work on different aspects of quantum dynamics, open quantum systems, and many-body physics. And also I work sometimes with experimental colleagues, both here and outside. And today I want to talk about this topic, Mpemba effect from Stark localization, which will eventually boil down to the overall message or a broader idea that you can design energy landscapes for quantum systems and use rare events happening on that energy landscape to produce a hierarchy of metastable states with exponentially separated lifetimes. Right? So these are in a relatively simple setting. So this work was done with Nico Albert, who is a PhD student in TU Dresden, with Masoud Haq. So this is not quite an Indo-French collaboration, but close. I'll get there. Okay, so let me move ahead with what is Mpemba effect. So this effect came to fame in the 1960s when a 13-year-old student in Tanzania named Erasto Mpemba was playing around with ice cream mixtures which are melted and trying to freeze them. And he noticed a curious fact that if you have a hotter mixture, that can cool faster than if you start from with a colder mixture. Right, so that's the characteristic feature. You start from a hotter thing and cool down faster. This crossing with another trajectory is the telltale signature of this, what's called Mpemba effect now. And this, instead of temperature, you can also have some other distance measure from some equilibrium state or some steady state. And with time, that distance will show crossings like this, right? So that's the more general Mpemba case. This is in a classical system, and by now there are several experiments which have seen this effect in different types of classical systems. These are some known examples from recent literature. And one unified description to understand this effect is in this form. So if you think that your classical state is described by some probability distribution which is evolving in time according to some linear differential equation like Fokker-Planck, then you can expand the difference from the equilibrium, the distance to the equilibrium, in some sense in terms of all the normal modes, right, all the relaxation modes. And one of those modes will relax the slowest, which is called this lambda 2 in this particular expression. So it eventually boils down to the coefficient of the slow mode that you have excited in your initial state. So how much? If you have excited the slowest mode more in your initial state, you will live the longest, right, because it takes the longest, survives for the longest. And so if you start from different thermal states at different temperatures T, this coefficient will depend on that initial state. And suppose your some relatively low temperature state has a high overlap, A2, right? So that lives longer compared to a hotter state which has a much smaller overlap, which will die out faster. So this sort of characteristic negative slope in this A2 as a function of temperature tells you that you will see crossings like this, right? Because hotter states will die out faster, relax equilibrium faster than colder states, cool faster. Okay, so this was classical, and in the last few years, people have asked whether similar effects can be seen in quantum systems. It's a natural question to ask, both in closed system as well as open systems. So closed systems, by now, there's already quite a significant literature, and this is reviewed by this nice review last year. And the central example that people talk about in this case is that of subsystem thermalization. So there's no concept of density matrix for the full system because it's closed, but you can talk about a subsystem of some extended system and say how it is thermalizing starting from a non-thermal state. Right, so and the typical example is suppose your Hamiltonian has some conservation law, for example, the total SZ conservation, but your initial state doesn't preserve it. So you suppose you prepare all of them in the, all of the spins in the Z direction, then you rotate them all by the same amount. So then you will have a superposition of different total SZ numbers, different quantum numbers that are individual, that are conserved by the dynamics. So if you start from an initial state, then your subsystem A, the density matrix for the subsystem A will have off-diagonal sort of, it will not be block diagonal in this quantum number in the symmetry sectors, it will also have elements that are connecting different symmetry sectors because your initial state is not definite symmetry sector. And so in the dynamics, because the total Hamiltonian conserves this total charge, what you find is that these off-diagonal elements eventually die out, and so the subsystem thermalizes, which is supposed to be a block diagonal density matrix. Right? That's what eventually happens. And then you can, the question is, if I start with more off-diagonal elements, can I get rid of them faster? That will be an example of Mpemba effect. And people have found indeed that is the case. So this is an experimental example using a trapped ion chain,
where they have, start from, so this measure is measuring how much asymmetry is there in the initial state, and then it dies out, you see these crossings and so on. What's nice is that for integrable systems, there's a nice physical explanation of how this is coming about, what is the physical origin. And essentially the idea is that the initial state, which breaks the symmetry, you can quantify the symmetry breaking in terms of some quasi-particles that have been excited in the subsystem, right? And in the dynamics, as the dynamics happens, these quasi-particles will escape the subsystem, and that will correspond to thermalizing of the subsystem. And so if your hotter quasi-particles, so more excited, more symmetry breaking state, if those quasi-particles can escape faster out of your subsystem, then of course you can reach equilibration faster, right? So that's a hand-wavy physical origin for this kind of effect, of course, which is made more precise in this paper. But the nice thing is there is a nice intuitive understanding of integrable systems, which doesn't apply to non-integrable systems or open systems. The thing I'll discuss is about open systems. So in open quantum systems, again, you have some density matrix evolution. So you have some Liouvillean dynamics, some linear dynamics of the density matrix, which you can expand in different modes of the Liouvillean. And again, typically there's one slowest mode which will take the longest to die out. And so it boils down to this coefficient C1. If you have more C1, then you will live longer. And so one brute force approach is to simply engineer a unitary that you can apply on your initial state to kill this overlap C1 completely, right? So if you can engineer, do something to the system to make C1 0, then of course you will relax much faster because the slowest mode is not present. And so this idea was also experimentally tested in this paper with a single trap time.
Just a question.
Yeah.
So you don't care about the steady state, you care about the mode with the...
So you will eventually reach the steady state, but how close you reach depends on your overlap with the slowest.
Engen value with the largest wheel, the smallest wheel path.
Exactly, exactly. If you don't have that mode present at all, you will relax faster. Okay, so it again boils down to this variation of C1, how that depends on your thermal states as a function of temperatures. Again, there's some negative slope or something. And what's nice is that recently there's also some sort of more theoretically oriented papers which have said that the subsystem thermalization problem in closed systems can also be recast in terms of some slow mode overlap. So this, if you like, is providing a broad framework for thinking about MPEMBA, the slowest mode overlap. And by now, you will find lots of papers also in open quantum systems which have found this MPEMBA-like effect arising from different sources. So symmetry, nonlinearity, criticality, metastability, noise, and blah, blah, blah. There are lots of examples. But if you read those, it sounds a bit like magic because you have some ingredient in the system and that somehow gives rise to MPEMBA. You don't really intuitively understand what is causing it. So this physical origin, which was present for integrable closed systems, is not really there in open systems. Okay, so that brings us to what we do. And what we do is this investigate this energy landscape picture. This is a very nice picture which was developed for classical systems. And the idea is that you have some potential energy landscape which has a global minimum here and lots of other local minimum. So if you're trying to, the classical ground state is basically sitting motionless at the global minimum. And so if you compare, if you have some local dynamics on this energy landscape, energy surface, then starting from a metastable state like this, it'll take you much longer. You have to first go up in energy and then come down. Whereas here, starting from a relatively high energy state, you can directly go down to the low minimum. Right? So this provides a physical picture of why this effect, where is this effect coming from, on the nature of the landscape and so on. Well, you can ask whether this landscape picture also can be generalized to quantum systems. Does it make sense to ask of a quantum energy landscape? And can you get a similar effect? So here you have to remember two things. One is that the quantum ground state is not really sitting motionless at the bottom of the potential energy. Right? We have uncertainty principle, so it's the total energy you have to minimize. You're not just going to a potential energy minimum. And so you have, is there any notion of total energy surface in that case, not just potential energy? And then you have to have some notion of local flow on the energy surface. So you cannot directly hop from this to that, which will correspond to a non-local tunneling process. Suppose you don't want that, otherwise the MPEMBA effect will not be there. Right? So these two ingredients you need. So the question becomes, how can you design a total energy landscape with this kind of flow in quantum systems? Right? So
For that, you need some, suppose your dynamics is local in position, and then you need some correspondence between total energy and position, right? Because otherwise you cannot really say that as a function of position, this is my energy, right? So that sort of naturally tells you that you need localized eigenstates of the Hamiltonian. So that there is a definite relation between where it is localized and what its energy is. That will allow you to construct a landscape as a function of position. And the natural models we know of, which gives you localized eigenstates, are these hopping models with different types of potentials. So disorder or quasi-periodic gives you random energy landscape as a function of position, whereas if you have a tilted lattice, that gives you a more structured. So you know that as you go this way, the energy will keep, the total energy of the single particle will keep increasing, right? So the latter allows you more control to design an energy landscape. And if you wanted some idea, some similar thing where you have competition of two, one global minimum and one local minimum, this is a minimal setup, right? So this I am thinking of as the global minimum, this I am thinking of as the local minimum. Your eigenstates, suppose your J, the tunneling elements, is not very strong, such that the eigenstates are relatively strongly localized, and this potential here is lower than that potential, so your ground state is basically sitting at this site, right? So that is, you want to get to this state if you want to cool down to the ground state, right? And then you have these nearest neighbor hops, but on its own, the Hamiltonian dynamics will not take you from somewhere here to the ground state. You need some other component as well, right, which can lower the energy. So you need something non-unitary. And so one way to do it would be to have incoherent hopping one way on this left leg, right? So whenever you get to this particular site, you can then hop here. You have a biased sort of directionality, which takes you eventually to the ground state, which would be an eigenstate, and you don't evolve, right? So this incoherent hopping can, of course, arise from different physical ingredients. For example, you can, for this site, you can have an excited band, and maybe the hopping takes you, the coherent hopping takes you to the excited state, which then decays to the ground state band, and so on. That is one way. You can also think of measuring whether the particle is in the site or not. And if you detect it on the site, you can apply some gate or something which will transfer to the other side, right? So, and all of this can also be done in a spin model. So if you have a single particle, you can have think of it as a single spin-up excitation in a sea of spin downs, and you have sort of spin exchange model instead of this hopping model, right? So that's the basic setup. Now, if you start from some non-ground state, so some state, eigenstate like here, right, this state, this wave function will have some amplitude at this site too, at this peak site. So you are trying to detect the particle at this site, then only it can be transferred here. So the detection probability is the rate at which you are doing the measurement times the weight of the wave function at this site, right? So it's a product of these two things, psi d squared. And we know that psi d depends strongly on d. The farther you have, the more larger you make d, the less and less wave function amplitude you have at this site. It actually goes down faster than exponentially. And so therefore, you see that if I start farther, which is lower energy, I will take a long time to eventually cool to ground state. Whereas if I start closer to this peak, I will soon be detected, and then I'll come down to the ground state. So therefore, it sort of very naturally leads to higher energy states cooling faster, right? And okay, so this is a rare event, this detection event, and that gives you a hierarchy of cooling times depending on how far from the peak you start. That's the basic idea. And then you can simulate this, right? You take some particular model, let's say I release it from here. It's a tilted lattice. So here I don't see the incoherent hopping. I've simplified this setup a bit. So I only have one bond here. I'm taking the limit where this hopping is extremely small. Doesn't really matter. The effect is also present if this is non-zero, but this just makes the analysis simpler. So if I start from a state like this, what you expect is it to oscillate under block oscillations in a tilted lattice. And indeed, that's what happens. So if you evolve a trajectory, like a pure state trajectory, it oscillates as a function of time until it gets detected at this site, and then sort of hops to the first site. So you have this long oscillations, and then eventually it goes. So these are showing 5 different trajectories. They have decayed to this ground state at different stochastic times. And if you average over many such trajectories, you get the gray background, which is the average evolution coming from the density matrix. One question you might have is, why is this moving up slightly, not just oscillating at the same level? That's because you are measuring it repeatedly, and lots of the measurements
tell you that the particle is not there. Right? So these negative measurement outcomes actually project out that site from the wave function and sort of pushes the wave function away from that site. So that's why this actually moves up slightly. Okay, and then if you look at the average, compare the average evolution starting at different sites, indeed what you find is a site 2, if you start from site 2, you decay very fast. Site 3 decays 10 times slower. Site 3, increasing the distance, it sort of exponentially becomes slower and slower. And you can go on depending on how many sites you have. You see these satellite plateaus here, that's because of this upward shift. So it slightly moves away in the course of non-detection events, which makes the final relaxation a bit slower. But you can clearly see the hierarchy of cooling times. And you can also try it, these are for localized initial states. You can also try it for different thermal initial states, which is the original Mpemba. And indeed, if you start from a higher temperature state, that eventually crosses below the low temperature evolution, and the distance from the steady state becomes smaller. Right? So at site 2, you're measuring, and then that takes you to the site 1. At, on average, some intervals. So this is modern, I mean, the simulation is from Lindblad, but you can also do it regularly. I suppose it's the same sort of. Yeah, so you clearly see thermal Mpemba as well. And the overlap curve, the C1, overlap with the slowest mode, that again has a non-monotonic, this negative slope as a function of temperature. So colder states cool slower than hotter states. Right, so that's the, and what's nice is by tuning this epsilon, you can sort of tune this overlap curve also, because your slowest mode is basically sitting at the 7th site. And how, as a function of temperature, the overlap with the 7th site first increases, and then the temperature becomes much higher than epsilon, then the overlap goes down. So you see where it is coming from. Okay, so that's for single particle, and the coherence in the position basis is crucial. If you try to do the same thing for a classical particle, so if you make all the hops incoherent, then it doesn't happen. So I can also have, just R1, classical random walk with rate R1 this way, rate R2 this way, and rate R prime from going to here to there. I don't have the reverse process from this to that because I want to eventually reach this state. And if you think of some metropolis cooling algorithm, this would correspond to a temperature which is much bigger than this spacing delta, but much smaller than delta prime. So you don't have any reverse hop. You have only one hop, one way, whereas these two are bidirectional. If you do that, starting from a localized state, you don't get block oscillations. Instead, you get diffusive spreading, which is what you expect. And so the trajectories look like this, with the background spreading diffusively. So this is very different from the quantum case. The separation of timescale is not present because it's not exponentially localized. And also, for thermal states, you see negligible Mpemba effect. The crossing is almost invisible. Okay, another broader message is that using this technique, you get this hierarchy of relaxation rates. This is the full Liouvillean spectrum. It has a lot of structure to it. So if you focus on the real eigenvalues, you will see that these are basically populations of the different sites. So this is the population of the energy eigenstate localized at the 7th site, the last site, which decays the slowest. This is the population of the energy eigenstate localized at the 6th site, and so on. If you look at the imaginary eigenvalues, then, okay, and these rates we can sort of predict analytically also. The imaginary eigenvalues represent coherence. So this is the coherence between site 6 and 7, the last two. This is the coherence between site 5 and 6. This is between 5 and 1, and so on. Right? So essentially, the density matrix elements in the energy basis have their own timescales for evolution. They are not almost talking to each other. And this, you see that the coherence decays at twice the rate or half the rate as the populations, and that also you can sort of explain using this hand-wavy argument that these different eigenstates will evolve at different, independently with their own scales. I won't go to the details. Okay, this was all for a single particle. I can ask what will happen if you add interactions, or if you just add two particles. Because then if I just have two particles, the number of states are not just this, right? So I can put one particle here, one particle there. So there are two coordinates. There's no one-to-one relation between coordinates and energy. But on average, the average energy is set by the center of mass of the two particles. And if the center of mass is closer, then you can decay faster. So on average, you see that higher energy states will cool faster also, even without any interactions. if you add on-site interactions, then this protocol takes both the particles to site 1 eventually, and that will be the ground state only if the interaction energy is negative. Right? If you have both particles sitting here and that costs a positive interaction energy, that may not be the ground state of the whole thing. Thanks. And so that's why I take U less than 0 and equal interaction energy on all sides. Right? So what you find is that the nature of the decay is very sensitive to this interaction energy, U, the value of U. So when U is 0, they sort of decay independently. So if you release both particles at site 7, basically one goes to the site 1 after some detection event, this one remains at 7, and after a while this one also goes to 1. So this is the sort of, if you take the expectation of n1 times n7, it goes to some non-zero value before it comes down. Whereas if you do the same thing with a strong negative, strong attractive interaction, then it's very difficult for the Hamiltonian to break the two particles when they're initially released both at site 7, right? So they remain bound, and they cannot sort of migrate independently. So or they just remain 7, 7 until both of them goes to 1, 1. So you never get a population excitation of 1, 7. So this n1, n7 is almost close to 0. And because so the slowest mode here is 1, 7, whereas the slowest mode here is 7, 7. And 7, 7 is a low energy state because there is a negative interaction energy. So lower energy states will be the slowest mode, will take the longest to decay. So the Mpemba effect is enhanced. Right? So you see that larger negative view, this overlap curve goes down, the peak, far strongly non-monotonous compared to this thing. If you do the same thing for repulsive interactions, okay, so there's some technicality. You have to set the U to 0, otherwise this will not be the ground state. But that technicality aside, if you increase the effect of the value of U, you see again the same sort of transition, independent to collective decay. But here, 7, 7 is not a low energy state. It's actually a high energy state. And so higher energy states compared to this decays slowest. And so the Mpemba effect, that's not Mpemba, that's the standard effect. Higher energy states will decay slower. So the Mpemba effect, this overlap curve actually goes down. It loses the non-monotonicity for large enough U. Right? So interactions have a strong effect, and you can sort of get, as a function of interaction strength, you get 3 regimes with collective versus independent decay and enhanced versus no Mpemba and so on. Okay, so that brings me to the summary. Again, this I will not repeat. Basically, you can design energy landscape and use rare events on top of that to get this hierarchy of relaxation scales. I hope it will be possible to realize experimentally. There's some ideas. And before ending, I'll just want to flash another direction on which my postdoc Revati is also giving a poster. So this is sort of disconnected from what I said, but it's a series of works we are looking at quantum many-body networks. So for example, Umakant talked about all-to-all connectivity, and we are essentially exploring if you go outside of regular lattices, what sort of collective effects you can get that is not present on regular lattices, including the generation of long-range W states, getting non-ergodicity without disorder, and then some aspects of frustrated magnetism which can be controlled by changing local topology. Okay, and Revati has a poster on that. On that, I'll end, and thanks.
Thank you for spot-on timing. Any questions?
Is it easy to have both a localization and a tilted potential? Because
so the people, if you don't have the wedge shape, if you just have a single sort of slope, that is the Stark problem. So that has already been realized in experiments, and certainly in cold atom experiments, you have this tilted lattice on which you can see these block oscillations for, I think, several thousands of time periods.
So is that what you call it, Stark localization?
Yeah, that's what I call it. The eigenstates of the energies are Hamiltonian are localized around the sites.
Oh, Stark localization is because of
because of the tilted. Okay. So it's.
But why Stark?
Oh, I think it's because they use some Stark shift to generate the tilted lattice. I mean,
okay, so it's really related to cold atoms and the tilted lattice.
Yeah, okay. Yes. Has its origin in cold atoms.
Maybe one more. So you got it essentially by putting dissipation on the left side of the chain. Yes. What if you put dissipation on the right side?
Yeah, so if you have dissipation on all the legs going all the way from right to left, then I think the detection
What,
event will not be rare anymore.
No, but what about from top to bottom?
From top to bottom. Oh, you mean this way here and this way here. Yeah, so that's sort of what happens if you have a classical metropolis cooling algorithm that you have the energy lowering steps are favored compared to the other way. So in that case, what you find is that as long as there is some reverse process on this leg, you will eventually go down, you can go down here. If there is no process at all, then you just end up at this metastable minimum and just stay there. Right?
Do you include tunneling in the reverse process, or like the projecting at site 2?
Yes, the idea is that the
non-zero
tunneling,
projection?
the eigenstates of the tunneling are localized states. Right? So if you go to some eigenstate of the tunneling which is localized at this site, tunneling cannot really change that state. You need some sort of incoherent hopping to take you from a localized eigenstate.
So the fact that psi of d might not be 0 at the top is not sufficient to induce switching to the left side?
Not under the Hamiltonian alone, because you can just have an eigenstate of the Hamiltonian which is localized here. So you need the incoherent hopping to eventually take you from site to site. You can think of starting from an eigenstate of the Hamiltonian, and then the Hamiltonian does nothing.
At some point, you said that the eigenmodes with an imaginary eigenvalues are associated to coherence.
Yeah.
Why is it so?
Because you have some energy difference between the, let's see, this one. Yeah, so if you take this particular imaginary eigenvalue, complex eigenvalue, the corresponding eigenvector looks essentially the coherence between sites, the eigenstates localized at site 6 and eigenstate localized at site 7. So why is that happening is because if you think of starting from a superposition of two such states, then essentially the coefficients evolve independently of each other. And then you see that if you take the coherence, it has a imaginary oscillatory part which comes from the energy difference of these two sites, which is basically delta, the tilt. And there's a real part which gets added together, the decay rate from site 6 and decay rate from site 7. But the decay rate from site 6 is way bigger compared to the decay rate from site 7. So therefore, this just becomes approximately equal to site 6 decay, which corresponds to this population decay rate. So that's why they sort of club together. So this is like one group, this is another group, and so on.
So the zeros eigenvalue of the Liouvillean is just the ground that
just
zero?
there. Yeah.
Is that because you stopped like your slope? I mean, if that's right side.
Yeah, if you extend, yeah, if you keep extending more and more sides, that can eventually go down below this side, and then that won't be the ground state.
Right?
So the mechanism will still bring you to the site 1, but that will not be the ground state in that case.
You'll still, because it's biased in that.
It's still biased.
So it won't go to the ground state of the Liouville.
Of the Hamiltonian.
Of the Hamiltonian.
Yeah.
Still the ground state of the Liouvillean.
The steady state, you mean?
The steady state.
Yeah, so the steady state won't be equal to the Hamiltonian ground state if this is not lower. That's why it's kept lower.
Any other question? Okay, let's thank Chauvin then again. We are not too late, so let's reconvene at 15:45, and then I will have to nominate someone. And
Okay, let's start.
Sure.
Okay, good afternoon, everyone, and welcome to this afternoon session. I hope tea is keeping you awake. So the first talk in this session. Oh, okay. I am Rupak from Theoretical Physics Department here in RRI. So in this session, we have a talk from Professor Smijesh N. He is in Light and Matter Physics Group in RRI, and he will talk about beamline for attosecond nonlinear studies up to 150 electron volt. So I welcome him.
Thank you for the introduction. So, good afternoon, and thank you, the organizers, for giving me an opportunity to talk about beamline for attosecond nonlinear studies up to 150 eV. So, I'm Smijesh, as the chair mentioned. I'm again a local here, local experimental faculty. So this development is as a part of collaboration as well as my postdoctoral work in Umeå University. And in this particular beamline for attosecond nonlinear studies, I would be explaining the photoelectric effect at ultra-high intensities, the multi-photon, multi-electron ionization, and how we can use how we can study multi-photon, multi-electron processes in high harmonic generation process, or the use of high harmonic generation to look at multi-photon, multi-electron ionization studies, and some of the nonlinearities that we have found using this technique, and all attosecond pump probe experiments for decoding the electron dynamics after the photoionization process. So most of the talk that I'm presenting today is dealing with 93 EV. Oh, sure. Am I audible? Okay, good. So most of the work that I'm going to present today is dealing with 93 EV radiation onto xenon systems, because that has a certain importance. There are different systems people actually work with, attosecond pulse experiments, but then we are interested in this particular system because you can actually look at the process of exciting 4D transitions, 4D levels, and then kick out the electrons from the system and look at the cascading process afterwards. So one of such process that is published in 2007 is photoelectric effect at ultra-high intensities from in flash, where they utilized a 93 EV radiation and focused it onto a xenon system using silicon and molybdenum curved mirror. And then upon focusing, what they did was they measured the ionization events, or the ions that are generated upon irradiation as a function of irradiation intensity. So they varied the intensity from 2 into 10 to the power 12 to 7 into 10 to the power 15 to understand the system. Surprisingly, they have been able to record, they were recorded photoionizations up to 21 plus state. So this was very surprising to them, and then they tried to explain this based on the perturbative and non-perturbative approach. Both of them were very difficult for them to solve. So what essentially that they come up with as a function of xenon charge state, what could be the typical process that you can have in the system is what is explained here, up to 6 plus charge state. So there is a sequence of 1 photon ionization, outer shell ionization, and then followed by a 4D excitation and a Auger decay. Sorry, I mix it up. So basically, this process 4D excitation and then Auger decay. That way, one can generate 6 plus state. However, if you really look at 10 to the power, if you really look at 21 plus state, then it should be a sequence of multi-photon outer shell ionization process. So to look at experimentally again, what they have done is they have made a measurement by changing the irradiance as a function of ion signal. So by fitting this equation, one can find out what is the number of photons that are responsible for this process. For 1 plus, 2 plus, and 3 plus, it is found out that the process is linear. However, for 4 plus generation, 5 plus generation, 6 plus, and 7 plus generation, it is found to be nonlinear in nature. And afterwards, whatever the intensity of irradiation, the changes in the irradiation intensity doesn't affect the system. So it is found that it's more or less, the slope of the graph is more or less constant. Now, to theoretically interpret this one, there was another paper, came in 2009, where they have decoded what could be the pathways of xenon excitation. So if you send in 93 EV to the system, it can go to XC plus state or an XC plus state with 40 minus 1 level. So then there are autoionization possibilities, and autoionization can take over. It can go back to XC2 plus or XC3 plus, and there are multiple other pathways. So essentially, the theoretical model was based on one of the important crux is that the integral volume of the interaction process is, so the volume integral stays constant. However, the intensity is the only variable parameter there. With limited input parameters, they have modeled using perturbation theory. However, the experimental part is actually fitting properly around the lower intensity. However, the saturation it reaches is quite faster compared to what is predicted by experiment. So theory is following until 10 to the power 14 watt per centimeter square, but afterwards it's not following it. Now there is one more thing that is important, that to look at such a system, what they claim that only ion charge or the ion information. The information about ion is not sufficient to look at the process. We need a detailed information of the electron, energy, and angular spectra to look at the process completely. So that's what the theoretical survey. To look at this kind of process, one can actually look at, one can use two different technologies. One is FEL-based technology and the HEG-based technology. FEL-based technology tells you that, you have high photon economy and extreme multi-photon ionization is possible if the xenon is subject to such a kind of radiation with something like 10 femtosecond pulses. However, the price that you have to pay is the timing jitter. You don't have access to, less than, in the current system, current scenario, less than 200 attoseconds. So the short-to-short fluctuations from self-amplified spontaneous emission affects a lot in the system, because the energy stability in such a flash system is 15% and the intensity is 35 to 45%. So that kind of a fluctuation can lead to many different processes, and that introduces a lot of backgrounds. Whereas HEG technology, the biggest problem with HEG technology is that the low photon economy and two photon processes are rare. The good thing with this is that the jitter is virtually zero, and short fluctuation is absent compared to FEL technology, and the background noise, it's a background noise free technology. But the problem is low photon economy. If you have some development towards the generation of high flux in HEG technology, one can adopt this method as a complementary technique to the FEL technology. Now, with this in mind, I would introduce, because I work with HEG-based technology, I would introduce what is HEG and then so on and so forth in the coming slides. So typically, if you look at titanium sapphire amplifier CPA-based system, you have something like 25 femtosecond and 800 nanometer. You can reach energies up to 10 millijoules from commercially available, 10 to 13 millijoules from commercially available system. And if you focus that down to a gas medium, let it be neon or argon or anything, so you can generate harmonics of the fundamental driving pulse. And if you look at it through a spectrometer or XUV spectrometer, what you see is that you can have many different compliance spaced twice the energy of the fundamental photon. So this is what you get, and then if you really look at what you get as a function of time, you get an attosecond pulse train. So there are 1, 2, 3, 4, 5 pulse trains, but this is not good for an attosecond pump probe experiment. So we need to select a particular one. But given the limit of the system, it's a broad source of many different broad source which will be used for many different applications. For example, if you select a particular harmonics, you can get femtosecond XUV. And if you select a particular comb frequency, if you have a very good dispersive element for the harmonic comb spectrum, and then you can even go to narrowband CW XUV. So basically, it's a rich source. However, our area of interest is to generate isolated attosecond pulses than this attosecond pulse train. Basically, what it says is that you need to select this one out of the train. The way to go forward is eliminating those, but then how do we do that? One of the ways to go forward is to reduce the pulse duration from 25 femtosecond to shorter pulses, where you can have only 1.5 optical cycles or less than 2 optical cycles within the envelope. Now, how to do this? The method to do this is sending this, focusing this 25 femtosecond 800 nanometer onto hollow core fiber, using the principle, invoking the principle of cell phase modulation. You get you can generate broader bandwidth responsible for the generation of pulse durations up to about 5 femtosecond or less than 5 femtosecond. So if you have compressor optics like dispersive mirrors, and then you can routinely generate less than 5 femtosecond. So this is a straightforward technique, but the problem with this technique is that the energy that you get out of the hollow core fiber is limited to a certain amount. So for example, typically what you can go up to is 1 millijoule from out of the hollow core fiber. But what we needed to have such an HHC technology that is relevant to the nonlinear studies is mainly something like 50 millijoules of energy. So we needed 50 millijoules of energy. And also this 5 femtosecond pulse doesn't come, it has its own problems of dispersion. So as you propagate this 5 femtosecond pulses across, even in air for larger distance, what would happen is the dispersion in the medium that can elongate the pulse duration. So there is no point in actually, having 5 femtosecond pulses, sending across a meter or more than a meter in the experimental station. So what we do is we have to mitigate this problem, and also there is another thing related to the short pulse is that if you look at the cosine pulse and the sine pulse within the envelope function, they are different if you measure the intensity, or if you calculate the intensity, they are different in terms of intensity. So this would affect the T0 of your experiment. Time is equal to 0 of your experiment. So this is really important, and you need to stabilize this. And this stabilization method is called CEP. If you have mitigated all these problems, these are useful, but still the energy is low. Now, these experiments has to go hand in hand in experimental technology and the theoretical aspects, and therefore, so I would like to bring your attention to a laser system which is 11 meter by 5 meter, where we use OPCPA technology, where we have the original master oscillator and the broadband seed generation, as I just mentioned now, is here. And then you seed the beam onto the optical parametric amplifier, and the optical parametric synthesizer has 4 different non-collinear optical parametric stages, where you start with the dispersed 1 to 3 microjoules, and then after going through the preamplifier, the red part is lifted, red part of the spectrum is lifted to 1 point, and then you get 1.3 millijoules. And if it passes through the NOPA2, you get to 1.25 millijoule. And after propagating through the power amplifier, using the process of optical parametric amplification, one can reach 101 millijoule. So this, when compressed, it can generate 4.5 femtosecond pulses with 80 millijoules of energy. There's a massive energy that can be utilized for different experiments, and more details of this is available in this report. Now, with that, my own group actually did some experiment. So what they have done, that they focus the part of the energy, like 40 millijoules, onto a neon cell, and producing harmonics from 70 eV to 130 eV, and then focus it onto the xenon system. The xenon gas jet is actually focused to the spot here, and that is the focal plane of the iron microscope. The iron microscope detects the detects, this is a gated ion microscope. It can detect the time of flight measurement as well as the number of ions per shot if you look at. So what we identified or what we understood is that, during this process there are ions generated up to Xc5 plus. So if you compute the energy, photon energy requirement for the generation of Xe4 plus by adding this number to this number to this number to that number, it goes beyond 93 eV. So Xe4 plus, if at all generated, it should come from a double ionization process or something called a nonlinear process, which is, whereas the Xe plus, Xe2 plus or Xe3 plus can be generated by single photon excitation process. Now, we have also calculated the relative yields in percentage. You can see Xe2 plus is the most probable state, but then there are states with Xe4 plus and Xe5 plus. Now, to understand this process, a calculation is performed and it's compared to the experimental data of the cross-section of the process. Now, what we did was here, so the theoretical calculation is based on the sequential ionization method. So we use sequential ionization method to understand what is the cross section of the process, and then use these two equations which are available in the supplemental material of this particular journal, how this arrived. So how this equation is arrived, and then it is calculated here. So the cross section of the process is calculated here, and an average is taken. But by looking at the theory and experimental data, it is deviating very much more about, like, say 3.7 to 26 is about 7 times, 7 orders different. 7 times difference. And likewise, 115 EV excitation is giving you much different data. So the analysis started assuming that it is sequential ionization. However, which from the calculation we understood that this is not a sequential ionization process, considering the pulse duration of the attosecond pulses that we have generated. So 200 attosecond is the estimated pulse duration, or rather we would say 200 safely, but we have 150 attosecond. So 150 attosecond is insufficient to address a sequential process. So the process that if you really think about what is happening in the process, like, so you have to go from Xe to Xe plus state and then to the other state. So this is really a ladder kind of a process. But by the time you don't have pulse, you don't have the pulse anymore, and therefore this process is impossible. The next way to check whether this is a two-photon process is to look at the quadratic nature of intensity. So what you do is you change the intensity and look at how the ionization yield is changing. So when you look at that, this is proportional to I square, and therefore we confirm that this process is from nonlinearity. So there are, sorry.
What are the gray dots?
So that I'll explain. So this is basically, the signal from the image microscope. So the imaging microscope is actually looking at the interaction volume directly, and this is at the focus what's actually happening. A and B, so A, C, B and D are the linear. A is the linear and C is the nonlinear, and B is the linear at 115, and D is the nonlinear contribution at 115 eV. So it's basically, Xe4 plus, and maybe this is Xe2 plus or Xe3 plus, and this one is again Xe4 plus, Xe2 plus or Xe3 plus. So yeah, so from this data you can also calculate the Rayleigh range as well. I mean, I don't want to go that much detail into the process, but what finally the message is that we could have a nonlinear process in the system. That's the crux of the experiment. We need to have nonlinear experiment to actually look at the multi-photon multi-ionization event. So this experiment says that, okay, this is possible in the system. Now, if I want to look at the electron correlation, what I have to do, or the electron, to look at the angular distribution of electron in the process, what I should do is I should do a pump probe technique. For that, I need to improve the energy to another order of magnitude. So with this in mind, we improved the system energy from, so it was a 20 terawatt laser system we started with, and then we improved the system to 100 terawatt. So the energy changes from, sorry. Yes, it's a peak power, yes. Yeah. So 20 terawatt to 100 terawatt, and then this 100 terawatt laser system, when we explained this is like 4.5 millijoules at 100 millijoules of, 4.5 femtosecond at 100 millijoules of energy. Now, here in this, you can see the beam is focused using a very loose focusing geometry, which is using a 22 meter focal length, and then we focus it onto the gas jet producing XUVs, and it follows this line. And here we have implemented the XUV split and delay unit. And then if you send to the spectrometer, you can record the spectrum. If you send to the XUV CCD, you can record the beam profile of it and also measure the energy by using the photodiode. If you leave the beam going all the way, we had an ellipsoidal mirror which focuses the beam onto the X xenon target. So this is the experimental setup, and you can look at what's happening there. Now the pulse duration and the other characteristics of the laser is given here. So this is 4.3 femtosecond with a flat face, and you can see the spectrum looks like this. And when it is focused onto the gas cell, which is generating XUV, it is of the shape of this. Now, because of the 22 meter focal length, it's a pretty long system, and therefore one has to measure the pointing stability. The pointing stability, which we measured X to Y, is well within 4 microrad. This is more than sufficient to go forward with an experiment. Now, one way to improve the energy is to, when you selected the gas length and the gas pressure, is that you can experimentally tune the parameters of astigmatism and coma using a deformer mirror and shift the focus along the gas jet. So by doing that, we can see the improvement in the XUV energy within the window of 65 to 150 EV. Now we just improve this system one step further by temporal tuning, where we can change the GDD, TOD, and FOD by an AOM, acoustic modulator, and with respect to GDD, the photon energy is measured. Now, if you focus such a pulse onto the gas target, so we expected this to focus at 1 micron dimension, but in fact, due to the aberration, we could only focus it to 7 microns. So now the intensity goes down by 49 factor. And with that, what we have done some measurement, which I'll come to it. But then when you look at the XUV spectra, it looks like this, and the hole here in the middle is just because the split and delay unit, which are in the grazing incident path. So there's a split and delay unit which can move back and forth to look at XUV pump probe experiment. Here, what you see is non-modulated XUV spectrum, and therefore if you can filter this part out, you get isolated attosecond pulses. Now there are different ways to filter it. You can use the filters. And we were not stopped there. There is one more technological advancement happening together with this, that was on the temporal super resolution. What we can do is, usually when you have a spectrum, you can Fourier transform it and get the shorter pulses. But then that is the minimum pulse duration that you can get from the spectrum. That is called Fourier transform limit. However, if you introduce phase and amplitude corrections or whatever you want, I mean, you play with the phase and amplitude of the spectrum, then you can reduce the pulse duration below the Fourier transform limit, and we reduced it. This gave us more finer, non-modulated pulse around 100 EV to 140 EV in different excitation, different CP. So what we achieved is that we could have shorter pulses. We didn't measure it. We could have shorter pulses than what we started with. So this is one way to go forward. If you look at the global map of this work stands here, and this is an isolated attosecond pulses around 650 to 150 EV range, and yeah. So there is one which is not measured, and it's a train. So you can see how bright is the source for extreme ultraviolet nonlinearities. So with this, we tested one measurement I would say, because as I mentioned, the intensity was 49 times slower, so we could only achieve a nonlinearity. We could only achieve linearity with this XUV pump prop experiment. However, by changing the mirror, we of course we think that we can get to. We have already got the nonlinearity. We could come back to a nonlinear regime. But to understand electrons and how the dynamics is, we have developed an electron spectrometer which spans from 10 eV to 240 eV in one go with a resolution better than 2 eV. So, and we also calibrated the split and delay unit. The jitter associated with the split and delay unit is the actual jitter in attosecond experiment with high harmonic generation technology, and that is about 20 attosecond. More details are available online that you can find. So now you might ask what I'm doing here, because this is a part of my experiment work. Currently, I'm building an attosecond facility here at Ararai with accessible parameters upon commissioning are 80 nanometer to 30 nanometer with energies up to 1 nanojoules. We will be initially looking at XUV transient absorption studies in complex systems, including but not limited to plasma. So with this, I thank all the co-authors of this particular work. So I was there in UMA University. Still, the collaboration is going on, and Anil Ulier was the one, who did the theory for the thing. Per was the one who's helping me with the design of VMI, and Sylvian Malcote was also involved in. So he's in CAMAP, and Anna Lullier is a French citizen. French physicist. So she received Nobel Prize in the year 2023, along with Pierre Agostini and Ferenc Krauss. Pierre Agostini is again a French physicist. Thank you.
Questions?
Hi. Very, 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 very naive question. So it seems like whenever I see, so I'm really not from XUV, whenever I see talks about that, it's nearly often with noble gases. Why is that?
So in principle, you don't really. So the HOG generation part you're asking, right? Or okay. In general, yeah. See, this is a naive technology, and therefore, starting with, you don't want to have any background from any other interaction. So you start with a simple system to look at the process. But now the technology is evolved, and you can use other systems. Say, for example, solid state based HOG is also available. And plasma-based technology is also available. So it's not limited to noble gas.
Okay, so follow up, why are noble gases then a simple system in that context?
Could you elaborate which simple system, then I can explain.
Well, you said, well, we start with a simple system.
So basically there is no interaction. There are no interactions. So you don't want to worry about the interaction problems, one-to-one interaction between atoms. So you just ionize the system and you look at the coincidence measurements in most of the cases. Okay, we can talk if you really interested.
More questions?
Thank you. So in the Optica article, you showed that you actually reconstruct the attosecond pulse because
no, we didn't reconstruct. And in fact, this is one technology to reconstruct the attosecond pulse in an autocorrelation way. So we are building a system. I didn't tell that. We were building a system to measure the pulse duration by autocorrelation. This is a pump prop technique. So we didn't measure the pulse because it's way beyond the normal XUV range. So you usually have 30 EV to 70 EV where all the optics are available and you can have systems. But then here we are struggling with the energy. So it is 90 EV or above 70 EV, and making a measurement or a two-photon process is slightly challenging. And the technology for this coating, the optical coating, is also challenging. But then with the nonlinear studies, this is what part of the game. So we will eventually come up with the pulse duration, but then estimated by using Fourier transform. And we don't see two pulses when you do the Fourier transform. And the modulation, as you can see, there is no modulation at all wherever you pick the pulse, pick the spectrum from.
And just short follow-up, so your beamline that you're planning here, So what kind of diagnostics are you planning to
So initially I'll go for linear processes and look at autoionization processes in the low-lying, I mean not low-lying, towards the balanced lying systems. But right now we are under the development. We don't, this is not completely defined. There are two different experiments that is planned. One is interferometry with XUV pulse, and the second one is about the characterization of complex systems using attosecond pulses. One of the line is we are thinking along Redbug systems as well. That's in the future.
Thank you.
Cheers.
Any more questions? We can have another one if there is.
So yeah, thanks for the nice talk. So you were mentioning about the low efficiency of low efficiency
Yes.
in that, right? And I think compared to free electron laser, and it's already been, the technology has been there. And what are still challenges to enhance this efficiency? Because that's important for all your experiments,
so this is
right? And the motivation also in terms of competing with FEL techniques.
Okay.
So what exactly?
Yeah, so there are two questions. One question is why a different technology and how that can be, at par with the FEL technology. FEL has its own limitation, like pros and cons. FEL cannot resolve anything less than 200 attosecond up to the current technology. So there are, because you generate electron bunches and then you, divide them into two and then use the XUV pump probe experiment. But the generation of electron itself from a noise, and that can have the jitter shake. So if you really want to pinpoint some process which are happening within that time scales, that's not a good experimental technology. However, at the same time, if you really want to have enough photon flux, like if you want to go for 10 power 16 watt per centimeter square, HEG technology is not good. So these are not one-to-one technology, and we are not competing each other. So these are two different technologies to look at two different parts of the spectrum. But with FEL, you can even go to X-rays. Yeah. But pushing the limits of the energy, photon energies to higher energy is very limited. The only thing is that you get clean signal to understand what's actually happening in the interior of the system, which is really unknown till today.
Thanks.
Okay, so let's thanks Mrijesh once again.
Thank you.
So next speaker is Dr. Advait K. Varoli, and he will talk about revealing atomic correlations in warm vapors through spin noise spectroscopy.
Okay.
Hello everyone. I am Advait KV. I did my PhD here at LAM Group with Professor Andal Narayanan, and later I did a postdoc at Hungary, and from 2023 October onwards I am working in Lumin Group in Paris with the Professor Fabia Bruttenacker and Fabian Goldfarb, Professor Fabian Goldfarb. And so mainly I am working with the Rydberg atoms as well as with the spin noise spectroscopy. So today I will be talking about how spin noise spectroscopy reveals atomic correlations. And we already had a wonderful talk by Professor Dibyendu and Professor Saptarishi on this subject, so it made my life easier. So usually the noise is something which we don't want. We wanted to avoid it because it usually hides the information what we have. So this is usually a random signal and hides the information, and usually it's a problem, and there is no information containing in a noise. But physicist always finds a way to get information out of, useful information out of noise. And one such example is the famous Hanbury-Brown twist experiment conducted in 1956. So they could measure the angular diameter of a star by measuring the intensity noise correlations with two detectors. So what they did was they measured the intensity noise with two detectors placed apart by R1 minus R2, and they measured the correlation. And as you can see that when the detector distance is increasing, the correlation starts with a value higher than 1, and it starts decreasing and approaches 1. So from this correlation length, LC, one could calculate the angular diameter of the star by using this formula, and lambda is the wavelength of the light they have used. So, but today I will be talking about atomic systems, and here in this workshop the main theme is atomic systems, not about stars. So, in an atomic system, consider a paramagnetic sample of a spin half system, where since it's paramagnetic, the average spin of the system is 0, but there will be a spin fluctuation. So the variance will be non-zero due to the transit of the atom through the probed area. So the yellow atoms are the probed area. So the atom will be going and coming in a warm vapor cell. So through this transit of the atom, there will be fluctuations, as well as there can be spin exchange collisions in this system. So how can we measure this spin noise spectra optically in the system? So I'll be explaining the principles of, briefly explaining the principles of spin noise spectroscopy, and I'll be showing how the experiments we have done with a thin vapor, specially designed vapor cell, and the results which shows the atomic correlations. So imagine a spin half system in two-level spin half system, and we apply a sigma plus circularly polarized light to probe the system. So what happens is that so it's a note that it's detuned field. So in this case, the absorption will be nearly 0. So in this case, you can see that the real part of susceptibility follows the famous dispersion curve, and depends on the number of atoms in this level, the amplitude changes. And what if we introduce another the orthogonal sigma minus circularly polarized light? Since it has a different atom number, so you can see that there is a population imbalance. So you will have the similar dispersion curve for the real part of susceptibility, but you can see that the amplitude is different. So if you are probing at a different distance or a detuned field, so we can have different values of this. And due to this, when the probe beam passes or propagates through the medium, the sigma plus and sigma minus polarized light acquire a phase difference, plus phi and minus phi, and this is circular birefringence. And so I'll tell you how we use this technique. Okay, so imagine we have a linearly polarized light in the lab, and we send it through the atomic sample where we wanted to study. So within the cell, we can take decompose the linearly polarized light into circular components sigma plus and sigma minus. And as I explained earlier, due to the circular birefringence, it acquires a phase difference. And when it comes out of the cell, it is again a linearly polarized light. You can write it as a linearly polarized light, but note that there is a additional phase. So there is a polarization rotation happen to this system. Okay, but in our experiment, we don't have real population imbalance. What we have is a population dynamically population changing. So we have a fluctuating Faraday effect in our case. So this is the spin noise we will be studying. So, so how we will detect this polarization, small polarization fluctuations around nanoradians? So for this, we have a balanced photo detection. With this balanced photo detection, what we can do is that we can convert this polarization fluctuation into an intensity fluctuation, and later observe the spectra with a spectrum analyzer. So the power spectral density of this system will be shown like this. The peak will be peaking at 0 frequency because the average spin is 0. But if you apply a transverse magnetic field, you can make the spins precess around this magnetic field, and the power spectral density will be peaking around the Larmor frequency of the system. So in atomic systems, the first spin noise spectra has been studied by Alessandro and Sapolsky group. So it happened in 1981. So at that time, there were not really very good low noise lasers and good electronic technologies to analyze the data. Due to this problem, in the sodium vapor, they obtained the spin noise resonance as a error signal, and they have used an automatic plotter here, you can see here. And And it took another 20 more years for the physics community to rediscover this field and conduct a quantitative spin noise spectra. So the earlier one was purely qualitative. There was no quantitative information we could take from the spin noise resonance signal. So Croker et al. Group came up with the spin noise spectra study really quantitatively after 20 years. So this happened in 2004. So they did this spin noise study on the rubidium vapor cell, which is a naturally abundant rubidium vapor cell where 85 and 87 rubidiums are present. And what they did is that they could actually measure the Landau factors of both 87 and 85 rubidium. Also, they measured the isotopic ratios with this spin noise spectra technique. And also they have got information about the Siemens structure and the hyperfine structure of the system. And note that this Croker et al. Group is actually originally coming from a condensed matter community where they are also interested in spin noise studies. But in this spin noise spectra with optical studies, it is like a nearly non-invasive technique. So this is the interest for condensed matter physics community. So later by Katsoukarakis group, they increased the temperature of the system and they could increase the number density of the sample. And with this, they could see in the spin noise spectra, they could see the contribution apart from the transit time broadening, they could also see the spin exchange collision contribution also. But note that even at this number density, which is around 9 into 10 power 12 atom per centimeter cube, which gives a number density, interatomic distance around 200 nanometers. With this system also, this is a weakly interacting system where the atoms you can consider as identical but non-interacting spin systems. Okay? So, due to the non-invasive nature of this spin noise spectra studies with the optical method, condensed matter physics community also came to this use this technique, and they have done a spin noise spectra study by Ostrich et al. On the bulk gallium arsenide crystal, and later quickly this extended to low dimensional quantum systems like a quantum wells as well as quantum dots. So you can see again Croker et al. Here in the condensed matter paper. So the problem with the condensed matter system, I mean it's not a problem, but the spin noise signal contains many information. So a condensed matter system is a strongly interacting system. So it will be very difficult to understand the spin noise spectra from the contribution from the interactions in the spin noise spectra. So with a room temperature vapor cell, it will be slightly easier to understand the spin noise spectra with this system. So so in an atomic vapor, people have even tried on a identical but non-interacting systems. What they did is that they took the ρ1. So ρ1 is the density matrix of the spin half system, one of the spin, and you can see that they took it out of thermal equilibrium. Okay, so basically you can imagine that you have now you have an external interaction. So on this Glasenev work, what they tried is that they applied an AC external magnetic field and they studied the spin noise spectra, and they could see the signatures of this external perturbation on this. So this paper has been explained very well by Professor Dibyendu in the last session, and there were multiple papers from Raman Research Institute by Professor Saptarishi and Dr. Sanjukta Roy and also Professor Dibyendu on this, and especially on this out of thermal equilibrium condition. So one can ask another question, can we study the interatomic relations? Okay, so interatomic correlation in this vapor system. So not from a external field, but imagine that you have spin systems, but what you wanted to do is that start interacting between the systems. So so one could imagine a simpler step as imagine two atoms or two spins are interacting each other. So one can study this by using the temperature as the tool or knob to study this system. So you can increase the temperature of a vapor cell, like we are taking a 5 centimeter vapor cell, standard vapor cell in a quantum optics lab. In this case, if you increase the temperature from 80 degrees up to 180 degrees Celsius, the number density can be increased from 10 power 12 atom per centimeter cube to 4 into 10 power 14 atom per centimeter cube. So, but the problem with a 5 centimeter cell or a usual cell is that the probe beam won't be, you won't be able to measure anything at the end of the cell because of the large absorption of the beam because of this bigger cell. So this brings me to the experiments we do in our Lumin group, where we have a specially designed thin cell where we can solve this issue. And with this kind of a cell, we studied the spin noise spectra and we shown atomic correlations. So, so this is the specially designed 1 millimeter vapor cell, and we have this. We have a heater here which can reach up to 180 degrees Celsius, and so mainly this experiment has been developed and set up by Dr. Joseph Delpy. He was a PhD student in our lab, so. So his contribution was a bigger thing in this one. So we are continuing the same as Joseph started. So with this small cell, we can again, this is the same curve as I showed earlier. With the temperature, we can increase the number density, but the transmission, you can note that we can, even at 180 degrees Celsius, we still have a probe beam to detect the spin noise spectra. Now, with this temperature change, we can have an average interatomic distance ranging up to 75 nanometers, so that the atoms are very close nearby, so you can expect some interspin or interparticle correlations in this system. Yeah. So this is taken from the Chandrasekhar formula, which is 0.55 into. So the average interatomic distance R is 0.55 into n power minus 1 by 3. So yeah, it's just estimated from that. Yeah. So this is the experimental setup, and so here we have the new PhD student Elvin. So I joined in this spin noise spectra project with Elvin on this. So Elvin is here, and he is having a nice poster on this project. So do visit. So here we are working with the D2 transition of rubidium, and this is the Doppler profile of the rubidium. So we have naturally abundant rubidium cell where we have 87 and 85 rubidium. So for our studies, we are detuning the probe beam from the maximum absorption line of 85 rubidium f equal to 3 to f prime transition, and this we take it as a reference 0, and we detune the field by 1.5 gigahertz. We do this because we will be getting contribution from both the 85 rubidium Doppler as well as the 85 equally. So with this, we obtain the power spectral density, and you can see that here the temperature is not here, and the temperature versus the number density graph here shown here. So you can see how it propagates when I go, and this is the average interatomic distance for this. So the power spectral density, you can see that the 85 rubidium, which is a bigger one, and 87 rubidium, so happening at 15 megahertz and 10 megahertz and 15 megahertz for 85 and 87. And as we increase the temperature, the number density increases, and also the average interatomic distance decreases. And you can see that the power spectral density amplitude increases. This is expected from a non-interacting spin systems. So, but as soon as we hit the 150 degrees Celsius onwards, or 155 onwards, what happens is that not only the amplitude increase changed, and the profile completely drastically changes, and the bandwidth of this power spectral density increases, and there is a low frequency component start appearing, so that you can see here. Also, you can note that the 87 peak and 85 peaks are merging each other, you see. So this drastic behavior, so there are two contributions here. You can clearly see that the bandwidth is increasing, and secondly, there is a low frequency contribution appearing on this power spectral density. So we have studied first the bandwidth increment in this case. So we obtained the half-width at half maxima of the 85 rubidium contribution, and we plotted with the number density. And as you can see that initially when the number density increasing, the bandwidth increases, not much increment in the half-width at half maxima. But as soon as we hit a point, there is a transition in the physical system, and there you can see that there is a drastic increment in the half-width at half maxima. So there is a drastic broadening happening. And this broadening cannot be explained easily with a transit of the atom or spin exchange collision rate. So there was previous studies from our group on this spectra, and this dramatic broadening is associated to the resonant dipole-dipole interaction. So how did they did it like this? So imagine that you have two atoms, and one atom have some residual absorption, and it is in the excited state. Now it can spontaneously emit the photon, and the nearby atom can absorb it and go to the excited state. So this forms a dipole-dipole interaction in the quantum picture. So in a dipole-dipole interaction, the collective decay goes like this, and the shift of energy levels dominate at smaller interatomic distances. Due to this, these are the simulation results. Considering two dipoles are aligned with a distance of r, and with the distance r around 10 into lambda by 2 pi, you can see that the typical power spectral density where there is no splitting and everything. But as soon as we decrease the average interatomic distance, you can see that it starts splitting. Okay, so this is due to the dipole-dipole interaction, and in our real system, the distance is not fixed; it is changing, as well as there is a dynamic configuration change with r, theta, and phi. Okay, so due to this, we can obtain a power spectral density something like this one. So this clearly shows it's a collective spin dynamics, and you can see that it actually qualitatively explains the results we obtained in the experimentally, and at a lower number density, you can see that it still follows a usual single particle dynamics where there is not much broadening. This can be explained with the transit of the system, and there is no low frequency contribution. So previously, we couldn't study the spin noise variance of this system because our detector bandwidth was limited, and now we have a nice balanced photodetector with a bandwidth of 350 megahertz. So with this, we obtained the power spectral density, and you can see that for a 120 degrees Celsius temperature, the power spectral density follows something like this, and the signal contribution is only within the peak of the rubidium. But as we increase the temperature, there are multiple contributions. There is a broadening, there is a low frequency contribution, and the signal is still exists even at 200 megahertz detuning. Okay, so for this 120 degrees Celsius, we can still see this toy model as a identical non-interacting system, but this is not the case for a 179 degrees Celsius, where we have interatomic distance below 100 nanometers. So we measured the spin noise variance by integrating the power spectral density, and as you can see that with the number density increasing, the spin noise variance linearly increase with the number density. This is expected from a non-interacting ideal. Sporadic behavior starts appearing on the system. Okay, so this measurement has been taken with the detuning of 1.5 gigahertz, as I mentioned earlier.
Did you try to quantify that dipole-dipole interaction? What is the value of dipole?
What do you mean by quantifying?
Yeah, like we have a paper in 2015, again from Scott Cooker group also, means together. So there we have like rubidium and cesium, and we are calling like cross correlation spin exchange kind of to measure that what is the spin exchange value between rubidium and cesium. And the plots are similar, like the broadening and all those.
Okay.
So there we could quantify what is that spin exchange from those spin noise, but we of course use two light, like two beams for the probe.
Well, what we did is that we studied the broadening of the spin noise as a function of the density, and we recovered similar scaling when we introduced the spin noise, the dipole-dipole in the two-body simulation. That's all we did.
But the dipole-dipole interaction strength, I'm saying.
Yeah, well, this is given by the average distance between the atoms, and this is our number that we vary. And when we vary this number, we vary the dipole-dipole strength, so we can recover the strength of the dipole-dipole interaction.
So you can measure, have a measure of dipole-dipole interaction with density?
Sorry?
No, you can have a measure. Measure means like quantification of the dipole.
If our model was perfect, yes, but for now it's not perfect.
So with such a system, we obtained the spin noise variance nonlinearly increasing with the number density, and we have calculated the residuals from this linearly extrapolated fit, and you can see that from the number density around 1.6 into 10 power 14 atom per centimeter cube onwards, it follows a quadratic trend. So for our spin noise spectra, we couldn't fit a constant curve where a linear behavior and a quadratic behavior. We have a transition around when we hit a number density around 1.6 into 10 power 14 atom per centimeter cube. Okay.
Sorry,
So
y-axis is what? Y-axis is what here?
Sorry.
Y-axis is what here?
So this is the residuals calculated from the linear fit. So this shows that how much it is varied from the. So if you have a non-interacting spins, we expect a spin noise variance increment with a linear to the number density, and how much it is varied from this is calculated as the residual here.
Just subtraction.
Yeah, exactly. So this shows that we can fit this quadratically, and this indeed shows that we have atom-atom correlations successfully observed in the spin with the spin noise spectra. But what we wanted to do additionally is to have a tunability in this. How can we increase or decrease this interaction? So for this, we know that mainly this correlation is appearing because of residual absorption. So residual absorption can be changed by probe power as well as the detuning of the probe field. So we studied the spin noise variance with the detuning. So here you can see that we used two different detunings. One is 8 plus 8 gigahertz from the Doppler background. So you can see that it's much away from any Doppler profiles, as well as minus 7 gigahertz in the other direction. And in both cases, the spin noise variance is linearly increasing with the number density. So this clearly shows that we can indeed tune this interaction, and when we have a near resonant interaction, then we have atom-atom correlation due to the residual absorption, and hence the dipole-dipole interaction picture. And if we change the probe power at a chosen number density of 3.3 into power spectral density, we integrated the power spectral density. So the bandwidth is changing depending on the signal. So like at lower temperature, as I mentioned earlier, the main spin noise signal power spectral density is only on the 85 and 87 peak. But as you increase the temperature, you can see that there is a low frequency contribution also coming, and this extends up to 200 megahertz. Yeah, so for the data for higher temperature, we have to take the integration with the full thing. And for lower temperature, we don't need to take because the signal is not there. So the integration range changes with the temperature. Yeah, this is the main idea, because otherwise we won't get the information. We wanted to collect all the information. That's why we use a bigger bandwidth, like 350 megahertz bandwidth photodetector. Yeah. So here, this is a spin noise variance. With the input probe power, we changed from 1 to 3.5 milliwatt. But to avoid any detection problem with the, since the input power is changing, the detected power shouldn't change. So we kept the detected power around 160 microwatt in this case. And for a number density of 3.3 into 10 power 14 atom per centimeter cube, you can see that the probe power, with probe power, the spin noise variance increasing. So this indicates that indeed we can tune our dipole-dipole interaction or spin-spin correlation. We can tune it. We can increase it by increasing the power. This is understandable with the residual absorption, because if you increase the probe power, the residual absorption will also increase. And if you study the system with the different number densities, like for example very low, like 3 into 10 power 13 atom per centimeter cube, with the probe power input, you can see that there is no increment or change in the spin noise variance. So this shows that at lower densities we don't have this atom-atom correlations, but at higher densities we do have these correlations. Okay, so with this I conclude. So we have shown a good system which shows a signatures of correlations, and we can study this with the spin noise spectra. And this is the first time one shows a nonlinear spin noise variance in an atomic system. And also we shown that this interaction indeed is tunable with the optical parameters. And we explained a dipole-dipole interaction model, and this actually predicts the data qualitatively only, And so this also open up a new field with the spin noise spectra. You can study the complex quantum dynamics of any system, of some systems. Okay, so our resonant dipole-dipole interaction two-level atom model can only explain qualitatively. So it cannot accommodate the large low frequency contribution coming here. And probably this is because due to the binary model we chooses. So this is indeed incomplete. And if you use a toy model, if you see the uncorrelated part which is proportional to the, if the spins are not interacting each other, you can see a linear behavior. And as the spins are started interacting each other, you can see a quadratic behavior. So if you could fit the data with the alpha n plus beta n square, which we couldn't do, because we clearly have a transition at one point, one critical atom number density. So you can have a typical correlation length of 6 micrometers and corresponding to 300,000 atoms. So indeed we have many atoms. So by the way, note that this calculation is purely qualitative, so it's not purely quantitative. So indeed we have many atom correlations.
This is what mean field kind of picture? Mean field kind of picture?
Yeah. So this model will fail for higher atom numbers, I think. So we are open to discussion. So the Dr. Nikos is here, who is our theory collaborator, and Professor Fabian and Professor Nadia are also here. So you all can come and discuss. And also do visit Elvin's poster. His poster number 16. So he explains the theoretical model of dipole-dipole interaction in detail outside in the poster, as well as he give more experimental data. So we have a confirmatory test with a we have de-excited the excited state of atoms, and we shown that the atomic correlations or the quadratic spin noise spectra indeed coming from an excited state of atoms. So this has been shown in the poster. You do visit, and so this is our group. So you are all familiar with this photo because already Fabia shown this before. And this is our preprint, and yesterday it has been accepted in the physical review research, and yeah.
Questions?
So your low frequency part,
Yeah.
I mean, couldn't it be 3-body effects? Because I mean, your density is just ramping up as you're heating cell.
Yeah.
Your density is going up very exponentially.
Yeah.
So it is easily something that you could have. I mean, and the 3-body effects will wash out. You won't get. I mean, already you're seeing a broadening with the spin-spin correlation.
Yeah.
The 3-body is going to be, I mean, unresolvable in most. I mean, my impression would be that it would be. Do you have any comments on this?
We think that it is many-body effect, but with the simulation model, I mean, it's really complex to simulate the system.
No, 3-body should be okay because it's going to basically just become a noise floor actually for you. I mean, and that's no. Why not?
Yeah, I think Nikos
With the former PhD student, we tried to do the 3-body, and it did not improve the signal. So we stopped at that point. So for the low frequency nodes, there are many possibilities. We don't understand this properly now. One possibility is that it comes from light scattering in complex medium, because we are reaching optical density of 1 at this temperature. And so we cannot disentangle when we move the density like we do. We cannot disentangle effects that depend on the average distance with the spin and effects that depend on the optical depth. And what we would like to do, what would be the best thing, would be to make simulation or experiments that permits to disentangle the two, vary the optical depth at a given density and vary the density at a different.
So can I make a suggestion?
Yeah.
I mean, if you taper a cell, if instead of a 1 millimeter flat cell, if you have a tapered cell, so that you would have different path lengths, you would maintain the equilibrium temperature.
Problem with the polarization. You need several sizes. It's very sensitive in the polarization. If it's tapered like this, I'm sorry, but for the polarization, it's bad. No, we need several lengths. This is something we've done too. But we need same makers for the design.
Any more questions?
What would be your intuition if now you do a 2-photon excitation to a Rydberg state? You take your laser, the other one on the table.
This is exactly what we wanted to do.
Okay.
So we initially tried, but we couldn't see much signals.
What did you try?
We tried to put a 480 nanometer laser.
Okay.
To excite it to Rydberg state.
What was your 2-photon detuning? You were detuned, or were you on resonance? What were you?
Okay, so if I start explaining this, it will take more time.
Okay.
So yeah, maybe I think we can
discuss this later.
But with this, so the short message is that with this, at the moment we are still continuing this experiment. So we will have to optimize some parameters. So
Did you see any signal from the speed noise?
at this moment we couldn't because of some experimental problems, which I think I can explain after this because yeah.
Okay, thank you.
Yeah.
We can have one more if there is any. Okay, if there is none, let's thanks Advait once again.
Okay, thank you. Thank you very much to the organizers. And
Is it a break? Okay, it's a break. How? Okay, it's a 15 minutes break. Then we'll come back after 15 minutes.
Guys, let's go. We are starting.
Hello. So we can have settled down. Our next speaker is Professor Sadiq Rangwala from LAM department in RRI, and he will talk about symmetry transitions and stochastic dynamics in trapped ion crystals.
Hello, everyone. Yeah, you can hear me? Great. So I would like to start by thanking the organizers for putting together a lovely program. And so let me start by just making an introduction to myself. So I did my PhD at the Tata Institute of Fundamental Research in Mumbai. I worked in electron molecule scattering. I subsequently went to Orsay and worked with Alain Aspect and Philippe Bouillet on rubidium degenerate gases. And then I went to Max Planck Quantum Optics, where I worked on the cold molecule experiment in the group of Gerhard Rempe. And since then, I'm here at the Raman Research Institute. And I work on several things. I'm going to give you one of those things. And you can always catch me and ask me what are the other things I've missed out talking about. All right. So let me tell you about this. This is a very recent experiment. This is the latest experiment in our lab, which has, started giving us nice results. And these are the co-authors on a lot of the science, on the science work that I'm going to show you. So our group is called Quantum Interactions. And we have a startup, which is called Nexatom, which does many things. But yeah, that's a story for a different conversation. All right, so let me tell you. So ion traps, you have been introduced to ion traps. You have got helium electron bubbles, and you have had the talk by Umakant yesterday. And we have been working in ion trapping for 20 years. And we have been working in the linear Paul trap configurations. And this was not for any precision measurements, but this was to study ion atom interactions. And we have a great deal of work in the domain of ion atom interactions. In this context, we have a very successful Indo-French collaboration, which was concluded a few years ago. This is with the group of Olivier Delieu at Amicotin. And these are some of the people who have worked on the lithium experiment who are here. Niranjan is here, okay? Yeah. And in this meeting, and so on and so forth. What I'm going to tell you about is this experiment, which is the new experiment that we have built. This is a precision metrology experiment. And this is a clock-like experiment where the idea would be to trap a single ion and do metrological spectroscopy on such a system, on that ion. So what does this ion trap look like? It looks like two needles which face each other with a very small gap in between, and a cylindrical electrode which surrounds it on both the sides. So this is what is called the N-cap type Paul trap.
So what I'm going to present to you is the physics of clusters of ions in this geometry. And so this is what the instrument looks like. And in fact, since Niranjan told you about where his experiment was located, this experiment is located right beneath my feet in the lab below. Okay, so this is what the trap looks like. And essentially, if you zoom super in, you would get trapped ions there. And we work with calcium. Okay, so calcium is a very nice ion. It's very simple to work with. And simplicity is a good thing because there are too many moving parts in these experiments anyway. Right, so now, one slide summary of what are potential. And so if you trap many ions in an ion trap potential, so a any Paul trap is due to a combination of DC and radio frequency electric fields. Now, in the effective potential that is created because of the combination of DC and radio frequency electric field is that of a 3-dimensional harmonic oscillator. Okay? So in the adiabatic approximation, which is where we will be for most of this thing, and we can discuss why we are in the adiabatic approximation for what I will show you later, you have essentially the overall potential in which everything is based is a 3D harmonic oscillator, and then you have the repulsion between neighboring ions, which will give you, I mean, it's an all-to-all repulsion, but it's a 2 Rij kind of a, it's an Rij kind of a term. So now, if you have a 3-dimensional harmonic oscillator potential, you have, in principle, 3 curvatures, okay, in the x, y, and z. But because our trap has cylindrical symmetry, the beta is in effect 1, okay? And I will show you enough evidence during this particular talk that you can really believe that beta is 1 for us. And so x, the frequency along the x and the frequency along the y is, the curvatures are the same. And so there is a z with a different curvature. And that's basically because you're putting radio frequency on the tips of the pins, and that frequency is basically the lines of electric fields are either going out or going into that particular radio frequency electrode. And so natively, in the absence of any other potential, if you ground everything else properly, the curvature in the z direction will be twice the x and y direction. This is the same is true for atomic traps or whatever it is. It's just flux conservation. So, however, by applying small DC voltages on the pin electrodes, we can alter the potential and the stiffness of the trap along the z direction. And this is our tuning parameter for a large number of the things I will show you in what comes forward. All right, so this is the money shot, okay? This is basically the full crystallography of 4, 5, and 6 ions trapped in a 3-dimensional harmonic potential. All right? And what you're seeing here, these numbers are what is the value of alpha, which is the adjustable parameter along the z direction. All right? And what you are seeing that initially, if the first row is 4 ions, next is 5 ions, and the last is 6 ions. And so what you're seeing here is actually a laser-cooled, 4 laser-cooled ions, and because of the pressure from the z direction, they're confined to the xy plane, and they are in a square geometry. Now, it is important to kind of just appreciate that what you're seeing is not 4 points, but you're seeing a streak. okay, with some concentration of fluorescence. So this is a fluorescence image of the 397 laser, which is essentially cooling the ions. Okay? So now what you are basically seeing is this, because it is cylindrically perfect, the potential, or very close to ideal cylindrical potential, there is no every position is equivalent, which means that any photon momentum which is transacted with this particular thing in the xy plane, it gives you essentially a radial random walk on a circle. So since the ion trap is like this, the needles are like this, the ions are somewhere here, we are imaging in this direction, so we have Z resolution, and xy is essentially, we just see one slice of the xy plane. We see the projection of the xy. All right, and now you see that this is, for instance, a square. It is moving, it is distorting into a trapezoid when the x, y, and z are all the same curvature. You basically get a sphere, and this is basically atoms which are decorating the sphere in free motion. Okay, so this is what it is. So this is the full crystallography as can be measured in 3 dimensions for ion crystals.
Sorry?
Yes.
The ions, they move in the trap?
Yes.
Or they are, yeah, okay.
Yeah, they move. So so okay, I will show you what the numbers are. The numbers are coming. Okay? So yeah. No, that is because of some bowstring effect, okay? Okay, we can talk about this. It's not really part of this talk. We can talk about this, okay? I will show you stuff down the road. Okay, so now, so as you're transforming the alpha, you are changing symmetry because your structure is changing. So we need to understand what is causing the structural change in the configuration. So if you are looking at structural configurations, you can call them, stuff which can crystallize into multiple symmetries are called polymorphs. And there are basically 2 kinds of structural transitions that happen. One is where there's a point group relationship between the product and where you start, which is called a displacive transition. No bonds are broken, there's displacements. So this to this is what you call is a displacive transition. On the other hand, you can have reconstructive transitions, which are like graphite and diamond. You cannot get from graphite to diamond by just sliding things around. You have to break bonds and you have to make bonds, and these have different physics signatures. Okay, and we're going to see what happens now. All right, so now a little bit of symmetry breaking. So imagine that you have a potential and you have a string of ions. Okay, now you lower the symmetry and you can go into a zig or a zag. Okay, this is spontaneous symmetry breaking. All right, and you can, this is Landau theory for symmetry breaking. Now, what is causing the symmetry to break? What is the active thing that is actually happening? And that is the normal modes. So you have a structure, it has normal modes, and as in the Landau picture, as you are changing this parameter, it can be temperature in a real crystal or whatever, as you're changing that particular parameter, you will, one of the many normal modes that the system has, that will start changing, it will decrease, and it will freeze. So one of the normal mode freezes, that pins the entire, that basically precipitates a structural change in the crystal. So this is a symmetry breaking mode of a linear crystal, and this is a symmetry restoring mode on the other side, and this is the parameter. It can be anything, and you will see such a frequency spectrum. Okay, now who did it first? C.V. Raman. Okay, Raman and Nedunkudi in 1940 actually have the paper on how this symmetry breaking is happening. Actually, the paper is just this much, and it describes all the essential physics quite nicely. Okay, so if you are doing it for 4 ions, okay, you have a bunch of normal modes. The beauty of ion crystals is that we can film them, as you will see. We can actually, it's a small system. On a laptop, you can actually compute all the normal modes and so on and so forth, and you can actually pinpoint where the physics of interest is. And so what you are seeing is this is the full normal mode spectrum of all the degrees of freedom. And these are the symmetries which I showed you in the image. So first you start with this, then you break, okay, then you are going this way, then you are going this, then you are going this, and then you're going into a straight line. Okay? So that is this is how it's going. So now let me tell you how you go from a square to tetrahedron. Okay? How is this symmetry breaking? So this is the soft mode. On both sides you're going to 0. Okay? From the left and the right of this particular point, you're going to 0. And this is called a displacive transition. And so now, when you have a square and you're deforming it, you're basically doing a bifurcation, because you can, when the symmetry lifts, it either lifts like this or it lifts like that. So you have had a bifurcation from a singular square structure. You have had a bifurcation. But because we have azimuthal symmetry, we actually have the symmetry. You have a Higgs-like mechanism for symmetry breaking. This symmetry is broken in the octopole moment. Okay? Not the dipole, not the quadrupole, the octopole moment. This is where the symmetry and the Higgs and Goldstone modes can be recovered from such a thing, and we can actually measure this stuff. Okay, so what you can see, this is the symmetry, this is how the symmetry is broken, this is how the symmetry is restored. So if you want to break symmetry, this is the soft mode you have to put energy into. If you want to restore symmetry, this is the soft mode you have to put this thing into. So what you can do is, now you have a crystal, you have held this fellow at a certain alpha, and now you can set it into vibration by parametrically exciting this particular vibration, and you can measure at what alpha how much of this vibration is excited. Okay? And when the amplitude blows up and this crystal smears, you get essentially, you know that you have hit the resonance, and you put a point on the graph. Now here's so you get a series of points. You cannot go very low frequency, because then you lose, there's a limit to the resolution with which you can measure. Your optical resolving power is not good enough. And these points are just measurements. The normal mode spectrum is just overlaid. Rather, the measurements are just overlaid on the calculated normal mode spectrum. The green line is not a fit. So this is the precision that you can get in such an experiment. Now let me show you something that happens with 6 ions. Okay? What we are going to do here is we are going to go from a pentagonal pyramid to a square bipyramid. Okay? And this is the spaghetti of normal modes. Again, laptop worthy. Okay? And what we are going to show you is that here, in the normal mode spectrum, you have essentially such a structure. So your normal mode collapses, it abruptly cuts off, and at a certain frequency, and another normal mode emerges at a different frequency. Once again, this is an octopolar symmetry breaking. By the way, this is the only time anybody has ever demonstrated octopolar symmetry breaking. So this is positional reconfiguration, and this is what it looks like when you just go to the lab and measure it. You can see that one ion is blinking out, and when it blinks out, the plane in the center is shifting. That's because it has gone into the plane. The charge center remains wherever it always was. The center of charge is conserved, so the plane shifts to accommodate the change in the positions of the ion. And this is exactly how it works. So this is stochastic switching. And how does it actually, so well, I think I'm going to run out of time, but so I'm going to skip through a few things. So here is so what happens is this is the global minimum. Either the up or down pyramid is the global minimum, and this is the central part. And what you can find is that this is the square bipyramid. And if you position your alpha at this value, you see the spontaneous switching. All right? Now let me take you to 5 ions. Once again, octopolar symmetry breaking. But now here there is a very interesting case where on one side it is displacive, on the other side it is structural, okay, reconstructive. Okay? And we can actually see a triple point. 5 minutes? Okay, fine. So we see a triple point. I will not belabor you, but so what is the triple point? There is 2 sets of out of plane buckling modes and 1 first order transition. And the first order transition is basically measured by a hysteresis. So if you change alpha, you can measure a hysteresis curve, and you can make the so you have a combination of 3 different symmetry distortions happening at the same time. These, once you go up, okay, you can stay back on the way down for a long time, and it's like supercooled water. You know, you have packed in some energy, and then suddenly some collision or some disturbance happen, and it can collapse back into these more stable state. So it's all cool. So in the last 3 or 4 minutes, I'm going to tell you something else that we have done. This paper just came out like last week. Okay, so this is again 5 ions. This is a pentagon. This is 5 ions. But so we are going to only look at the square pyramid. Okay, now the square pyramid can exist either as an up pyramid or down pyramid. And there's a barrier and between the up and down pyramid. Okay? So what is the rate at which the system in this well is going to jump into this well? This is a problem due to Kramer in 1940 when he was looking at Brownian motion. Okay, and the question was, you put a particle in a finite potential, undergo in contact with a bath, when will the particle escape? And he came up with a theory. This problem, the Kramer thing, is super important. It is used all the way from field theory to protein folding, chemical reaction dynamics, everything. And the number of experimental validations is exceedingly limited. There are 2 experimental validations of a single particle, but here we have 5 ions, and they are all changing their position. So the generalized Kramer theory is the Kramer-Langer theory, which has never been validated. So we go about doing that. And in order to do that, we need to know what the height of the barrier is. Okay? So what does it all depend on? So I'm going to skip through a bunch of things. You can always ask me. Okay? So we have a barrier, and what you find is we can tune the barrier as we change the alpha. Okay? So the pyramid lasts for a range of alpha, and as we change the alpha, we are tuning the barrier. Okay, and so here if alpha is 1.17, you can see there are jumps. This is one up configuration of pyramid, down configuration of pyramid, and there's a frequency to the number of jumps. It is all stochastic. When you put, what do you call it? When you lower the alpha, the jumps increase, which is right. Because if you were to go, the lower the barrier, higher the rate. Excellent. So you can measure. And what is Kramer's theory? Basically of how fast it will go over the barrier. Well, there's the Arrhenius factor, which is always used to show you how chemical reactions will go up and down with temperature. And there is the frequency of the well, there's the frequency of the hill, and there is basically the damping factor. Okay, that sets you up. So it is a completely computable thing, and because we have a very limited system, we can compute this using molecular dynamics. Okay, so I'll skip through that. So here is what you have. So these points are molecular dynamics points of, as a function of alpha, if my system was at a certain temperature, if my 5 ions pyramidal system was at a certain temperature, what would be the rate at which it would flip? Okay, and you can get a curve, and you can always do it for different temperatures. So these are all at different temperatures. And the lines are Kramer-Lange theory. Okay, so this is the agreement that you get between Kramer-Lange theory and just a raw molecular dynamic simulation. So now we say, okay, there is pretty decent agreement in this range between Kramer-Lange theory and what you get from molecular dynamics, and you fit the data for a temperature, the rate data that we had got for the up and down pyramid, you fit it for determining the temperature, and lo and behold, you can derive a temperature of 1.86 millikelvin plus minus 0.03 millikelvin for the iron crystal of 5 ions. This is unique. It's very difficult to come with a measurement of crystal temperature. But there's one more thing. How do we know this is not just stuff which is happening? So, like collisions with the background or whatever it is. So collisions with the background this is where the barrier becomes so big that the background collisions are steady and they flip it at a proper rate. But what you can do is you can always substitute one of the isotopes. Okay, I'm done. Last slide. Okay, one of the isotopes, and you can see you completely, the mechanism for flipping the crystal is not, the mechanism for flipping the crystals is not through the plane like this, but it is actually substitution of a outer ion in a square and one of these 4 ions in the corner coming back. That is the low energy barrier. That is what is called, what the alpha is operating on. And so when you put 3 ions, now that permutation symmetry is gone. So what you get is a turnstile rotation. The 3 ions have to move, which is of course a lower probability thing. And so the dynamics freezes. Okay, I'm done. I'll take questions while you can go through the conclusions.
Yeah, we can have one question actually very quickly, and rest we can move for discussion.
No, so since you have a high-dimensional space, the Kramer's problem looks quite complicated. How did you identify a single coordinate?
Okay, so this is where Chauvin, really, so Chauvin had worked on, so what you do is there's a technique called nudged elastic band. Okay, now what see, finally, okay, in 15-dimensional space with 5 ions, 3 degrees of freedom, 15-dimensional space. In 14 dimensions, you are in a harmonic oscillator potential. In the 15th, or you're in a trap, okay? It's only in 1 dimension that a barrier is getting manifest. So finally, even in this particular situation, okay, there is one, in 15-dimensional space, there's only 1 dimension where there is this particular thing. Now so we have done a lot of numerics to basically get hold of this particular feature. And how do we find the height of the barrier? This is very important because everything is quantitative here. So that we use this technique called nudge elastic band. It's a great technique to find what is the height of a barrier if you have some knowledge of of the environment. We can talk about it. I will tell you about it.
Thank you. I was wondering, how do you measure or how do you estimate the error of, how do you measure the error of your temperature of the pyramid of 0.03
so that is so that is from you take huge, I mean you take different sets, you take a lot of stats. It's statistical error. Yeah. Right.
Okay, let's thank him again. Next speaker is Arnav Maiti, and he will talk about a new fluorescence microscope for optical lattices.
So, hello everyone. I'm Arnav Maiti. I'm a second year PhD student in Laboratory Charles Fabry. I'm working in the team of Max. So this institute is located in the south of Paris. So I'm originally from India, and so for the Indian people, I completed my master's and bachelor's from ISA Kolkata, and then I went for a PhD there. Okay. So is it fine now or no? Okay.
Can you talk?
Yeah. Can you hear me now? Is it fine or I can speak louder? Yeah. Okay. Yeah. Okay. Thanks. So today, first of all, I would like to thank the organizer for giving me the opportunity to present here. So today I will talk about a new fluorescence microscope for strontium-84 atoms in optical lattices. So before going into the details of the microscopy setup, first I would like to give some motivation as to why we are building a new microscope. So our goal is to study quantum many-body physics with ultra-cold atoms, and specifically to understand the collective behavior of strongly interacting quantum particles. For example, we want to understand phenomena like superfluidity, superconductivity, and magnetism, etc. So understanding the microscopic processes that gives rise to this kind of macroscopic phenomena, this is very challenging both theoretically and computationally. And Feynman's idea was that we can actually build a quantum simulator in our lab, which is kind of a controllable quantum system to study the properties of another quantum system. And quantum gases in optical lattices, they provide a good model for coherent quantum system, and these are not only limited to the condensed matter physics. So now I will try to introduce a model which was proposed by John Hubbard in the 1960s. And it was proposed to explain why certain metal oxides behave as insulators while they have been predicted as conductors by band theories that did not take into consideration the interaction between the electrons. And in this model, electrons are placed inside a crystal made by the ionic cores, and electrons can hop between the neighboring lattice site, which is given by the term J here. And also, if two electrons with different spin occupy a same lattice site, there is an interaction energy cost, which is given by the U here. Now, in our lab, we can make an analogous system with atoms in optical lattices. So, optical lattices are periodic potential that are made by interference of laser beams. And we can, as an atom, we can place either bosonic atoms or fermionic atoms. And if we put bosonic atoms, this becomes a Bose-Hubbard model. And the main difference is that multiple bosons can occupy one lattice site. So now when the J term dominates, then the ground state of the system is in a superfluid state where you have long range phase coherence. And when the U term dominates, then the ground state transitions into a Mott insulating state where the interaction energy freezes the atoms in place. And here different color represent different phases of the atoms. So at absolute zero temperature, the competition between these two terms drives a quantum phase transition, and which is strictly a property of the ground state. And here is the phase diagram of this quantum phase transition. In the x-axis, you have the interaction energy, and in the y-axis, you have the temperature. Now, if you work at a bit finite temperature, just above the quantum critical point, there is a quantum critical region where the low energy spectrum of the system is highly correlated, and it shows universal behavior. And we are exactly interested in this region here. So to study the physics near the quantum critical region, we want to measure the correlation between the atoms in position space. And one of the way to do this is using side resolved fluorescence imaging. This technique is known as quantum gas microscopy. So the basic idea is that atoms are trapped in an optical lattice, and we shine a resonant laser to excite fluorescence, and the scattered photons are collected using a microscope objective. And we can get a picture like this, which is shown here. And the information we want to get is the occupation of the lattice site. So there are mainly two standard requirements for a quantum gas microscopy experiment. First is that we need a very deep pinning lattice up to a millikelvin depth. And for this, either we need to focus our lasers very tightly, or we need a very high laser power. And this limits the system size. And also we need a microscope objective which has a very high numerical aperture, and also which is designed to be aberration free and diffraction limited. But this microscope objective is very expensive and it's hard to align. So in this talk today, I would like to convince you that it is possible to relax both of these requirements. For example, in our lab, we have shallow optical lattices with trap depth around 50 microkelvin. And our goal is to make a very large system to observe the criticality. And also, we have a very simple and cheap imaging system, which is easy to align. So we are using strontium atoms, which is a alkaline earth metal, and it has 2 valence electron. And specifically, we are using strontium 84, which is a bosonic isotope. And it has mainly 2 transitions. First one is the 461 nanometer blue transition. We use this for laser cooling, and also there is an intercombination line at 689 nanometer, which has a very narrow band, line width of 7.4 kilohertz. And we use this we use this transition for both laser cooling and fluorescence microscopy. So strontium has several unique properties. For example, due to this narrow line transition, we can laser cool the atoms to extremely low temperature. And also it has 3 bosonic isotope and 1 fermionic isotope. Now we are using bosonic isotope, but later we want to switch to fermionic ones. And for the fermionic isotope, the electron spin is decoupled from the nuclear spin, so the interlying interaction does not depend on the nuclear spin state, so we get SUN symmetry. And also there is a ultra narrow band transition, which has a bandwidth around millihertz, which is not shown here. This is known as the clock transition. Okay. So our experiment has 2 phases. First, when we want to study the strongly correlated physics, we keep the trap at shallow lattice depth where tunneling is allowed. But when we want to image the system, we freeze the dynamics by ramping up the power to the highest, and here the tunneling is forbidden. So during the imaging phase, we can consider the lattice as isolated pinning traps that is holding the atoms. And for fluorescence imaging, there are mainly two requirements. First is that we need to scatter enough photons to get a very high signal to noise ratio. Also, there should be no or little motion of atoms during this imaging. So that means the atoms should not get lost during this imaging process. So there are several strategies for fluorescence imaging. For example, we can give a very short and strong pulse to excite fluorescence at the resonance. And in this, so this is kind of a free space imaging, and in this case, the atoms will do a kind of random walk in the momentum space. And if we want to use this imaging, we have to use the blue transition because it has a very high scattering rate. And if we want to scatter around 2000 photons, we need a 20 microsecond pulse. And in that case, the atoms will be displaced by 0.4 micron. But in our case, the atoms are separated by 0.5 micron, so we cannot use this strategy. In fact, you can use this strategy if you have another system. For example, in tweezers, atoms are separated by 3 to 6 micron, and also people are using some kind of accordion lattice where they can adiabatically increase the period of the potential to like image in this regime. Another strategy is to use a very deep optical lattice, and in this case, you don't care if the lattice depth is higher than the hitting rate after n scattering events. So in this case, if we want to scatter around 2000 photons, we need a 1 millikelvin trap depth, but as I told you, we are working with shallow lattice, so we cannot use this strategy. And the final one is that we can do some kind of laser cooling while we are imaging. And in this case, the energy will reach some steady state after some point. And this is where the narrow band transition of the strontium comes into play. And due to this transition, so this transition has very narrow line width. That means the scattering rate is low, but at the same time, you have less recoil heating. So we can use this transition to cool and image at the narrow line at the same time. So this is the strategy we will apply in our experiment. So this is the outline of my talk. First, I will describe our setup, and then I will talk about how we image in shallow lattice, and then I will present some conclusions. So our lattices are at 1064 nanometer, and in the horizontal plane, we have two retroreflected beams that makes a square lattice, and with a fringe spacing of 0.5 micron. And at the highest power of the beam, we have a trap frequency around 95 kilohertz, and also we have a large horizontal waist of the beam because we want to make a large system around 100 times 100 lattice sites. And as a consequence, we have shallow lattice depth around 50 microkelvin. In the vertical plane, we have two beams that interfere at 12-degree angle and makes a vertical lattice with a fringe spacing of 5 micron. And we want to load a single layer of this vertical lattice to make a 2D lattice. And also, at the highest power of this beam, we have around 10 kilohertz trap frequency. And for this beam also, we have large horizontal waist and shallow trap depth. For the imaging setup, we have a single aspheric lens inside the science chamber with a numerical aperture of 0.64 and also a focal length of 19 millimeter. So firstly, this aspheric lens is very cheap. And also, second thing is that if you want to use a very good microscope objective with multi-lens system, which corrects for all the aberrations, it only works for a certain region. For example, if the atoms are displaced by, for example, 200 nanometer, the very good microscope objective, it will not work well. But the aspheric lens has a very high depth of focus, around 10 micron, so it is very easy to align with the atoms. And this aspheric lens performs very well on axis, but if you go away from the optical axis, the performance gets reduced, but I will show you later that it is actually enough for our experiment. So another drawback is that this is not achromatic. So we use a single lens to focus the photons onto a camera, scattered photons onto a camera. And for the camera, we are using a camera which is usually used for astronomy purposes because this has very high quantum efficiency around the red laser, also has a very low read noise. And overall in the system, we have a magnification of 11. This is only possible because you have a very small pixel size on the camera. And again, this small magnification makes the alignment pretty easy. So as a conclusion, we have a very cheap and simple imaging setup. So this is how we prepare a 2D gas. So we have strontium oven, and then we pass it through the Siemens, we pass the atoms through the Siemens fluor, And then we trap the atoms in a mud chamber where we cool it into 2 steps. First, we use the blue light to cool it down to the millikelvin temperature. And then we use the red light to cool it down to the microkelvin temperature. Next, we transport the atoms from mud chamber to the science chamber using a dipole trap. And then we load it into a crossed optical dipole trap, and we use evaporation cooling to make a Bose-Einstein condensate. And then we turn on the vertical lattice and horizontal lattices to make a 2D lattice, and we perform the fluorescence in the 2D lattice. So with our system, we have been able to get side resolved images of strontium. Here, for example, this image is taken with 1 second exposure, and it has essentially no background. And here, each red dot you see are single strontium atoms, and we collect around 200 photoelectrons per atom, and also we have around 2% loss in the system. So this image represents around 100 lattice sites, which is a very big field of view. But now, if you zoom out, you can see that aberration starts to appear at the edge of the picture. And to quantify how well our spherical lens work, we divided the picture into 5x5 grid, and we reconstructed the point spread function in each of the grids. Now, if you look in the middle grid, it looks very good. And if I fit the middle grid, middle PSF with a ARE disk, we get an equivalent numerical aperture of 0.61. And from the diffraction limit, we can get an NA of 0.64. So at the center, we are very close to the diffraction limit. But if you go away from the center, you can see aberrations just to appear, mainly the coma aberration. But in the middle 3x3 grid, it represents around 100 times 100 lattice sites. The PSF looks almost good enough for our experiment. Okay. Now, if you have a system, for example, in the tweezer system, where the atoms are separated by 3 to 6 micron, you can easily pinpoint the atoms by simple side-by-side thresholding. But in our case, the lattices are separated, the atoms are separated by half a micron, and so that the atoms are not optically resolved. And also the PSF overlap between the atoms prevents the simple side-by-side thresholding. So we have to do some kind of image analysis. So this is generally known as the reconstruction algorithm. So if we know the PSF and also the lattice grid, we can kind of pinpoint the atom position from a picture like this. Okay. So now, so the standard method for the reconstruction algorithm is a deconvolution method. But in our lab, we have recently developed a new deconvolution method, which is known as the optimal linear estimator method. So this method is more robust and accurate than this deconvolution method. And also, this new method can take into account the spatial variation of the PSF over the whole region. So I do not have the time to go into the details of this reconstructional algorithm, but if you are interested, you can see these 2 papers. Okay. So now we took the middle 3x3 PSF, and we generated some simulated images where these images actually represents what we have in our experiment. And this is a simulated images, so we already know where are the lattice positions are. And from this, we can get the estimation of signal per lattice site. And from the estimated signal, we can get a histogram of occupied and unoccupied site. And if we put a threshold in this histogram, we can detect the actual atom position. So this is a reconstruction algorithm. So of course, we will make some mistakes, and this is given by the detection error rate here. So this is the error we make in this detection algorithm, and we have around 2% loss in our system. So for the detection algorithm, we can actually use an averaged PSF over the whole system, over the whole region, or we can also use the whole PSF calibration. That means we can feed into the detection algorithm the spatial variation of the PSF. And this is only possible because we are using the new detection algorithm. This is not possible with the previous deconvolution method. So if we use an averaged PSA over the whole region, we can get around 1.7% detection error rate. But if we use the whole PSF calibration, we can get below 1%, which is 0.9%. So it's not visible here, but it's 0.9%. Okay. So as a conclusion, the spherical lens works well for our purposes. Now I will talk about the fluorescence imaging in the shallow lattices. So as I told you before, our strategy is to cool an image on the narrow line transition of the strontium, and we are using a single propagating beam red laser for this. And our goal is to reach a quasi-stationary state characterized by a equilibrium temperature which should be less than the trap depth and also a large scattering rate. Now, for the laser cooling, the good conditions are we need a narrow line transition, and also the recoil energy should be low, and also we need magic trap, which means the ground state and excited state should have equal polarizability, hence equal trap depth. For strontium, we have already a narrow line transition at 689 nanometer. Also, we are within the lamp decay regime, but at 1064 nanometer with linearly polarized lattices, we are not at the magic polarizability condition. So the excited state is less trapped than the ground state in our case, and in this case, the laser cooling will not work well. So we needed to optimize this polarizability ratio to go to a good condition for the laser cooling. So for strontium ground state, we only have the scalar polarizability, but for the excited state, we have both vector and tensor polarizability. And the coefficient of this vector and tensor polarizability depends on the trap polarization and the magnetic field with respect to the direction of the magnetic field. And we saw that if we have a circularly polarized lattices and if the magnetic field is along the lattice direction, then we can get to a magic condition. So with this, we have lattices in different configurations, so we cannot put the magnetic field along all the lattice direction. So we decided to put it in the vertical lattice direction, and in this configuration we have almost equal polarizability for all the lattices. But now the atomic dipole is unfavorably oriented with respect to the aspheric lens, so we lose a bit of collection efficiency. And now with this configuration, the laser cooling should work well. And to quantify if the laser cooling works well, we did some loss rate measurement where we took 10 consecutive images of a dense cloud, and we looked at the decay of the signal. And from the decay of the signal, we can get the lifetime of the atoms inside the trap. And this loss rate.
You have 5 more minutes.
Sorry?
You have 5 more minutes.
Ah, okay, thanks. And this loss rate will depends on the detuning and the power of the laser. And here the general trend is that if you go closer to the resonance, then the loss rate increases. And if you are away from the resonance, then the laser cooling works well and you have less loss. But at the same time, we have to scatter some photons. And for the scattering rate, the general trend is that closer to the resonance, and if you increase the power, the scattering rate increases. But if you go away from the resonance, the scattering rate decreases a lot. So you need to find some optimum between these two parameters, which is given by the figure of merit, which is if you divide the photoelectron counts by the loss rate, and here clearly you can see some optimum in this case. So this means that we can scatter around, we can collect around 100 photoelectrons within 1% loss. But if you want to collect around 200 photoelectrons, we have to live with a 2% loss. So to conclude, we have a new quantum gas microscope in Palaiseau, and also we have a much simpler and cheaper imaging setup. We can also image a very large volume optical lattices. Also, we have an improved reconstruction algorithm. And this is where we got so far. So we have been able to see quantum phase transition with our microscope. So we start with a superfluid phase, and if we increase the lattice depth, we go into a Mott insulator state. And then if we increase the atom number, we can see a cupcake-like structure, which is an indication of a Mott insulating state. So here in this picture, because of the harmonic envelope, in the middle you have 2 atom per lattice site, and in the outside you have 1 atom per lattice site. And if you have 2 atom per lattice site, due to the light-assisted collision, it will get lost. So you get a hole in the middle. But in this case, you have 3 atom per lattice site in the middle, so 1 atom survives. In the ring, you have 2 atom per lattice site, so it gets lost. And in the outside ring, you have 1 atom per lattice site. So this Kafka-like structure is the indication of the Mott insulating state. So this is our team, and thank you for listening.
Yeah, thanks, Arno, for finishing in time. And questions?
Thank you, Arnab. For your lattice, you've went with the configuration with the retro-reflected lattice. And what would be the effect of this choice? Would it be better if you choose to send your lasers without retro-reflected beams? Would it change anything in your magic trap calculation? Did you take any of this into account?
No, I mean, if we don't use so what configuration
I mean,
you have in your mind?
when you're in a retro-reflected configuration, you lose power on the way back.
No,
not necessarily.
No, it's the same power. Like it's, for example, like if you give like 10 watt, it will like retro-reflected also be 10 watts. So
okay, you're not losing power. Okay, thank you.
Any more questions?
Thanks for the talk. Could you come back to the slide where you show the losses versus the...
Yes.
No, I think it was almost at the end. Yeah, exactly. So when you increase the power, the losses are reduced. It's due to what? Some kind of light shift effect. For example, on the first column, yeah.
You mean it's not uniform? Yes. So this is because. So I have a backup slide on that. Yes. So this is because, like, so for example, in our case, like most of the atoms are in the ground state, and then the scattering is from, like, if we consider in the sideband regime, the scattering is from like M0 to N0 state, and the cooling transition is M equals 1 to N0 state. Then from this low power, if we try to increase the power, then there will be light shift from this detuned transition. And then due to this light shift, if we want to be on resonance on this cooling condition, we have to be closer to the resonance. But then if you go above some certain power, then like things become very complicated, and you need to consider all the above levels. Like you cannot consider only the 2 levels or 3 level diagram. You need to consider all the other motional sidebands. So then due to this, you need to again go back.
Another question. So what is the intensity of the beam that you are using? Because you put the power in microwatt, but what is the size of the beam?
Size of the beam, or just
the waist of the beam to get the intensity of the laser?
Yeah, it's a very large beam. It's 1 millimeter waist or diameter. And if I give you the saturation intensity, it's like 25 microwatt corresponds to like 150 I said. So we are highly saturating the transition.
Is there any more questions? Okay, if not, let's thank the speaker again. With this, we conclude this session, and yeah, over to Nadia.
Yeah, so there was to be a show and tell. Did we thank all the speakers for the session? No. Okay,
let's thank all the speakers in this session. Thank you.
So I wouldn't be in need of someone. So can I plug my computer or go online to just show to go to the show and tell session? So I don't know if the participant from India got the link, because I don't have the email address of everyone, to access to this file, where we can put together. Wow, so yeah, I created that collaborative file. So it's from a pad, so everyone can enter and write whatever they want to go along the theme I suggested. So you remember, do you have some technical points you would like to address? I think I sent the link to Sanjukta. So okay, so everyone has the link. So I'm seeing 3 people connected. Okay, so 2 anonyms I love. So you have the link. You can enter whatever you would like to address there. And we had dedicated time now and tomorrow to discuss these. So I see that along the technical points, Anthony said he would be in need of a good software. So Fabienne at some point wanted to discuss atom cells. I don't know if whatever was discussed across the talks is answering the questions, or if we just want to set up atom cells here. So it's to be, I can organize the discussion. We can decide to address the topic and how much time we are going to dedicate, but if you don't enter any point, we cannot discuss anything. So you can, so this is for the technical points, and this was meant to trigger. So if you deem that II is not going to change your life, you can actually say so, either putting your names and saying so, and we will just give the mic to whoever wants to comment on what is written there. So that was my beautiful slide about the kind of points I suggest we address together, or maybe we see how much we can talk to each other discussing those points. So technical points is there. So apparently, fingerprint or specificities, I was the only one to enter something. So I had one small point about rules and discussing them, and unconventional collaborative ideas and shared files. So we'll see if it works. And for perspective, I had much more success. So I was personally quite interested in the way Alexei in his talk organized the way to think about photon-photon interaction, saying that there seems to be wow, I'm going to die soon. There seems to be some fundamental roadblock, and the ways to go around them. So I was interested in him then putting back his slides up and just digging together slightly, apparently involving Alban or whoever made work along that line of work, to say how this fundamental roadblock was overcome in current things. So misconception is something I find very interesting. So apparently Alexei discovered things about Raman cooling. No? In which state are you now? You understand it or you don't understand it? So you understand it now? Okay, so we should make a measure together once he's in the right state. So whether hand-wavingly or with one slide, it will be interesting to hear about it. So apparently we don't understand read-bear blockade. I'm sure I don't. But so is the truth that it works fine or it doesn't? It doesn't. Okay, so actually the world is not working as it should, and deterministic photon subtraction is not working as it should, and Fabienne has something to discuss there. And we have a dedicated career spot, so this is maybe for younger scientists. If there is a specific question you want to address and to ask everyone, it's also maybe the file where you can enter your question anonymously, like, is research really exciting? Or if it were to do it again, would you do it again? And we can vote together. So it's completely anonymous, as you see. So if you want to enter your name, thank you, Alban, you can. Or if you want to, write your name so that we remember, you can. But if you just want to enter an anonymous question or an anonymous point, saying, I really don't see the point in doing all these things with atoms, because atoms are well known and they are an uninteresting system, so go ahead for it. Okay? So that was trying to get things started again. So I think I'm going to stop now for this show and tell session so that we can together go nicely and visit the lab of Sanjukta and Saptarishi. I can maybe just kill those two. So this one, I'm sure you guessed. So the idea is to, or my idea at least, is whatever we are doing collectively and we are used to call a conference and a workshop, maybe we have the possibility and the power to slightly change it. So maybe people doing posters can also have talk. Maybe people doing talks can also do posters. Maybe we can rely on the organizers to do stuff, but also let them, in our case, the ladies, enjoy also the science part of the conference and take collectively the responsibility of organizing some sessions. And maybe we don't need to have dedicated people to put together the list of posters. For example, we have a collaborative file for posters that you can all enter and just copy-paste your name, the name of your co-author, and the title of your poster, and this will be done. So this was just the point I wanted to make there. And about rules and discussing them, and an example of good practice. So organizing a national, quantum national initiative in France and discussing diversity also in my lab and inclusion and discussing how it was done in other labs. I've realized that some labs put together some rules like to, against harassment of all kinds, against a toxic environment in science, and I was very much against not putting a step just where I stand. Okay, and so I was very much interested in that set of rules and discuss it with the people who put it together. And the interesting idea that I wanted to pass around was what they answered to me. The interesting part was not the set of rules that we could take and bring to our lab. What was interesting is that those rules were discussed every year among the team, and that they all actually very much enjoyed the fact that they discussed each of the points, trying not to give examples or react too much, and that they thought that it was very interesting to do this. So I just wanted to pass that around. For the French people, it's what they do at Lipsis. Okay. So who's organizing the lab visits? It's Sanjukta, so go ahead.
So the speakers and participants who want to visit the RRI labs, please stay back here, and we organize in batches to visit the labs.